Shall we start? Or the? Well, I don't have a presentation anyway, so I can start in the meantime, and maybe in the meantime they can fix the lights. Good morning, everyone. Good morning to the 11th PolInSAR workshop. You might have noticed that this is a bit of a special occasion for various reasons. It's special because we are organizing this PolInSAR workshop together with the Biomass workshop, which we already did in 2015 for the first time. Now, as we are approaching launch, we thought it's a good idea to bring the communities together again and to exchange a bit ideas and views and how far we are with biomass, because we are actually in full swing with all sort of preparatory activities. Most importantly, and you might have noticed on the desk, on the post on the desk, that this is a special PolInSAR meeting because we celebrate 20 years of PolInSAR. So the first time this community met was in 2003 and was at that time a very small meeting which built on two studies that were started at the agency. During these 20 years, this community was growing and thriving quite a lot. You were responsible for a lot of innovations, for a lot of developments in SAR. And actually, we are quite happy that in the meantime, or this week, we can welcome more than 200 people meeting with us here in Toulouse. Also very special because we are meeting in Toulouse. It's the first time we meet outside Esrin, and to celebrate this anniversary in the beautiful city of Toulouse. And this gives me also a good occasion to thank our French colleagues, especially CNES, CESPIO, the University of Toulouse, and Superior. You helped us organizing this very nice meeting here. You also helped us last week to organize a training workshop, which was also very successful and very much appreciated, I think, by the students. And with this, I would like to hand over to Jean-Claude Cerise to give a welcome from CNES.
Thank you. Okay. Thank you very much. So good morning, ladies and gentlemen. My name is Jean-Claude Souiris, and I am presently the Deputy Director of CNES Technology and Digital Directorate. I have the great privilege and the great honor to welcome you today on behalf of the French Space Agency, the Centre National d'Études Spatiales, to this event, which is shared between the PolInSAR workshop and the Biomass workshop. So bienvenue à Toulouse, welcome in Toulouse, and hopefully beyond the technical assets of this workshop, I hope that you can take some time to discover during the week the charms of our city, the so-called Pink City. You have a beautiful panorama from this balcony. And on behalf of CNES, I would like also to thank the many people who have been involved in that conference preparation, the scientific community, which is composed of countless experts coming from all over the world, as well as the organizing committee, which made an amazing work to set up this event, especially the group from Toulouse and from ESA. So I should talk a few minutes about the achievement of CNES and the contribution of CNES to Earth observation mission. In addition to its contribution to biomass, CNES is also involved in many missions dedicated to climate change studies and climate monitoring. We can, for example, quote a microcarb, which is a cooperation with our friend from UK, in order to characterize the carbon sinks. We have been also developing YASI-NG, which is a new generation of infrared sounding radiometer for meteorology. We are involved in Trishna with the Indian Space Agency. Trishna is an imaging system which will observe the Earth in the thermal infrared. And also a cooperation with DLR, which is Merlin, in order to characterize the CH4, which is the methane, and which is one of the main greenhouse effects. So having said that, I could also talk about our contribution and our support to the biomass mission, but I'm sure that my colleagues from CNES, from CESBio and from ESA will do it much more better than myself during the week. And I must actually confess that I'm not very keen today on making an official speech, you know, because when I read the scientific committee members list, as well as the author index, I must confess that I was suddenly filled with a lot of nostalgia and excellent memories of a time where I was happily part of this polarimetric radar community back to more than 15 years ago. And I have wonderful memories of this time, and I would like to recall some of them and to share them with you. I remember the first PolInSAR workshop, which was held in 2003 during some sunny days in Frascati. So we celebrate today the 20th anniversary of the PolInSAR workshop. And it has been a very long road since this workshop with many achievements that will be discussed during the week. I remember the relentless Yves-Louis Desnos and his endless energy to organize a workshop and events promoting the radar. This event included a series of CEORSAR workshops. One of them took place here in Toulouse back in, I don't know if you remember the year, it was about in 1999, almost 25 years ago. It was mainly in the framework of the preparation of ANVISAT, the program preparation. And I remember also the talent of Yves-Louis for singing. I remember some, maybe during the week you can prove that you didn't lost this talent. And I have a few pictures at home of this thing. I remember, of course, and I will always remember Tuile Tohan, how much energy and how much passion she dedicated to radar science and more specifically to the biomass mission, together with Sean Quigan, Fabio Rocca and all their team of young scientists. And on a more personal note, I should admit that I will never forget how much I owe to Tui for many reasons in my career. And I remember also all the colleagues and friends from this period whose contribution have been so fruitful, be it in the theoretical domain or in the experimental domain, and who are still in the landscape. So I will do something quite dangerous right now. I try to set up a list, and obviously some of them will be forgotten, and sorry in advance for that. So I have a wonderful memory of Shane Cloud and my friend Eric Potier, Laurent Ferrofamil, so please also very pleased to meet him again today. Rida Tuzi, Pascal Dubois, Irena Hansek, Keith Rene, Kostas Papatanasiou, which I met today, it's a great pleasure. Elise Collin, Philippe Payou, Malcolm Davidson, Nicolas Fleury, Klaus Sipal, Francesco Mattia, Francesco Sarti, Tom Hensworth, Carlos Lopez Martinez, Andrea Monti-Guarnieri, Henning Schriver, Yamaguchi, Masanobu Shimada, Lars Ulander, Wolmoon, Sasan Sachi, Marco Lavalle, and some others. Wonderful memories of all these guys, and most of them actually were, of course, already present and active during the first workshop in Frascati in 2003. And these strong memories make me realize how close this small and very solid polarimetric interferometry radar community works to some extent like Hotel California. I don't know if you remember the last two verses of the song of Hotel California. Hotel California conclude by, you can check out anytime, but you can never leave. And I think that such is working the radar polarimetric interferometry, which is our community, which is a strong and very pleasant community. I don't forget also those who passed and who led their imprint in space radar history. In particular, Professor Wolfgang Borner. A lot of us were very impressed by the contribution of Professor Borner and his personality, as well as Jacob Wenzel. Both of them had a great influence on us. I don't know the new generation, but I'm sure that given this magnificent genealogy, that this generation share the same spirit, the same energy, and the same talents. So in conclusion, I wish you a very nice week in Toulouse and a nice success for this conference, and I hope that all of you will enjoy your stay in Toulouse. Thank you very much.
Okay, so good morning. It's a real pleasure to be with you. Actually, I should have been to a science strategy conference, so I send all my best people there in order to be with you, because it's really my community, and I would like to celebrate with you the 20 years of work. When I say 20 years, it's 20 years of PolInSAR, but it's not really 20 years in SAR Polarimetry. Actually, I started to work on, my first job on ESA was to work on the Maestro, on 36R Maestro campaign data, which were fully polarimetric, multi-frequency SAR data. So I don't know if you can put the first the slide for the presentation. And I've prepared, I've not prepared the slide actually, which is very bizarre, because usually we always prepare our slides. I've been given a number of slides from the community to mark a bit the anniversary. Okay. So, if I go to next, yes. So this is the, actually we did a poster for the PolInSAR 2003. The real work started in 2000. We were made aware of a thesis, of a few work actually, not only one. The thesis of Kostas Papatanasiou, the work of Shane Cloud, and we saw that there was really something new and interesting, and we really wanted to push this domain. So we issued an ITT, and we got so good proposal that I had to go back to contract and say, can we place 2 contracts? And it was a bit difficult, but we managed to place 2 contracts. And it was so interesting and so successful. Let's organize a workshop. Let's gather this community and see. We are expecting maybe 20, 30 people. We got over 100 participants and a lot of young faces and new people. And it raised a lot of interest, and we worked together to define a number of things, which were, of course, present the geophysical parameter, assess tools we could have to support the work of the scientists, demonstrate the latest technique, make recommendation, prepare for future mission, get the data shared. So in essence, it's an open science project. It's one of the first one of its kind, where we were really gathering the community, sharing knowledge, sharing tools, sharing data, and making progress, and trying to make progress from there. So this is really, I think most of them have been already quoted by Jean-Claude. The starting team, I think most of them are still working in the domain, even some being in pension and still working in university. I'm thinking about Masanobu, for example, just one example. So you have this, we started with this list of scientists, and it has, there were not so many young people, so we've been working on that quite hard. And I'll show you later how we did that to get you on board and get new faces working in this domain. So some pictures, it doesn't, from 20 years ago, of key contributors at the time, and still you had, if I take, of course, Eric, Shane, Professor Ashash was my director, and he was somebody pushing a lot in the SAR domain, no-brainer, working with us. You have on the right, top right, Mark Doherty. He was a pioneer in SAR interferometry. He's the one who created a similar kind of process actually around fringe and to develop the domain. Xiongtsang Li, Dirk Hoekman, Sean Quegan, Thuy, and Professor Berner was always after me saying, in ESA you don't have polarimetric mission, but I have a slide which is a bit the response to this query and question from the community. So you have here a list of activity we have been active, not only organizing workshop and writing paperwork and recommendation, but making them happen, acting on those recommendations. So we have been working, of course, we had the opportunity to work with our Japanese colleague from the time. So it's not nothing new. We worked in the past with DLR in the campaign, GPL with 36R. We have been funding some campaigns, and we started to organize the first polarimetry course around PolSAR Pro, actually, and I'll speak a bit more after on PolSAR Pro. We organized a symposium in Rhodos, and we have a famous, by the way, product of this, which is the Golden Fish Club, but I'll explain to you privately what it means. It's a group of scientists who have had a nice experience in Greece, and that's why we call it. And they are all specialists in polarimetry. We have done working with PulSAR, in-orbit demonstration study, moving a bit from airborne data to spaceborne data with their different geometry and trying to apply our algorithms there. A number of AO, of course, around RadarSat-2, so always proactive, trying to continue fuel data to scientists to do the work, campaigns, AO with Canadian Space Agency, and lately we have done even more recent AO. So 2014 Sentinel-1 launch is not fully polarimetric, but we tested a few things with Sentinel-1. Actually, I should say, I was told by my colleagues in ESA, don't touch Sentinel-1, it's operational. And we decided not to do that, but to put the scientists to work on the data. And 80% of the first result of the mission were delivered by scientists. So we did well at the time to not to listen to and to be a bit disruptive in ESA. Then we had a number of other, there is of course in parallel we had all the sequence around the biomass mission, which I'll give some slides about. Some latest PolInSAR workshop, 2017, 2019, proposing a Professor Borner Award, which was something good. Hopefully it's continuing. The 10th workshop, unfortunately, was virtual, but here we are all face-to-face and happy to work all together. Here is first slide prepared by Eric. Eric Potier, you have the source on the right side. So we decided to look at moving a bit from science to application and get the community to write a number of chapters in a book on what we can do with polarimetry for various applications. And this is the compendium which has been prepared by the community, showing progress and making a bit explaining to students how we can do things from SAR polarimetry and PolInSAR. Then 20 years of the SAR toolbox. So these are really the font and the slide from Eric. Once upon a time, the story of a simple toolbox. They had the idea actually before the PolInSAR workshop to create a toolbox for students, for PhD students, even master students. So it was presented, and we thought it's a great idea. Let's support the work of the university and Eric and Laurent and go for it. So you have the first version which we released in 2003 to the community. So Eric mentioned here, we worked a lot to prepare the young community, the young scientists. We have done 34 trainings from 2005 to today in Europe and also in China. Actually, we tested in China some different form of training, which we have imported back in Europe, and this was also something very useful. I know there are some Chinese colleagues from the Academy of Forestry or the University of Forestry in the room. So this is really the evolution of PolSAR Pro to PolSAR Pro Bio, Bio of course for biomass, which was an evolution of the latest version. And we are continuing, of course. Eric did this, again, this nice slide as a conclusion. It's not a conclusion, it's really a preparation for the next step. Thanks, of course, to all who supported the development, the community, having really contributed to PolInSAR. And I say happy birthday to all the community and, of course, for these 20 years. Then he made this one, which I have to present, which is really trying to continue. Of course, now we have the mission. It's not time to release the pressure. It's just the time to really move forward and get the tools further made further available in a different environment. So we decided to integrate it in this ESA-NASA map platform, which we are working. Actually, we had a meeting last week with the NASA colleagues as they came to Italy, and this was one of the topics which was discussed among others. And by the way, we are creating with NASA also a group on application, just for you to know, and working together with them. So the evolution, so Magda prepares this slide, explaining in detail what it will do in its future context. So I'm not going to go in the detail, but of course we are going to expand beyond the biomass mission, looking of course at NASA, ISRO, SAR, NISAR, etc. So if I look at the evolution, you have a series of slides which have been contributed as well on the evolution of what we can do on a forested area. And the first one is really this, actually this is one of the first really triggering of the technology we had from the work of Costas and the group at DLR, showing really the use of PolInSAR from airborne data. And this is, as I was saying, plus the work of others. I'm not sorry if I miss one name or another. It's not by. It's just to say this triggered really the work and the studies, the original studies. Then we have. It's not in the same or in the order I put them, but it's okay. I can survive like that. This is really the where we are today, exploiting Tandem X data in terms of mapping forest height. I had put this one at the end, but it's coming here now because I thought it's really showing state of the art of what we can do over Amazon, where you get this and the comparison of Tandem and Jedi forest height retrieve, which is actually quite good if you look at this cloud of correlation. Now we go back to some of the original work. So it's not starting, and not everything started in 2003, fortunately, as I was saying. I was dating it back to 1989, but this is already some of the first publication of what we can do with for retrieval of biomass by tree. Then there is a PolInSAR work from height generated from PolInSAR from land forest from Dubois and Fernandez. And then we had some of the first tentative of tomography from the TomoSAR, which is a work from all these contributors showing a tomographic reconstruction from airborne data, I believe, over French Guiana. So I'm going fast because I know you are going to explain this in more detail later on. Then we looked at the mapping of high-range biomass in tropical forests with TomoSAR, and looking at what we can do, what we can isolate in terms of component in the layers, canopies, around the topography, and making some progress. So from 2016 and 2019. And then some of the last work on radar intensity above ground biomass, looking at different application up to TomoSAR intensity at main canopy height correlated to AGB, and some of the results from the data set of TROPISA and ONERA. Now, looking at some ice application, so here we have a lot of also historical work. Here I've quoted some work from Armando from 2003, which was presented at the time, which used the quad-pole behavior of ice over ice, and the first step including interferometric formation in models, publication by Jürgen Dahl and Kostas. Then we go to some of the models which were developed to retrieve parameters, work from Irena, I think it's, and also Kostas, and the use of polarimetric tomography, which is currently being used, and we have some nice animation coming up of what can be done in terms of sensing a glacier with different, showing here in top left the illumination, the information we can get from the surface, 25 meters below the surface, 50 meters below the ice surface. And if it sticks well, the animation show you the going through all these layers and how we can infer the results. So very promising application. Then we go to ship detection. Ship detection, there is, of course, a lot of work which is being done on ship detection. I was just discussing some other application on ship, which we are doing currently. The use of polarimetry, of course, is a help, and this is a domain which will expand further with all the upcoming mission we have. We are also working on other techniques such as, but I'm not, they were presented at the CSAR meeting in Svalbard in the beginning of May. We are looking at inverse SAR, which is classical, but some more of less classical technique, which are the microdoppler, where we can detect the vibration of the engine of the ship, the rotation of the antenna on board, and these kind of things. And ultimately also the SAR video, which we are getting when we increase the integration time of up to 25 seconds at X-band, and we have a lot of good stuff there. So some of the use of quad-pole data for ship detection, and then a bit of machine learning, which is the fashion in town, and which is of course good when you have good data and you understand what you are doing with the data. So we have done training. So this is also important to train the young generation, get them up to speed with tools, with professors, and we have done a lot of efforts and still continuing. There was a training last week organized in Superhero, and so I have also some slides on that. And it's complemented by a number of online courses. We have developed a platform, actually with German ministry and the university, a spin-off of University of Vienna. We have developed yocollege.org, which is a way to have in Europe a platform for education and having the massive online course, having resources for training and sharing it with the community. Then data, it's all about data. I mean, the truth is in the data before it's just theory. So we have shared data from the beginning, mainly from campaign. Here it's talking about all the campaign. We need, of course, in situ, we need documented data to do calibration and validation. It's important to be sure about what you are doing. So this is a series of campaigns we have been supporting and continuing. And we are also working now, I mean, recently, Francesco has been taking over I created the name, and he did the job, actually, the PUMAS initiative to work with our Argentinian colleagues to get hands on SAOCOM data and to be, so there is currently an AO open, and I look forward to you to use this data. We need absolutely to get hands on this data to exploit them for science and application. So this is a continuation effort. We have not only the data, we have programs to support the work on those data, and I'll speak about it at the end. Because if there is no budget available, you're missing something, and from an ESA perspective, I've been working on that. So looking back at the evolution of a proposal for we have a mission. We have a mission which is biomass. It's the first of the polarimetric mission in ESA. There is a long history. It was using at the beginning only SAR polarimetry, but with the PolInSAR technology being available in the background, of course, the evolution made it to let's include the technology. Normally there were 3 slides, but okay, it's okay. So it gradually we integrated the polarimetry, PolInSAR, and then tomography to have a complete exploitation of the mission. And this is where we are today in 2023. The launch is, Klaus will confirm, the launch is foreseen in Q1 2025. Actually, if you invite me, even in pension, I think I will join. But it's a message to Klaus. Even, yeah, that's something I would do. And then we have the future mission. So they are all, finally, I would say, it's a response to, I had a different slide showing a bit so it's not the good version of the presentation, but it's okay, I can. Rose L will be quad-pole, Sentinel-1 next generation will be quad-pole. So it's a bit the answer to Wolfgang. On the long run, we have listened to you. Here are coming up a number of fully polarimetric missions, and for this community, it's really, this is why I'm saying it's a start. It's not 20 years anniversary and we stop. It's the start of a new era where we'll have really operational mission, but still remember serving the scientific community. So we're looking forward to that. So you will see here how they are defined in terms of application and service. To do things, of course, evolution of Sentinel-1, which is really, I would say, workhorse of delivering application operationally. We use Sentinel-1 a lot, but not in isolation. It's used in combination with other sensors. With Sentinel-1 and other sensors, we are capable to, for example, to provide information to ministry in charge of the Green Deal implementation in Europe. So we have done that recently and opened a solution for Austria, actually. And it's online, and so you can have a look at that. So we are using Sentinel-1, Sentinel-2, and answering to what they need in terms of checking how the policy is implemented in the country. Rose L, which is, of course, most awaited L-band, fully polarimetric data, and which will, of course, bring all the benefit of the L-band data, which we know since the end of the 80s and the first mission. So last week was the PolInSAR Biomass workshop in Toulouse, just to confirm that we are continuing, and a lot of young people, young faces, happy faces, and presenting. Can you put the good version of the presentation? Because here I have a small problem, which is the one I gave to Magda, because I want to show you something about how we can cover the work of the scientist with budget. I can take question because the time they put up the presentation, but it's just 2 slides, so it will be maybe 3, because there is one which I wanted to show a bit, to give a bit of a perspective of no, bon. I think it's better when you have the presentation here, because you can at least, that's my view, there is no dependency. So do you have it? Is it here? So if I move, yes. That's a good one, actually. That's the one I wanted, one of the one I wanted to show. When we think about the pioneer in ESA, just to recall you, I worked on the ERS mission, ERS-1. And from before the launch of ERS-1, we were developing already operational application. We have prepared a processor which were a very streamlined processor, close to, they were fast really, and they were already, the operational application were ship detection and fisheries monitoring. So it's something we have done from the outset. Then we worked on I worked on the NVSAT mission, but it's not talking about me, as principal engineer, trying to move from a classical SAR to something with an active area antenna. It was only dual pole, but we had the difficulty already to pass from a centralized amplification to a distributed amplification with so many TR modules, singing and dancing. Actually, they were a bit singing and dancing on the shelf even. So some of them were changing characterization while was being stored, and we had to deal with a number of funny things. Then the operationalization of that came with the Sentinel-1 A and B. Just recalling that the scientific community was strongly involved in developing application for Sentinel-1, despite the existence of operational services. Then we have biomass, and we have the evolution of the Copernicus program with ROSE-L, A and B, and Sentinel-1 next generation, fully polarimetric. And of course, last in town is Harmony, which is, in terms of application in number of domains, will be really a huge prospect of what we can do with this mission. So just to say that it's a message back to Wolfgang and also to the community. ESA has been working extremely successfully also on preparing new SAR missions. So the future is great for this community. So if I go quickly, normally after that, yes. So the outlook is we have this Copernicus program with associated project and services, which gives really data continuously for service, for responding to policy, delivering operational application, but also a lot of new science, of course. And best example, we have a lot of nice examples. We have been, from the work of a student, we have been capable to develop a system to monitor trucks using Sentinel-2 and the parallax effect we have on the sensor. So it's a parasite, more or less, but it's being used operationally. And to deploy this wall-to-wall over several years in Europe, it took us 2 or 3 months. So the Earth Explorer program, of course, is about exploring new things. And what we are doing with the funding we have is looking at what we can do beyond mission objectives. So you have the mission objectives, which were, when you conceive a mission, you say, I'm going to do that, that, and that. And us, we are looking at what we can do on top of it. And I've seen some of the early work on the exploitation of biomass over the ice shelf, which is quite fantastic, by one of our postdocs. And this kind of things we are doing, also biomass over the ocean and other things like this. So the field is really to be explored. And us, in ESA, we have a program which is called EOS Science for Society, which is covering science application, also industry, prepare industry for being first to market, but also developing application. And we have on the bottom right what is called Sentinel user preparation. So we have a program by which we want to be ready to exploit ROSE-L, Sentinel-1, and next generation. So working with polarimetric data and moving the domain and preparing for the next generation services. So that's my last message. So we can support some activities. There will be a lot of opportunities to work on the Explorer, but also on the Copernicus Sentinel next generation mission. So that's it. Thank you.
Thank you, Jean-Claude, for the welcome, for the nice welcome speech. Thank you, Louis, to recap a bit the history of this community. I think it brings back very nice memories to the people here. Before we enter the sessions, I still have to make some announcements and logistics informations. Is the presentation? Ah, it's here. Now, how do I? Next. Just to remind you of the objectives of this workshop, we have put together end-to-end both communities, PolInSAR and biomass. Of course, there's big overlaps. Just to remind you of the objectives of the PolInSAR meeting. As in the past, we want to provide a forum to exchange. So for us, it's very important that you use the time here to discuss with your colleagues, that you give us recommendations, that you tell us what are the gaps, the challenges, what are opportunities that we can take in future. To present the latest exploitation results from full airborne, but also now from spaceborne systems that are available, to review the retrieval of biophysical and geophysical parameters and their challenges, to make recommendations for algorithm development and new products, to support the preparation of new missions, of third-party missions, and of the mission exploitation of future PolInSAR missions. And Yves Louis has shown a growing family of satellites that will have this capability. And finally, to present innovative polarimetric applications and idea for future mission concepts. And we will hear already today some new concepts that are coming that have been selected only recently, and which will have a lot of polarimetric capabilities and interest for scientific exploitation. For biomass, of course, as the mission suggests, one of the key questions, key objectives here is forest science. How can we contribute with these observations to advance forest science and carbon modeling? International reporting, this is more the societal feedback of this mission, giving back to these reporting obligations, which become more and more important, and where people are using more and more satellite missions, and where there's still a lot of open questions how to use satellite mission in this context. We will also use here specifically a lot of time to discuss ground-based measurements for validation and calibration. We have actually a separate session for this. And biomass science that goes beyond forestry. So biomass, as the name suggests, is not only a forest mission, it has also a lot of potential for ice, for deserts, for ionosphere monitoring. So I think there's a lot of interesting stuff that is going also beyond forestry. Coming to the program, you will find the program also outside. If you need access to it, you have here the barcode. It's also outside at the reception desk. You can look for all the talks. We tried to minimize as much as possible parallel sessions. So we will have, we will start with the PolInSAR sessions, with the classical sessions on the missions, on methods of PolSAR and polarimetry. We will have on Wednesday then, so Tuesday will be mainly biomass focus, but in this room here, so we have this common room where we tell you a bit about the status of the biomass mission and what you can do with the biomass mission. We will then have forest application sessions that are again more PolInSAR, but also of common interest to the biomass community. On Wednesday we have the application sessions for PolInSAR, so agriculture and land applications. And in parallel to that, we have two biomass sessions focusing more on the science side, so validation, modeling of carbon, and also on the multi-mission context of biomass. So not only looking at SAR missions, but also at other missions that are available to measure biomass and at other products, and how we can benefit from this growing family of biomass mapping missions. These biomass dedicated sessions will be in the room on the back. There's a big sign there, so you cannot miss it. And we will meet there separately. Then on Thursday, we will go back in the PolInSAR, talking again about methods, mainly tomography, but also applications, cryosphere applications. And we will have one parallel session in the evening again, and this is specifically focusing on the validation of biomass products. We have recently started a small project to set up a global network of biomass measurement sites. And we wanted to use this occasion of this workshop to gather a bit the community and get feedback also from the Earth observation community to tell us what they need and to discuss a bit with you. So you're happily invited to join this session if you like. And on Friday, the last session, hydrology, and then the workshop recommendations and wrap up. Oh, goes like this. You have the biomass sessions. Very important for us is to get feedback from you. And this was always the strength of this community, that you were really very creative. You were telling us your needs. You were telling us what we should do. And we were, Yves Louis already showed it, many of your ideas that were created in this community ended up in dedicated activities. We had campaigns, we had studies, we had toolboxes. So again, very important for us that you provide this feedback. There's not a lot of time for discussion. We don't have dedicated discussion sessions. So this time we thought we do it a bit differently. We have this online tool, Padlet, sorry, I always get it wrong. Padlet. You can log in. For every session, you will find a room there, and you can anonymously type your recommendation. You can also give your name if you like. You can make complaints, whatever you like. Every feedback is very much appreciated. You also find on your seat a barcode, which you can use to access this Padlet and to provide your direct feedback, even while we are talking in the sessions. We have not only that, I'm always using the wrong one. We've also put in the classical way. We have put in some paper charts at the poster session, at the coffee break. The best ideas usually come when you drink a beer and you take notes, you scribble on your napkin. So we follow this a bit. We will not serve you beer, but there will be coffee. And during the coffee breaks, if you discuss things and if you come up with some nice ideas, take your pen there and write it down, and we will take note of it, and we will integrate this in the recommendation session. This is also a message to the session chairs. On the last day, all the session chairs will need to go to the floor and we'll present one slide on the recommendations of their session. So I really would like to ask you, when you finish your session, maybe you can prepare one slide with key findings, key recommendations, opportunities, gaps, what you like to see. You can also use the Padlet, whatever. To see what the community responded. You can also go back to the paper boards to see if there are some comments that you can integrate. That brings me to the social events. Because we are a nice family, we're nice. It's a celebratory event. So we want to celebrate a bit with you, and there's a couple of social events. First of all, so lunches are every day from 12:50 to 14:10. There's no lunch served here, but there's a lot of places around this place, and you can go to a restaurant or grab a sandwich and have it outside on the terrace. Just please be back on time again, so that the people after lunch have also your full attention. Today, at the end of the session, we have an icebreaker that is sponsored by ESA. On Wednesday, we have an aperitivo that comes with the poster session that is sponsored by CNES. And also on Wednesday, there is a big celebration in the town. There's the Fête de la Musique, so you're free, of course, to enjoy and to take a lunch outside. There's a lot of bands playing in Toulouse on Wednesday. But because we are 20 years, well, we are here to celebrate 20 years, we wanted also to do a special thing. So next to PolInSAR Pro, PolInSAR Sim, I don't know, PolInSAR whatever, we have the PolInSAR Party. It's a new polarimetry thing that we introduce here. One of our colleagues, Clément, thank you for that. He organized a room in a cafe very close by here, so it's just 500 meters down the road there. It's a Delirium Cafe, where we have a room to party a bit on Thursday. And we will meet there at 9 o'clock, so you can have a lunch before. And a lunch, sorry. So you can have a dinner before, but you can also buy something to eat there, I think. I think there are some snacks served there. But we will have then our own floor, and we can celebrate there a bit. There's also a bit of a surprise. I've heard that Yves Louis is a good singer, so we will see. We have organized something there. So it will for sure be fun, and I hope I see many people here on Thursday night to celebrate with us. Group photo. It has been a long time. I think the last time we took a group photo was in 2015, so we thought we would like to have a photo again of all of you. So today, before the icebreaker, we will gather all here to take a photo. So don't run away after the last session. Wait a bit, we take a photo, and then you can go for the drinks. You can just repeat what Yves Louis said. Thanks for coming to Toulouse and to join us on this workshop. And I hope you will have a good time here. And we will have several occasions to celebrate, but we also have a very interesting program and a lot of very nice science talks. This brings me to the end. But before I... one more thing I forgot, two more things. First, for the recommendations, I said that it's very important for us to provide feedback. Today, at the last session, we have one cancellation, and we will use this to review a bit the recommendations from the previous workshops and to summarize. The program is already updated. So that's basically the start of the feedback. The recommendation station starts today before the icebreaker. The second thing is the Wi-Fi. There's a Wi-Fi in the room. The name is PolInSAR Biomass, and the password is the same. And you can also, if you have problems to connect, you can go to the reception. So this was the 2 points I forgot. And still, I'm not leaving the stage. There's one more thing I have to say. So before I hand over to the chairs of the next session, there's one more deed I have to do. So the PolInSAR group, I mean, we have heard it now, is 20 years old. It was the first time gathering in 2003. And back then it was a small group. To have first ideas to study PolInSAR techniques, polarimetry. It was after the launch of Envisat, so the first data came in. But it was not only that, it was not only the science that really was driving this community. It was really a family that was gathering and it was growing over the time. And this group that started quite small now was growing to a family of 200 or more than 200 people who will join us in this workshop. And who is still thriving. So you were really at the forefront of a lot of scientific developments and a lot of nice science that you did. But it's still, despite the fact that it's growing so fast and it's growing so big, it still feels a bit like a family. You see the same faces as always, and Yves Louis has shown some of them who were there on the first workshop, and they are still here in the room. So it's, I think that's also a nice proof how much we are a family here. And one person that was paramount to keep this family together was Yves Louis Desnos from the very first day. And you will be surprised to hear, especially if you see him sitting here, you will be surprised to hear that this is the last PolInSAR of Yves Louis. I've heard that you retire actually immediately after this workshop. November. So there's still a bit of time. But we wanted to use this occasion not only to celebrate PolInSAR, but also to celebrate a bit you and to farewell you. And maybe I can ask. Yes. No, I want yes. I want this one here. So we wanted to give you a little present for you, and I have to explain a bit. So Yves Louis, when we go back to 2003, oh no, let's start that way. We were asking a bit before we organized this conference, we were asking a bit around the agency, and we were saying, do you know any anecdotes of Yves Louis and any nice story? The first thing everyone came back, Yves Louis is the godfather of PolInSAR. And a lot of things would not have happened without him in charge and without him pushing it. So to honor a bit Yves Louis' visionary support, his inspiration, his dedication to this community, we wanted to give you a small award. And we were thinking what we can do. So we wanted to do something that is a bit more, not only an award, but it's also a bit more lasting. So we bought a little, or we followed one of the main applications of PolInSAR, that's forestry. And we decided to buy a little forest for Yves Louis to thank you, and which should also last maybe another 20 years or maybe even longer. I have to explain a bit. This forest is a bit special. So you buy a lot of forest these days to offset your carbon footprint, but this was not the intention of this forest. So this forest will support the local community. It's in Madagascar. It's a mangrove forest there that they plant. And I think this reflects a bit on one of your big qualities that you have, which is to support people and to let them thrive and to let them grow and to support them wholeheartedly. And with this forest, we hope supporting these local communities, you will continue over the next years. But this is not only for Yves Louis, this is for the whole community. As I said, we are all a family. So for each of you, we bought one tree that will be planted, and you will receive in the next days, I think, a message that will give you access to your tree. So you can look out if Yves Louis takes good care of his forest. And I hope that I hope really in 2 years that we will come back here when biomass is launched, and Yves Louis hopefully comes back from his retirement, and we hope that we can look at this forest then with PolInSAR eyes and to see it grow. Thank you, Yves Louis. Thank you for your support. You want to make a photo? Good. Thank you.
I think I've spoken enough already this morning, but I'll take care of the forest and please, if you want really to please me, continue like you have done in the last 35 years. Continue to work on this domain and push the SAR. I think you have enough missions to work with, and continue to innovate and continue to train, of course, the young generation with the technology they have. Sometimes I'm telling no excuse. If you understand remote sensing, you have with the cloud computing capability we have, no excuse is a bit exaggerated, but at least we have a lot of tools to work really faster, better than we were capable at the time. So continue.
And now we can start. So I would like to ask the chairs of the first session, it's Yves Louis and Tui, to the floor, and we will start traditionally with an overview of all the missions that are out there and that support polarimetry and interferometry.
So, good morning, everyone. My name is Thuy Le Toan, and I'm living here in Toulouse. And my excuse for the bad weather here today. But usually we have a very good, the best weather in France, in Europe. Okay, so our session this morning is about the SAR mission. And we have 5 presentations. And then I go straight to the first presentation. It's the status of Copernicus Sentinel-1 Next Generation and ESA Earth Explorer Harmony, number 10. The Björk Roman will be the presenter. Björk, the floor is yours.
Good morning, everyone. So now we have to make the switch to from all the celebrations to the mission status. And I have the pleasure to combine all these missions in a single presentation. So please buckle up. It's going to be it's going to be fast, but I think it's going to be as well interesting. So. Let's see how this works. Okay, sorry. Yes. Okay, so a bit of, let's say, I think you've seen this already before, but just very quick, let's say, in the pinkish red, you see the current generation Sentinels, let's say, and Sentinel-1 family. Of course, we had A and B, and of course, C/B is grayed out because, unfortunately, we lost control of it, let's say, or not control, but we lost the capability of the SAR to operate end of December 21. But Sentinel-1C and D are coming, and this is something I will let you know what is the latest status of this. Then of course we have the next generation, which is now as well continuing and starting already to make sure that in the 30s we will continue, let's say, having capability to operate and to continue, let's say, the Sentinel-1 operations. And then from the high priority candidate missions, of course, we have Roselle, which has been mentioned already before. Of course, I forgot to acknowledge my co-authors, so I will do this as well right now. So it was with Malcolm Davidson, Nuno Miranda, and Ramon Torres. So for Sentinel-1 overall mission status, so we, as you all know, let's say we launched Sentinel-1A back in 2014, Sentinel-1B in 2016. As I mentioned, we had a failure, let's say, a critical failure at the end of December 21 for Sentinel-1B after 5.5 years in orbit. And Sentinel-1A is now actually the only one continuing, which of course is an issue because the constellation has been built, let's say, to operate with 2 satellites, and now we have a gap. But we hopefully soon we should be able to complement again with Sentinel-1C, and shortly after the Sentinel-1D operations. So Sentinel-1 mission in a nutshell. As already a constellation of 2 satellites with A and B, but of course now B will be soon replenished with C. What's happening here? Yes. We have roughly a 7-year lifetime and consumables for 12 years. What I think interesting is that we are targeting Sentinel-1C launch for Q4 this year, and Sentinel-1D, which is currently in storage, will soon be further, let's say, prepared for launch as well. Okay, maybe I move a bit closer. Okay, so the radiometric accuracy, I think, is important to mention. I think is 1 dB 3 sigma, which has been demonstrated, which is, I think, very stringent requirement. And we'll mainly operating in an IWS, interferometric wide swath mode, 250 kilometer swath with 5x20 meter resolution. So Sentinel-1A is operating very well since launch, and is now basically already in the extended lifetime. We are already preparing ready for a 10-year celebration next year. So fingers crossed, we're gonna make that, and hopefully by the time the constellation is also complete with Sentinel-1C in orbit. Following Sentinel-1B permanent failure, of course the Sentinel-1 mission relies entirely on 1A only. The Copernicus contributing missions, RADARSAT-2, PASS, TerraSAR-X, ICE-I, and RADARSAT Constellation mission are mitigating the gap. So thanks to increased quotas for Copernicus services. And Sentinel-1B is being disposed of. We had an issue with the power unit supplying energy to the SAR, the C-band antenna power supply. All the instrument and other platform functions are working normally, which is really pity that you have such a well-operating spacecraft, but is not able to operate its main instrument any longer. The disposal of the satellite is now ongoing, and atmospheric re-entry is then planned within 12 years. I think what is important to mention here is that even with a system satellite that's operating so well, it's got 75 years of fuel available, that it will take us, let's say, up to, let's say, 12 years, worst case, to deorbit. So this is something to take in mind. People that think it's quite easy to deorbit satellites, it's a hell of a task. So, and all of the 1B data is available on the Copernicus Data Access Platform. So the long-term continuity is done, say, through the 20s and beyond, is ensured by the almost identical Sentinel-1C and 1D units. What's interesting to note here is that there is an addition of an AIS instrument for ship detection signals. Automatic identification system it's called. So all ships have an onboard transponder that is able to send the code and the characteristic of the ship to the satellite, which is then able to see as well what ship it is on top of, let's say, the SAR signature. And of course, as well a general improvement of the SAR performance. There's a slightly different internal calibration loop, slight changes on the actual SAR architecture, which we believe is going to improve the radiometric stability. And then the first generation will provide continuity with the next generation, which should then be replenished in the first generation in the 30s. So 1C launch was supposed to take place in May 23, but followed by an in-orbit commissioning of about 4 months. In December, we had Vega C failure, as some of you may know, and as a consequence of this, the 1C launch has been postponed. We expect Arianespace to provide us in July 23 more information on the launch manifest and the actual Sentinel-1C launch slot, 1 month launch window. And it's now been proposed to be the passenger of the return to flight of the Vega C launcher, and that's aimed now for December 23. And this is okay. Next month we know more, but it should be around that time period. So, and Arianespace is also expected in July to provide us a 6-month launch window for Sentinel-1D launch. So it's going to be a launch manifest being prepared for all the missions to be launched in the next years. During in-orbit commissioning, Sentinel-1C, and I think interesting to know, is flying a 1-day tandem configuration for 4 cycles, and afterwards will be placed in its nominal, let's say, 6-day configuration, 6-day repeat with in the constellation for the remainder of the in-orbit commissioning. The duty cycle, I think, is interesting to mention. Sentinel-1 can acquire up to 30 minutes per orbit of high bit rate, so interferometric wide and extended wide swath, within an orbit rolling window of let's say 100 minutes outside of eclipse season, and in eclipse it's still able to do 25 minutes. And here you see the initial ramp up, let's say, after Sentinel-1A launch in 2014, and you saw there, let's say, that the entire ramping up, let's say, the payload data ground segment, and also, let's say, to operate the system took us, let's say, some time, but not even that long. Because see, already in 2015 we were already at 250 minutes per day of duty cycle in imaging mode. As soon as we launched Sentinel-1B, you see that almost directly, let's say, following launch, apart from doing all the commissioning tasks, we were able, let's say, to ramp it up enormously fast and keep it at that quite quickly over time. After, let's say, we lost 1B, we were able, let's say, to have a slight increase of the duty cycle. You hardly can see it here, but there's still, let's say, some minutes were added, let's say, there as well. Which means that we have actually no capacity left in Sentinel-1A, so we're operating actually at absolutely max capability right now. So for the observation scenario, the Sentinel-1A observation scenario, what's interesting to see here is that you see here two graphs, one before Sentinel-1B was launched and the one after Sentinel-1B, and you see that the over-mission capacity to perform global coverage has, of course, been compromised because, of course, we lost after we don't have, let's say, this global coverage as we would like to see it. But we are pushing really the envelope further. We gave up a little bit, let's say, of the revisit, let's say, in the northern areas, as you can see here. It's less red, let's say, there. But as you see, for the other areas, we were able, let's say, to really complement this loss a lot to make sure that we were going to maintain, let's say, the interferometric time series as much as we could. So. Now moving to the next generation. So here you see the 1B, 1A, 1B, and C and D, so the first generation, and then this is the similar plot as Yves Louis has shown. Then we expect this from 2032 to be complemented with the next generation, again, 2 satellites. The main highlights for this to ensure continuity an expansion of services, enhance the existing service and applications, and enable as well new application, and look at, let's say, observation gaps, so looking at what can we do about the resolution, revisit, and others. Performance-wise, it should be better or equal than the first generation, so we are targeting revisit even of 3 days global and half a day in Arctic and sea ice. Resolution in the order, let's say, of 25 square meters, so similar to the strip map mode that we hardly operate on Sentinel-1. Noise giving sigma not improved by at least 4 dB with respect to the first generation, and a full continuity in dual pole, where you have a very wide swath, but as well, let's say, in a mode, let's say, with quad pole capability, which is similar to the interferometric wide coverage that we currently have. And what's also interesting to mention is a dedicated mission mode to cover the North Pole region. So the famous gap on the polar gap on the North Pole, we will not have it any longer with the next generation. And the same orbit of it will use the same orbit as the first generation and Roselle in constellation of 2 satellites. So quickly, let's say in yellow you see the main improvements, or with respect to the first generation. So we have -80 to +90 degrees. So we have no gap any longer in the North Pole, as I mentioned. So we go in terms of revisit, we're able, let's say, to do even better than what we do right now with the first generation. Incidence angle range wider than what we currently have, and a swath width larger than 400 kilometer. And these are the requirements that we currently have in the phase AB1 that has just been concluded. And the duty cycle, which is for Sentinel-1, requirement was 25 minutes per orbit. As I mentioned, say, it's actually operating right now beyond, let's say, 30 minutes per orbit. For the next generation, it's 43% average, which is roughly, let's say, 43 minutes per orbit on average, which means there are going to be, let's say, some peaks up to, let's say, 53 to 55 minutes. As well, the automatic identification system payload, which is already on CND, will also be mounted on, let's say, the next generation, and also operation to potential integration of additional satellites. And over the ocean, of course, the mission will continue to support the generation of wave mode products, as we've been doing ever since we've been flying C-band SAR. Here you see a bit, let's say, with a bit of the, let's say, image enhancement that we can expect. If you look at, say, the resolution, you see here some ESAR data for the AgriSAR campaign, and on the right image you see the interferometric wide swath, let's say, equivalent, and in the middle the strip map, and that is comparable, of course, to the Sentinel-1 next generation. So you see there already an enhancement, and then on top of it, let's say, of course, we'll have even, let's say, a higher noise giving sigma naught with respect to Sentinel-1. So things will definitely improve as well with the next generation. The current, let's say, candidate concepts, that's the parallel phase AB1 has recently been concluded in April 23. One consortium was led by Airbus Germany, the other one by TAS Italy. The highlight from these activities is basically we have a constellation of 2 satellites, same as the first generation. In principle, everything was open when we started this type of system activities in AB1. We're flying the same orbit. As I mentioned, the SAR instrument is based on the planar phased array. Also, let's say, reflector-based solutions were considered, but discarded during the study. And exploiting, let's say, state-of-the-art SAR technology based on SCORE, scan on receive, and maps in azimuth. The constraints were that we had to fly with a Vega family launcher, so we're now looking at Vega E, which is not yet, let's say, known what it's going to look like exactly, but it's going to have, let's say, an increased mass capacity, and of course technology readiness. As I mentioned, instrument is based on SCORE. There's digital beamforming and elevation, and MAPS, which is digital beamforming and azimuth on ground. And similar to Sentinel-1 first generation, we have a minimum number of modes to be implemented. Sentinel-1 next generation will also support the potential harmony mission extension beyond Sentinel-1 CND. And the AIS instrument, as mentioned, will be providing continuity with CND as well. So we recently concluded, let's say, the ISRR, Intermediate System Requirement Review, for both consortia, and the ITT for the B2CD activity is expected to go out in November 23. And the kickoff should happen, let's say, first half of 24, and then we're targeting an expected launch beyond 2032. So here you see the actual Copernicus, the different Copernicus services where Sentinel-1NG will also contribute to. So you see the climate service, the marine monitoring service, land monitoring, emergency management and security services. Where in yellow, you see where actually the enhancement of Sentinel-1NG will definitely contribute to. So in terms of sea ice type, concentration and motion, which are things that we will be able to do much better with Sentinel-1NG. Sea ice type, land use change, agriculture, forestry, wet snow extent, flooded areas, and iceberg location, vessel location, and oil spill location and morphology. And this, of course, the oil spill and for the ice is, of course, because of the increased noise given sigma naught, that will definitely help us there. And last but not least, let's say, moving to a different product, moving to radiometric terrain corrected products, so going away from the classical GRD product that most this community probably would not know because they're probably not using the intensity products all the time. But we're going to move, let's say, as well to going to more, let's say, application-ready data, which has been formulated by SEALS and worked a lot on, let's say, in the SEALS context. So it's backscatter normalized using local scattering area, not incidence angle, which helps really to look at, say, multiple sensors because the incidence angle dependency is then out, and as well able, let's say, to have multiple C-band SAR satellites, not even from the same space agency, to be combined, let's say, in a nice fashion. Then moving to my last part, let's say, is on harmony, which is not in the Copernicus context, but in the Earth science context. And this similar the graph that Yves also has shown already. You see there on in our Earth science pillar, which really started with ERS and NVSAT in the old days, but where we have our Earth explorers, but also, let's say, our scout missions and our missions of opportunity. As you know, let's say we recently selected, let's say in September, Harmony as a 10th Earth Explorer mission, and it will operate together with Sentinel-1D. There's been a very extensive report written, let's say, that for which we also had a user consultation meeting in July last year, which is publicly available on the web pages if you want to hear more about this mission beyond what I'm telling you right now. So Harmony in a nutshell is it's comprised of two companion satellites, which is flying in a loose convoy with Sentinel-1D with a long track separation of around 350 kilometers. So this orbit, this specific, let's say, orbit is going to be busy, yes, because you have the Sentinel-1, you got the next generation, Roselle, and Harmony. So you got a C and L band train going there and supporting the community from 2030 onwards. We'll be flying the system together, let's say, in a cross-track interferometry mode. So they'll be launched together in the Vega C launcher. And in that mode, we're going to be able to do cross-track interferometry covering land application like glaciers, permafrost, and volcanoes. Then we have 3 years of stereo phase, where we are moving them on either side, let's say, of Sentinel-1, where we're able, let's say, to do 3D surface deformation, and as well ocean applications, surface motion, and surface winds, sea surface temperature, and cloud motion, because we're also flying a multi-view thermal infrared instrument on each of the systems. So, if we already mentioned that we were able to do a lot with Harmony, we have identified 3 primary areas where Harmony will contribute, but there will be, of course, more because it's also enhancing some of the Sentinel-1 services. So, looking at upper oceans and ocean-atmosphere interactions, land ice and sea ice, and as well tectonic strain and volcanic processes. So Harmony is able to resolve the sub-kilometer scale motion vectors and topography changes associated to dynamics Earth system processes. So starting with this, over the oceans, heat, gas, momentum exchange at the RC interface, and the inner structure of ocean atmospheric streams. And with Harmony, we're going to be able, let's say, to characterize the marine atmospheric boundary layer in a way that we've not been able to do before, but especially at the smaller scales and looking at the actual processes that are taking place and trying to capture, let's say, some parameterization that is currently not able to be captured, let's say, in the Earth system models. Then for the glaciers, let's say, look, gradual and dynamic volume changes of global mountain and polar glaciers, but as well instantaneous sea ice motions to characterize sea ice dynamics. And you see that's in light blue because it's kind of a secondary application, so not really driving the overall design. And then 3D deformation over solid earth associated to tectonic strain. So finally, let's say, we'll be able, let's say, to really get, let's say, not only the east-west displacements, but as well the north-south and the up-down. So we'll be really able to reconstruct the 3D deformation over the solid earth. And topographic change at active volcanoes worldwide, and that's of course in the XTI configuration of Harmony. So then something on polarimetry, because this I think is interesting maybe as well to this community, is that of course now we're looking, let's say, in a multi-static way where we were able to get both the monostatic and the bistatic signals. You're going to be able, let's say, to do a lot more interesting, let's say, research and trying to analyze targets from space. Of course, the reciprocity that we all know is kind of lost in this configuration. Some of the canonical scattering mechanism, like planes, diplanes, dipoles, etc., they maintain the degree of polarization, but you have a polarization rotation introduced if you're looking, let's say, at the target. So for more complex targets, you would expect depolarization or loss of even appearance of BRAC. And this rotation of the polarization basis and the method to how to do this, let's say, for this particular geometry has been well described in a paper by Lorenzo Giannini on rough surface polarimetry in companion SAR missions. So definitely would, if you're interested, please have a look at this paper because it has everything described on the polarimetry that we can expect for this type of missions, which is definitely something interesting to look at. Then the Harmony development schedule key dates. We're now preparing the B2CD package for Harmony right now, and we hope to have a full system activity in place in somewhere mid next year. And then we have to, let's say, follow a very, very tight schedule to make sure that we're launching by the end of the decade, to make sure that we have sufficient overlap with Sentinel-1D. This is my last slide. So uniqueness and harmony. So we're looking really at simultaneous, let's say, order kilometer scale, sea surface temperature, cloud top motion, directional roughness, directional Doppler. It's C-band, so it's also known as an all-weather mission. So it means we'll also be able to penetrate the extremes. And over land, let's say, we're able to do 3D repeat paths in SAR, but also able, let's say, to do dense DSM time series at the order 50-meter scale. Over, let's say, land ice and over volcanoes. That was my last slide. Thank you. Oops.
Thank you very much, Björk. It's impressive progress since we have envisaged and now towards harmony. And I can see that when I traveling around the world, Sentinel-1A and 1B are the data the most used for application. So thanks to the systematic acquisition, but now with polarimetry, and I think that it will be the best categories of data. Yeah. Okay. So if you have a question to Björk. And I suppose that the information will be on the web or on the presentation will be available.
Will be available.
Yeah,
yes.
yeah. Okay, you will have the presentation of Björk later on the presentation report. Thanks.
Okay, thank you.
Okay, the second presentation is about Roselle mission status by Clément. Please.
Hello, good morning, everybody. So you will see a few common slides, so I will be a little bit faster on this one. So I will present the radar observing system for Europe in L-band, Roselle mission. Okay, sorry. I missed anything? No, okay, good. So here you can see the family of the Copernicus expansion missions. So Copernicus is a collaboration between ESA and the European Commission. So ESA funding the development of the processor and all the A units, and the Commission funding the development of the recurrent unit and the operation of the different missions. And in these 6 missions, you can see the ROSEL mission. So L-band, L-band SAR, addressing geohazard, polarize, forest management, food security, and maritime surveillance. So you already saw this slide showing the family of the Sentinel-1 current generation, Sentinel-1 next generation, and the ROSEL as part of the Copernicus. I just put Sentinel-1B in red, as we lost it, as you know. So the timeline that you could also see here, the message to remember is that the Copernicus expansion mission provides new information not yet available, but they also provide enhanced information in combination with the current Sentinel missions. So it's not missions that are completely, let's say, isolated. They really work in collaboration with the existing mission. So the launch date of the first ROSEL unit is planned for 2029. So you see it should fly at the same time of Sentinel-1 first generation and Sentinel-1 next generation. The different topics that will be addressed by the mission are the geohazard monitoring, land use, agriculture and forestry, soil moisture, cryosphere, marine monitoring and maritime monitoring. So the different topics that are already addressed by the existing Copernicus mission, and in particular by Sentinel-1, to support the different Copernicus services that you can see on the top left. So for geohazard monitoring ground motion, it will improve the coverage and the availability of motion information, especially in vegetated and snow-covered area, thanks to the L-band and the power of penetration. It will enhance also the robustness to the phase unwrapping, also thanks to the lower frequency in fast deformation scenario due to longer wavelength. So you can see on your right a comparison between the C-band and L-band with ALOS2 data. And the requirement is a bit similar to the one of Sentinel-1, so 6 days repeat pass with 2 satellites, but the resolution of 50 meters square compared to Sentinel-1 300 meters square, you could see before. And ascending and descending acquisition for the east-west motion displacement, and with low latency for rapid mapping after the events, so similar to Sentinel-1 for this. For the biomass and land use, land cover mapping, he will have new timely information on above ground biomass and biome structure and types, thanks to the L-band that is suitable for forests with AGB up to 150 tons per hectare, which is the case of boreal and temperate forests, compared to the C-band as very small penetration. Here we really have an information on really the biomass content and weight of the European forest and a lot of forest. It will enhance the continuity on deforestation monitoring, including tropical forest. And the L-band is sensitive to changes and losses, so not only the surface will be estimated, but also the quantity of biomass lost, for example, will be able to be estimated thanks to the L-band. And it will improve the land use, land cover in combination with Sentinel-1. So the revisit is here also 6 day, high resolution and companion friendliness. So similar to the concept of harmony, to allow to have a companion for L-band, or to SAOCOM companion satellite concept a few years ago. You can see also on the bottom right some comparison between Sentinel-1 and ALOS2 that show the sensitivity of the L-band to the biomass and to the forest estimate, which is not the case at C-band. For the soil moisture, we'll have a high-resolution soil moisture tracking in broad range of crops and vegetated lands. It will be complementing the Sentinel-1 surface moisture product, mainly suitable for bare soils. Here we'll have a little more penetration, so on soil moisture up to 5 centimeters of depth, which is compared to 1 centimeter, which is really the surface that we have at C-band with Sentinel-1. Here again, 6 days of a revisit, 3 days over Europe, high resolution, low noise level, and integration with other scatterometer and L-band radiometer. For the sea ice monitoring, here we'll have daily high resolution information on hazardous sea ice and iceberg, which is important for navigation and weather climate services. We'll have an enhanced mapping of the sea ice type and concentration, thanks again to the penetration of the L-band compared to the C-band, which will be more sensitive to large ice structures, and will improve the mapping of sea ice drift by flying in close formation with Sentinel-1. So we'll have more recurrent data. Here we'll have also revisit, which is quite important. 1 day in the Arctic, 3 days in Europe, 6 days global, low noise level, high resolution wide swath compared to Sentinel-1, and simultaneous acquisition with Sentinel-1 for sea ice mapping. Land ice and seasonal snow. Here we'll have enhanced high velocity retrieval, ice sheet and glacier, thanks to, again, the penetration of the L-band. New seasonal snow bordering capability through the retrieval snow water equivalent. And the requirement 6-day repeat pass for highest velocity, low noise level, high resolution, wide swath, and a close acquisition with Sentinel-1 in order to better retrieve the wet snow. And you can see comparison on the right with TerraSAR-X and PulSAR. For the maritime and marine monitoring, we'll have an added value of vessel detection. Thanks to the L-band that will be less sensitive to the surface of the water, it will improve also the detection of the iceberg, thanks to the sensitivity of the L-band I was saying before of the large ice structure. And it will add some value to extreme events like tropical cyclone, because the C-band is saturating quite fast up to a certain wind speed, let's say. The waves are getting a little bit too high and C-band is saturating. The L-band will allow to increase the range of speed, wind speed, to be able to be retrieved thanks to this frequency. So will be a wave mode as a requirement on the Roselle mission. Revisit similar to the one I was showing before. Low latency for European water, less than 10 minutes, and the other requirement that we saw before. The possibility to have a long track interferometry capabilities. So in brief, it's a constellation of 2 satellites, A and B unit, the options under study, but let's see, it's quite unlikely. It will have a service continuity with Sentinel-1, so first generation and next generation. The coverage will be similar to Sentinel-1, global land, excluding Antarctica. The Arctic will be also covered, revisit time very similar. Repeat cycle of 6 days over the global land with 2 satellites, so very similar. It's L-band SAR, dual pole and quad pole mode. So it's not completely designed how they will be used. Most certainly, mainly of the data will be acquired dual pole, so similar to Sentinel-1. Wave mode capability, resolution of 50 meters square for the Roselle interferometric wide swath mode, which is a bit similar to the one of Sentinel-1. You can see noise equivalent sigma naught is quite low. We have the ambiguity ratio also minus 23 dB. And the swath width, which is under definition, should be bigger than the one of Sentinel-1, which is 250 kilometer in IW. So it will be acquired synergic acquisition with Sentinel-1 with co-located swath, which we find important to be able to explore the data properly. And it will support convoy configurations. So there will be a low latency, 10 minutes over Europe coastal waters and 200 minutes globally. So very similar to the requirement you could see for Sentinel-1 next generation. And now we are at the beginning of the phase C, science plan activity starting this year, end of the year, and the launch is still expected in around 2028, with potential delays that we all have for different missions. And the Roselle B unit is expected to be delivered in 2030. So here you have the different, more detailed parameters with the current configuration. So these are the current, let's say, working numbers. They will be to be confirmed. They will be consolidated in the next years. So you see the 2 different modes, the Roselle interferometric wide swath and the quad pole interferometric wide swath and the wave mode. So the swath is slightly bigger than the one of Sentinel-1, but we have 50 meters square for the interferometric wide swath. So this is sizing requirement. With operation, we plan 35 minutes of dual pole SAR mode or 20 minutes quad pole SAR mode in terms of volume, and the remaining time for wave mode. So this is the baseline today to be confirmed. It will augment the Sentinel-1 with the synergic acquisition plan and the mission design. So it will be co-location with Sentinel-1 as I was saying before, same orbit configuration of Sentinel-1, phasing of the orbital plane just to follow the same ground track of Sentinel-1. Full swath overlap with the Sentinel-1 IW, which is quite interesting, and it will extensive global coverage and consistent long-time archive. Here again, like all these emissions, we have a free, full and open data policy, and we are moving toward a system of system concepts with enhanced information and product, as Bjorn was showing before, different type of mission, different frequency, but all working together. The main characteristic of the instrument, here you have a little bit more detail. It's a planar antenna, you can see with 5 panels. So 5 azimuth and 12 elevation subarrays, so 60 phase centers to go into detail. All the individual small sub-antenna, 150 watts peak, which is quite high. If we put the total radiated peak power, it's 9 kilowatts, so it's quite a lot. There will be digital beamforming to do a little bit this Roselle IW, which is kind of ScanSAR mode, and the possibility to have also the scan on receive, so with the beam following the ground to increase a little bit noise equivalent sigma naught of the data. In terms of volume, it's with the current approach, we have a 12.5 terabyte per day of level 0. So it's quite a challenge. To give you order of magnitude, it's 8 times Sentinel-1. For the level 1, we're around 6 times the level 1 of Sentinel-1. And compared to, for example, NISAR, which is already a very challenging mission, level 0, it's 4 times the level 0. So it's a lot of data. Because related to the fact that we'll have the information of the 5 antenna, part of the antenna that will be downloaded to the ground. So there will be additional science to be made during the processing to properly retrieve, let's say, the information from these 5 part of the antennas. The ionosphere at L-band will be challenging. It's our first L-band mission in Europe. It's not the first one in the world. So hopefully we'll capitalize on the expertise of previous missions. The ionosphere will impact all the aspects of the SAR signal. So the location accuracy due to the absolute range and azimuth shifts. There will be distortion of the impulse response function and the degradation of the resolution, the polarization, polarimetric channel mixing due to the Faraday rotation, and the disturbance of INSAR phases. To cope with that, we have this split band transmission capability with the split band techniques that will be able to be applied with 8 megahertz, yeah, if I remember well, bandwidth that can be separated from the rest of the spectrum. So in general, the science activity and the collaboration, so the activities are ongoing to contribute to mature the SRL of the Roselle product. Also a campaign aimed at investigating the potential of the L-band. The campaign in the past, we're here in the context of the Roselle mission with TomoSense, LuxCat, LCI, SNOLAB, NG. The project funded by ESA and the different sources initiatives, CCI, DUE, STAC. A newly funded activity as part of the Roselle Science Plan starting from this year, end of the year. And joint research activity carried out with other space agency, with JAXA, NASA, CONAE, and are also participating as observer in the Roselle Max. So we are involving all the expertise in the domain. ESA and JAXA put in place satellite-based environmental monitoring science and application. It's a project with 20 sites, around 16 topics with ALOS 2 and Sentinel-1, providing data coverage over all these different sites to work on the future synergies between Sentinel-1 and Roselle. And ESA trying to support the activity that make use of collaboration data set to secure the scientific output. And we have ad hoc acquisition in the context of extreme weather, for example, hurricane and disasters, I was showing before. And dedicated campaign, including RASAR-2, TerraSAR-X, Cosmos, CAMED data. And finally, joint conference session at LPS, Fringe, to present and collect results of the cooperation. For the science plan, the plans cover the mission development phase and the commissioning phase up to the end of the commissioning. And the expected kickoff of the first project is around second part of 2023. You will have, for example, the FSR2 airborne campaign that will not only support the P-band SAR for the biomass mission, but also the L-band SAR. So be able to support ROSEL and potentially NISAR, for example, and a lot of work on the ionosphere mitigation algorithm, which is quite a challenge for us at the L-band. So this slide was already presented before because it's a direction that we want to take. We follow SAR missions, so ERS, AMVSAT, Sentinel-1, Biomass, ROSEL. It's to move to this concept of analysis-ready data, so to help the community to better exploit SAR data. And we feel with the new approach, new data access that we are putting in place, that the current GRD product could be potentially replaced in the future by a more modern product with a better file format and already processing a little bit further the module up to have the RTC, the radiometric terrain correction, applied to the product. So the equivalent of the GRD will still be provided through a better access to the SLC, having the possibility to access the module of the SLC, for example. But this product, let's say pre-cooked product, will be also available for all the analysis that take topographic correction already taken into account. So, and ROSEL will be fully aligned with the Sentinel-1 approach, which is still to be confirmed. So the conclusion is that with the industry and together with the European Commission, we are preparing the expansion of the Copernicus SAR missions, SAR mission today at the S, and the ROSEL mission at L-band as a Copernicus mission to address the information gaps that we have today and to provide new information not yet available through the current Sentinel missions. So it brings new and enhanced capability, high resolution, low noise equivalent sigma naught, wide swath, in addition to this L-band new type of acquisitions. And Sentinel-1, ROSEL, Sentinel-1 next generation will address as a system, let's say the world, not as isolation. ROSEL will have the same orbit, swath, and acquisition geometry of Sentinel-1. There will be synergies between the C and L band, and synergies with other mission, especially with the biomass mission, with the P-band activities. So there is still work required to prepare to the uptake of the ROSEL by the user community, ionosphere correction, interferometric error budget, C and L band synergies. So still a lot to do, but it's a very interesting and bright future full of SAR missions. Thank you for your attention.
I don't know. I think we have time for questions or comments. Yes, Irena.
Yeah, thanks a lot. I mean, it has a really big potential to have ROSEL, and also the combination with the new generation Sentinel. But still, I see some difficulties how to solve, right? It's not so easy. And this was actually the topic about dual pole versus quad pole. And you mentioned already, it is not clear which polarization mode we will really get and how long. The one solution could be to work in phases, right? That you say, okay, I have 1 year quad pole and I have 2nd year dual pole. But then you don't have the continuation, which is probably also problematic. Another option could be to look for regions of interest, to say, okay, all the forest areas could be quad pole, and all the ice areas could be quad pole, and all the rest dual pole. You know, the question is, I'm not sure how ESA would like to solve this, so that's a little bit my question, actually. And then the second thing is how to bring this together with Sentinel and G, which is also quad pole, and should be on the same region, right? Have the same polarization combination could be probably best for the scientists. This would be really good.
So I imagine this question is valid for both missions, actually. So ROSEL is coming a little bit before, but how to say, it's a compromise to be made, and the constraints are a little bit the same, which is the data volume, which is quite high. So it's true that for a lot of parameters, as you could see, we are following the approach of Sentinel-1, but there's no quad pole on Sentinel-1, so it's something that comes a little bit on top, and it's not really clear where to make it. So we have a current approach, but this could change. And your, let's say, recommendations, even during this workshop, would be quite interesting and quite important. Maybe Bjorn, you want to?
Yes, to fill in
I
on
think
this,
they start to be tabled, the recommendation. Yes, go ahead, Bjorn.
Yes,
short.
it
Works, yes, okay. To fill in on this question for me, then I think of course, the Copernicus missions are going to be, of course, driven by the services. So it's not something that the agency will define on itself or the commission, but it will go really through the process, let's say, with the services. And as you said as well, Irena, of course, the continuity, let's say, of the data, let's say, of the stacks will have to be guaranteed. So it will be likely, let's say, that if services really are benefiting clearly, let's say, from the quad pole capability, and of course, then have to give up a little bit, let's say, on the actual coverage, then of course, this can be decided, let's say, on a region-by-region basis and driven, let's say, by actual application that is really done, let's say, through the Copernicus services. So this will be the process that will be followed, but of course, this is a process that is now being done, and of course, through the mission advisory groups of both missions, this is something that will be followed in that way. But it's clear, let's say, both missions, they do have, let's say, this quad pole capability, and it says it's capability, which of course Sentinel-1, the first generation, did not have this capability itself, but now we have these missions that have it, and of course it will be used, but of course we are, it will have to be done, let's say, in a systematic way over specific areas. I agree there. Yeah.
It's not possible to acquire quad pole the same way we are doing with Sentinel-1 today, with dual pole, and I imagine that NISAR, they have the same issues. Most of the world will be dual pole, and so here, if there are topics, particular topics for forestry, there could be indeed some areas that could be flown at quad pole. But as Björn was saying, we have to see with different application Copernicus services to be sure that it fulfills all the different applications and that in the whole budget, everything fits together.
Okay.
Fits together well.
Yeah, but this is a topic for discussion. I think we should really discuss this properly. Parce que qui peut le plus peut le moins, as we say in French. So you could imagine having a quad pole mode completely matching the old generation of Sentinel, except instead of having one or two pole, you have the four. Now I have a question, I say concern, but also it's a concern on the story of GRD, because with the technology we have, I think we should preserve absolutely the SLC. We could even think about processing the data on the fly. In the future, I think it will be no problem. So I don't see why we should go to GRD to get them in analysis-ready mode. You could imagine having, with the technology we have, we could have an API, getting the data, the SLC, putting them in a data cube, and getting them AI-ready. By this means, this is what we are doing today.
But it's a little bit the idea. To put them AI ready, you need to process them in a certain way.
But you don't need to put them in GRD. That's obvious.
It wouldn't be GRD, it would be following the CEO's
yeah, but whatever the standard here, you need to preserve the phase and have the phase information in the cube. That's a bit my recommendation. But it's idea for your further discussion. I just bring my own... we are using operationally data cube today, and so we have a bit of knowledge on that. And if we were to use the phase, it's much better to have the SLC.
And if you have recommendation on this topic, they're also
very I should welcome. Not table the recommendation. I'm just feeding the community myself. I will tell you directly. Yes, go ahead, one more.
Thanks for the excellent ROSEL mission as additional to Sentinel-1 and Sentinel-1 next generation. As I know, currently Sentinel-1 coverage for Antarctic, and the coastline of Antarctic is not very dense, and apart probably about 1 kilometer away from the coastline. I would wonder about the combined reverse date and also coverage with the ROSEL and the Sentinel-1 next generation for the Antarctic and also the sea ice monitoring. Give the more interest people for the Antarctic at the moment.
Here, yeah, the approach would be to follow the approach of Sentinel-1, so more the Arctic. It seems that the Antarctica will be covered by NISAR and other missions. But I don't know, maybe Björn, you...
Yeah, I
for
think
Sentinel-1, next generation will be following the same approach as Sentinel-1. You will cover completely the Arctic, but the Antarctica will not be covered fully.
Yeah, but of course, as you've seen for Sentinel-1 for the next generation, we go up in terms of, let's say, our operational duty cycle goes up enormously. So from, let's say, 25 minutes requirement to now 43 minutes average, which means that, of course, the overall global coverage with the full constellation will definitely increase, which means that also that there is going to be room, if, of course, driven, let's say, by the operational needs to also cover these areas, let's say, in more detail and have a more faster resolution, a faster revisit of those areas as well.
I think we should move to the next speaker, where we can continue this discussion in the roundtable session.
Yes, I think that the future mission, yeah. Okay, okay, so it's a passionate discussion that we can move to another table later in the week. And now the next presentation is from very far away. It's about SAOCOM mission by Laura Fulla. She's from CONAE, Argentina, so it's by remote presentation. Recorded, yeah.
SAOCOM mission objectives are to satisfy user needs and the space information sectors that belong to the National Space Plan that we review periodically. We supported agriculture, mainly thinking about the generation of soil moisture maps, hydrology for floods, and emergencies in general. And also, we have to operationally integrate the SIAGE system, that is the Italian and Argentinian satellite system for emergency management, composed by the SAOCOM constellation and the Cosmos Skyme constellation. Here we have the mission general features. I will not go over all the table, but mainly some things are repetition cycle, which is about 16 days for one satellite and 8 days for the constellation. The spatial resolution, which varies from 10 to 100 meters, depending on the mode. The incidence angle, which varies also between 18 and 50 degrees, depending on the mode. Decimal of values varying from -35 to 5 degrees, and the rest of the features that you can find in these both links, that you have these features and more. And you can find there all the features that correspond to SAOCOM, divided for each mode and all what you need to know. We have the emission acquisition strategy divided in 3 parts. One is the baseline mission dedicated to fixed acquisitions. For one side, on one side, soil moisture dedicated to Pampas region, and the other, the SAR calibration for the rainforest. We acquire from the rainforest over specific point targets that we have in Argentina and over doldrums. The other part of the mission is dedicated to the foreground, that here we can have the variable acquisitions, and there are what the users require. And the background mission that we think about having a useful database for users. And in Argentina, we are thinking about emergencies, maritime control, biomass, and Los Andes, mainly dedicated to tectonic plates and glacier movements. And over Latin America and the rest of the world, we thought about biomass and polar zone monitoring. Here is an example of the maps that we published prior to its cycle, and each map has the reference of the modes that we plan, the colors and the shapes of the modes are indicated in the reference, and we consider the mode according to the features of the region that we acquired. All these maps you can find in this link, and these maps are expressed in English. Nowadays, you have three possibilities of to access SAOCOM data. One is to navigate the catalog and for if the region of interest is the area of exclusivity of ASI, you can access ASI link. And outside the area of exclusivity, you can access CONAE's link. SAOCOM catalog can be navigated freely, and there you identify the existing data through this link, and you can see the thumbnails that they really are very small. But if you register, you can access to the quick looks, and these quick looks have another functionalities that are, for example, a zoom functionality from which you can identify very well the features of the image of interest. If you register, you can have an agreement and you can present a project, and in both cases, signing a license to use, you can access to acquisitions, to ask for acquisitions. Another way is what we name the one-click possibility, that it is from the non-commercial and commercial users. If the region of interest is Argentina, they can access directly, clicking in the web, the license to use for both Argentinians and foreigners. And through this possibility, the user can access to any archive data, level 1 and level 2. They can download, they can ask for reprocessing, and they can access also to interferometric products. And instead, if the region of interest is outside Argentina, for non-commercial users, they can have they can take the normal way to access the data. Let's say contact CONAE, always speaking about the area of outside the area of exclusivity of ASI. They can contact CONAE and presenting a project or through an agreement, they can access to acquisition request. And for commercial users, in the case of Argentinians and residents, they can have free access to the data, and for foreigners, they can celebrate some commercial agreement with our company bank. In both cases, for commercial users, have to contact our company. But the difference from this point is that in these cases, they can access of acquisition request. The link to get the possibility of one click is here, and the other possibility is through an initiative that we are having with ISA, that we have an announcement of opportunity, which is named Promotion of Utilization and Mission Applications and Science, named PUMAS, and this announcement of opportunity is an initiative under EarthNet third-party mission program for science and applications development only, and the call will close on July 31st, and we are thinking about opening another one by September of this year. The data available is from ISA, any data of Earth observation, the Copernicus data, and from SAOCOM, we ask for some quota that have to be less than 40 images outside the area of exclusivity of ASI. But anyway, if there is the need of more images, we can analyze case by case. These are the links that you contact this announcement of opportunity for CONAE and ISA. In relation to the product flow using polarimetry, only going to agriculture case, from the quad-pole image, we generate the Pauli decomposition, and we use this image for units identification. Let's say bodies of water, urban regions, crop regions, big units. And also from the quad pulsar image, using the Clopotier decomposition and the Wishart classification, improved by the diffusion reaction algorithm, we generate a land cover classification map that is very, this map gets into the agriculture processor, and this processor generates a soil moisture map. From the soil moisture map, we generate another products that are very useful, other products that are very useful for agriculture and hydrology. And also from this agriculture processor, we generate maps of vegetation water content and phenological stage. We also, from the quad-pole image, we generate a radar vegetation index that is very useful for the health status identification of the crop and other products for several applications. Here we have an example of the Pauli decomposition of some region of Córdoba in Argentina. Each color, of course, is related with the different scattering processes. And as I mentioned, from the quad-pole image, we generate the land cover classification map. Here we can see only the identification of soybean, maize, bare soil, and pasture. And the no class is related to urban regions and water bodies. And from this map, as I mentioned, we generate a soil moisture map, which spatial resolution varies from 150 up to 800 meters, depending on the mode, let's say, or a strip map of TopSAR and TopSAR narrow. And this is the map corresponding to the same region of Córdoba in Argentina. And each map is with the corresponding scale, where the blue regions are with water and the red regions are in the driest condition. All these maps you can find in SAUCON catalog. The soil moisture maps are validated. We have a very dense in situ data, in situ network, and this network is working from 2012. From then we have hourly data. We have nowadays more than 70 stations and more than 110 sensors measuring soil moisture, in some cases up to 2 meters in depth, temperature, and conductivity. Here we have an example of the radar vegetation index, and you have the link here where you can download only registered into CONAE. This index we obtain using the Kieman-Mansell equation, and we find that this index correlates very well with the normal differential vegetation index, and the scale of this map is here, where black regions are bare soil and the different green tonalities are related with the health of the crop and the phenological state. We also analyze radar vegetation index behavior in relation with the interferometric coherence, and as it is expected, we prove that higher values of radar vegetation index variation between the interferometric dates correspond to lower coherence values. We also prove polarimetric decomposition for leak detection in drinking water networks. Using the Pauli decomposition, we obtain all the polarimetric indices, the phase correlations and modules, and considering the multitemporal evolution, all of the data using artificial intelligent models. We can find, for example, these maps, and doing this allows us to determine a water leak probability map in which the hotspots indicate the highest probability of water leaks in the urban region. Also, we apply this type of techniques for lithium spatial and concentration estimation. There is a region of Argentina, main Tres Quebradas salar, is a salar, that from the Pauli decomposition we obtain the different indices and also the correlation indices and phase indices, and using also the soil moisture map in multitemporal analysis. We mix everything, and using artificial intelligent techniques, we can estimate where we can find lithium. And thank you very much. Commission objectives are to satisfy user needs and the space information that belong to the national.
Yes, I think we have some difficulty to answer the question live, as you can imagine.
Yeah.
But we can, I think, if there is any burning question, the only important message for the community, given the upcoming the PUMA CAO is open, so you should make use of it. When you see the network they have for in situ validation in Argentina, there are a lot of potential to do things with this, so this CAO. And if you want more information, I think we are going likely to keep it open for longer, of course, than was planned.
Okay.
And this with Francesco, I think we'll keep you updated because he's managing that.
Yeah, it was planned to obtain 40 images from the call, and the call is supposed to close at the 31st of July.
Yes, but we will keep it open. That's something Francesco will tell you in sessions how we are going to handle. The idea is having this data for European scientists in preparation for Roselle, and that's the idea we had.
Because so far you did not get send many. Oh, sorry. We will keep it until the end of October, and in the beginning we were a bit disappointed because we didn't get actually many requests from you. So also one of the purpose of this conference is to encourage you to really apply for this data because they are very worthwhile. As you know, we don't have those many quad-pol data from ESA via TPM, so it's really a good opportunity for you to get this data easily and straightforward.
So next speaker is Marco Laval. Is about the NISAR mission status. Marco.
All right. Good morning, everyone. And Thank you, Louis, for the introduction. So we'll be talking about NISAR. NISAR stands for NASA ISRO Synthetic Aperture Radar. It's a mission in partnership between NASA and ISRO, the Indian Space Agency. It's a science mission. As such, it starts from science questions. Some of them, you see them listed on the screen. They cover the broad range of scientific disciplines from cryosphere, ecosystems, solid earth, and coastal processes. And so this is important to keep in mind because everything you'll see in the next few slides, especially in terms of system requirements, flows down from these science questions. So the system salient characteristics are sort of listed on the screen. It's an L-band and S-band mission. L-band covers globally all land masses and ice. S-band is regional coverage over India and Antarctica and Greenland. Uses the sweep-SAR technique. It's something that you have seen in previous presentation called here as a score or scan and receive, and you see actually an animation on the side where we synthesize a broad beam to cover the 240 kilometer swath in transmit and a narrow beam in reception to get high resolution. Resolution ranges between 3 and 10 meters depending on mode. It's a 12-day repeat mission with a very good pointing control and orbit controls to do interferometry, of course, between all the repeat passes. Duty cycle for L-band is fairly high, I'd say. It's 50% with 70% peaks along the orbit. And it's a left-only mission, unlike all the other SAR missions. As long as I know, ESA usually tends to do a right-looking mission. Sentinel-1 is right-looking, and Roselle will be right-looking, which is actually an opportunity, so we can cover regions that the left-only looking mission doesn't cover, such as the Arctic. In terms of partnerships between NASA and ISRO, we have a separated set of goals in terms of implementation, mostly. So NASA provides the L-band SAR and the reflector. It's a 12-meter reflector that you see on the screen, and as well as some engineering payload. And of course, all the data processing and the operation of the L-band SAR, whereas ISRO is focused on S-band SAR as well as on the launching of the mission. As you can see here, we will be using the GSLV launch vehicle. The mission will be launched from India. In terms of ConOps, so concept of operations, you see an illustration of how the operation will be conducted after NISAR has been launched. The launch date, by the way, is late January next year, so it's in less than 7-8 months, perhaps. So you see the the operations are sort of split between L-band and S-band. L-band data will be downlinked to the US, the NEN network, and ingested in the AWS, Amazon Web Service, cloud, where will be processed within JPL and then shipped to or transferred to ASF DAC. That's where all users like you will access the data. The S-band radar data will be downlinked to India and processed on some India facilities, although there's a discussion whether we could sort of combine the processing or at least process some S-band data on the NASA side as well. The hardware status is fairly on time, actually. The satellite, the S-band is built again in India. L-band has been built at JPL and has been shipped in March to India. So it's currently in Bangalore in southern India, where it's been assembled and tested further before launch. So you see the last stage of this development is at the bottom of the screen, where you see the satellite mainframe. That sort of cube, it's been completed and it's now being integrated with the full satellite, the full instrument, that the vertical beam, let's see if this works, yeah, the vertical beam, the vertical structure here, where you see also the reflector, this vertical cylinder. And so the launch date, like I said, it's January 2024, and so we're mostly on schedule. There might be a few weeks of delay depending on issues that we may find during A&T. This is an actual picture of the hardware. This is in a TVAC chamber before it was shipped to a JPL, before it was shipped to India. And you can see clearly the L-band SAR feed antenna here with the boom that will hold the reflector. And again, this is the folded reflector antenna that will be used to illuminate the Earth's surface. Moving to the NISAR modes, so we have over 100 modes for NISAR, but of course only a small set of them will be used for imaging. The main mode, if you want to just remember one, just remember the background land. That's the main mode that will acquire data over all land. It's a dual pole HH and HV polarimetric mode with a 20 megahertz bandwidth. So resolution, it's about 6 to 7 meters in range and azimuth. The other modes are also, some of them are single pole, some of them are quad pole, and some of them are actually compact pole in the S-band radar. And I have a better picture here on how these modes are distributed globally. As you see again, the background land is essentially all over the globe. Quad pole will be acquired over India, as well as on some selected area in North America. You see the purple, the dark purple region here. Over North America, we have 40 megahertz, so it's a factor of 2 in terms of resolution along range compared to the background land. So another important mode here is the light blue here, where you have 80 megahertz single pole for LSAR, whereas also compact pole for SAR. So it's a fairly diverse observation plan, but I guess going back to one of the questions earlier, I think from Irena, how do we do polarimetry? We selected the second option, where we have some selected areas with quad polarimetry, which will be acquired consistently over the lifetime of the mission. So level 0, level 1, and level 2 products will be distributed openly and freely, of course. We call level 2 in NASA everything that is geocoded. And one of the products that is sort of new in the community is geocoded SLC. You see here GSLC. G stands for geocoded, R stands for radar coordinates. We'll be distributing RSLCs generated using back projection algorithm, as well as the GSLC, so which are level 2 products, although they are SLC, so they can be cross-multiplied and an interferogram can be generated fairly easily. And of course, for the purist of interferometry, one can always go back to the RSLC and do all the stack processing and all the fancy algorithms to generate a proper interferogram network from which you can do analysis. The other product, well, so in terms of going back to the resolution of the various products, we have like I said, 20 megahertz background land, but also 40 megahertz and 80 megahertz, 80 megahertz modes. You can see here a sort of comparison of the resolutions along azimuth and range for the various modes. So we're ranging between 2 or 3 meters up to 7 meters for the RSLC mode. An important innovation, I think, for NISAR will be this 5 megahertz bandwidth that you see illustrated on the side. And this was mentioned in the Clement slides on Roselle. So we will be using the split spectrum technique to correct for ionospheric distortions and retrieve, estimate the dispersive component of the interferometric phase, and so get a better interferogram as you know, by basically forming the interferogram in the 2 different bands, and then doing some processing to get that the difference and the dispersive component of the interferometric phase. You can also see that both 40 megahertz and 20 megahertz modes have this 5 megahertz subband allocated, which will again give a better estimation of the ionospheric distortion. This is how a NISAR product will look like in the standard mode. We have a frequency A, 20 megahertz, and a frequency B, that 5 megahertz that I just mentioned. This is in fact a NISAR simulated product that you can access and download if you like to look at it. It's in an HDF5 container where we are essentially simulating the NISAR return from UAVSAR data by making the resolution coarser and increasing the noise level. So these data you can download today. They're available for free on the UAVSAR website. If you Google uavsar.jpl.nasa.gov and search for NISAR data, you can download several of these data sets. And there are also different modes with different characteristics. The other level 2 product that we are generating, and this goes back a little bit to what Clément was saying about the ARD, is the GCOV matrix, the GCOV product, which is essentially the geocoded covariance matrix. There is a discussion, currently it's in the plan, we will be distributing only the diagonal elements, so the HH and HV backscatter, but there is a discussion whether we will be also distributing the off-diagonal elements, so with the complex valued elements of that matrix. So I guess as an innovation here, we are distributing the RTC gamma naught backscatter. So it's not only the NRB, the way that Clément described, but also in the both polarizations and with actually new algorithms using the local area. I think it was mentioned earlier, we call it projection area, JPL, but that's essentially, I think it's very important for those who are mapping biomass or disturbance. You will be receiving a stack of GCOV products, all already RTC'd, radiometric terrain corrected, and co-registered, so it will be very easy to do any science with it. There are no level 3 products currently, except for soil moisture that you see listed on the screen, being generated by the NISAR project by default, although there will be most likely parallel efforts. In fact, one of them is already ongoing. It's called Opera, to generate global level 3 products. And by level 3, I mean things like biomass maps or vegetation disturbance, inundation, crop area. These products that you see here listed here, VP stands for validation products. And so that's what NISAR by default as a project requirement will do, just generate these products on selected calibration sites. And leave the generation of global maps and harmonized products to other efforts, which are, again, already ongoing, such as Opera. The data volume is fairly large. We are downlinking 4.5 terabytes of data per day and generating 70 terabytes per day of level 0 to level 2 science products. These will be processed, like I said, at JPL and then transferred to the ESF DAC with a latency of about 1 day. This is a fairly conservative estimate. In an urgent response, we have 4 hours for the level 1 product requirement, and so we think we're meeting this requirement fairly comfortably. Everything is open and free. There's, like I mentioned earlier, already sample products, NISAR data from level 0 to level 2, and perhaps even level 3. Once those will be generated, will be completely open and free as soon as they are available. This is per NASA policy. There's really nothing, absolutely nothing being held by the process, by the projects. Even the calibration, the data, anything will be absolutely open. Some of them are, everything that we have currently is already online. Even the level 1 processor that we're developing, level 1 and level 2 processors, are already available. If you Google ICE3 framework, you'll find a GitHub page for that tool that will be used for processing level 1 and level 2 data. We also have level 3 calibration and validation notebooks already available. So these will essentially be the algorithms to generate higher level products such as biomass or disturbance. So if you're curious to see what is NISAR doing to map disturbance or biomass, so those algorithms are already available there. And so you can download and use them. There is an activity ongoing now to have to develop platforms. We call them collaborative platforms, so users can go in there, like all of us can go in the same platforms and collaborate and process data. One of them is the map. There is 2 more being developed at NASA called the NISAR On Demand and Open Science Lab. One is at JPL, the other one is at the ASF DAC. But those are essentially platforms, web-based platforms that you can based on Jupyter notebooks typically, that you can use. If you register, you can use, and there's some quotas also for using free cloud computing resources. This is the timeline after launch. After January 2024, we are going into a 3 months of commissioning, and after that, we have a 5 months of CalVal that overlaps with the science operations, and that's where the science data will be available to everybody. So it's in less than a year. We will be what we say, showered by data. So there's going to be a lot of data and an opportunity to process and do some science. What you see at the bottom of the screen is a deployment sequence that takes about 9 days, 9 to 11 days to deploy the reflector. And I have a video here. I think, hopefully this will play, that shows how what will happen essentially in about 7 to 8 months at the end of January. This is an animation showing the launch from the ISRO facilities in India. Satish Dhawan, I think, is the name of the launch site. This is the GSLV launch vehicle provided by ISRO. And you will see shortly how the spacecraft, here's the NICER spacecraft with the instrument, that sort of cylindrical shape, and the bus sitting on top, at the bottom. There will be a deployment of the solar panel. Some maneuvering, probably, to check out the solar panels. This is fairly standard. Followed by the deployment of the 9-meter boom. That's the black structure that holds the reflector. There's also some audio, but somehow it doesn't come through. And that's how the deployment sequence proceeds. So the boom raises. You can see the L-band feed and the S-band feed, they're next to each other. In fact, there's a small angle in the illumination of the two radars using the same reflector, and you'll see in a second. Here's the reflector. It's a 12-meter mesh reflector. It's now solid. So see, it's the same eye, transparent. That's my last slide. I'll leave you with the sort of announcement of this NASA ISRO SAR Science Users Handbook. So if you have questions about NICER, you can Google this NICER handbook, and you'll probably find the answer in this 250 pages book. Thank you.
Thank you, Marco. Any question for Marco? Yes, sure.
Comment. I think it's worth reiterating what you said about the level 3 products, in that the existing algorithms for an ISAR are pretty rudimentary, and equally the validation program is very simple. So they've really put all the science effort on the part of the applications people. It really is just a data producer. You really have to do it all yourself, not just look up their algorithms, because it won't work, I don't think, in some cases.
That's correct. Yes, I think it's a fair statement. We will learn probably a lot in the first 5 months, and so these algorithms will be refined for sure. There's currently there's a calibration plan that I didn't mention. It's written down and available online, both for data and algorithms. And so yes, but there's opportunities for improvement for sure.
Okay, Bjorn. En passant, welcome back in the SAR provider mode.
Yes.
This is a good milestone for us,
okay,
for the community.
Thanks, Marco. It was a very nice presentation. Last time Paul presented this, he was saying on the NICER, he thought it was indeed clear that also the S-band data would be also openly available. Is it something you can confirm now already, or is it?
That is, yeah, it's a good question. I cannot speak to that yet. So there was some discussion a month ago about the distribution and the processing of S-band data. My feeling, and again, it's personal feeling based on the discussion, is that they will be open, just like all the L-band data. But it is something that ISRO will probably have the last word on that.
Yeah, understood, yes. And one last point is, of course, biomass is also left-looking, so that is another satellite.
Okay, good.
You can add to your list.
I knew I wasn't right. I had the feeling that something could be left-looking. So, right.
Okay. Any additional question and comment? So just for me to understand, the L-band data are fully accessible. Huh?
Absolutely,
okay.
Yes. Everything is free and open from the moment they will be generated. Yes.
And I think I like the approach of having everything available on GitHub and in an open science. I know it's pushed a lot by your director,
yes.
Karen. She's very keen on that.
Yes,
and we will follow, of course, a lot of that as well.
Yeah, including the level 1 processor, because I know ESA doesn't. I don't know if there is any.
Not yet, no.
Not yet. We're not there yet.
Not yet, but it's a good guidance on how to do things properly. Okay, so let's.
Okay, let's move to the last but not least one, the Tandem X mission by Irina Hansen.
Okay, yes, thanks a lot also for listening now to this talk. Yeah, I have to say I'm not a new mission, or we are not a new mission. Tandem X is already since 2010 operationally. So which means really, so we are going back to the perspective to really the real world and how SAR missions are working today. And you, as said, from 2000, so the launch of 2010 to today, we have a really an operational system which is working amazingly well, I would say, in terms of performances. We have still enough fuel, let me say, hydrazine for TerraSAR-X and also Tandem X. We have enough battery capacity still available. And the instrument performance, which is really amazingly, is still in the sigma of 0.2 dB per square meter, which is an excellent system over the whole years that we are operating it. Tandem X stands for TerraSAR-X add-on for digital elevation measurements, and the digital elevation measurements is actually the main keyword here, which means Tandem X is meant to have produced or still producing 3D digital elevation models. The model that we have developed which we have been collected between 2011 and 2015, as you can see it here. And we have a posting oil coverage, so posting of 12 by 12 meter, and we have covered globally all land surfaces. And just to say, this has been completed in 2016. And the basis, this is today the basis actually for the Copernicus DEM that is available on an edited version on the Copernicus server, which is quite great if you can consider to have first, we have generated, and these data are available for everybody, we have generated non-edited radar digital elevation models, and this has been then used to do an edition, and like this, now it's available over the Copernicus date. In addition to the 12 meter, we have also the 30 meter spatial resolution and the 90 meter spatial resolution DEMs, and you see here the DEM product itself has kind of 12 meter and the relative vertical accuracy of less than 2 meter for low slopey area, and more, we were saying from the specification, higher slopey area for 4 meters. We have recognized that most of the areas which we have covered on a very slightly slope, we are reaching even 1 meter accuracy, and so vertical, relative vertical accuracies. In addition, we have, probably just to mention, so the 12 meter DEMs can be retrieved by a proposal. So that's a restriction that we have nationally. We are not able to distribute the whole globe just over a server, as NASA and ESA is available to do it. So we have national restrictions. And here, therefore, we do it over proposals. However, what we could achieve nationally was to provide a 90-meter dam, which is open and freely available and can be just downloaded over a server. So this is already available since 2018. We have also a product since 2019, which is called the Global Tandem X Forest Non-Forest Map, with a spatial resolution of 50 meters. So that's something that is also available and can be just downloaded. This is just for the DEM product itself, and probably just a little bit to have a look which kind of percentage in terms of downloads do we have or requests on this data. So the DEM is used as a basis for a lot of different applications, so that's probably you're aware of. We have a lot of applications here from geology, actually, followed by hydrology. Other application is a mix of calibration and new method applications where people are developing new methods, and we have quite a lot from glaciologists. Followed by the countries, you see Germany is, because it's a national mission, Germany has a high percentage of requests in terms of digital elevation models, and then followed by the United States, United Kingdom. We always put DLR in as an addition there, just to make a separation. Germany doesn't mean it's really is DLR, right? So we have two different things. So we have, in addition, also German users, which are not a DLR, but you can see also DLR users are using quite a lot these digital elevation models. Where are these tiles, the 12-meter tiles mainly, are really used or requested from? You see we have quite a strong distribution over areas as, for example, Greenland, very northern areas. We have on the coast, if you see North America, so these are the mountain areas which are very well also received. If you go also down to the Andes, also here we have huge areas which are requested. For sure, Europe is a big area where we also have a lot of data, and then you see in the Asian part also quite strongly, but also South Africa, Mid-Africa, so medium areas, we have also quite a lot of requests, and also Antarctica, which we have covered completely, and also this data can be used. So what we have in addition is not only the DAM, but we are also producing the co-registered single-law complex data. Co-registered means, as it has been just also explained, that we have the two acquisitions from the tandem, so which is TerraSAR X and Tandem X, and we have co-registered data already that can be delivered. And this co-registered data also here, we have different application areas where people are interested into it. Again, followed by just looking for glaciology, any kind of a huge amount of different applications that we just gathered together that are not belonging to the other categories. Then we have vegetation interferometry. We have, in general, development of new techniques, but also in geology again, and other kind of techniques that we have here. Again, for the co-SSCs, you see DLR is very prominent here because it takes a little bit of knowledge in order to process these data. It's clearly, so therefore, mainly users which know how to deal with radar data are using these data. However, again, we have Germany, followed by China, United States, France, United Kingdom, and so on. So these are the main countries which are also requesting this kind of data. What we have new since 2022 is actually a joint proposal, announcement of opportunity. It's not only Tandem X and TerraSAR X where we can deliver data, but we have now, in addition, PASS, which is a Spanish, the Spanish satellite from a Spanish agency, Inter. And we are in principle, what we try to do, we are following up in a constellation now. The mode that we have normally with Tandem X and TerraSAR X is 11-day repeat. But with PASS, what we can now achieve, because it's also an X-band satellite, as said, identical to the other ones, is in principle that we could have a 4 to 7 days repeat cycle, which is very interesting for very dynamic processes, to collect data over very dynamic processes, as for example, melting processes or any kind of agricultural growing pairs. That's also something, or probably what would be also very interesting is any kind of hazards in order to see the evolution. So that's the data that can be also ordered. For these, what you need to do is to order these data twice, unfortunately. So once you need to do a request to pass and another request to turn TandemX or TerraX. Let us go a little bit what we have done since 2016, because I said on 2016 we have delivered globally the digital elevation model. So what happened since then? So we are just collecting further data. So one main aim was the derivation or the bringing together digital elevation model, which is one part, but the other thing is also we are always collecting for smaller areas, smaller parts, data for scientific purposes, where people can use the co-registered single complex data and the coherences to estimate or do other kind of science purposes. And in addition, we have done now a kind of phase, which we called the TandemX change map, where we collected data now from 2017 to 19 over certain areas that you can see here, either once or twice, depending now on the coherence levels that we have. So that's our experiences from the real TandemX that we have collected between 2010 and 2016 or 15. And out of these, we were now defining which are the areas where we have the highest change and the best constellation also in terms of the constellation of the baseline that we can retrieve on this area. So you see until 19, we have collected again Greenland, glaciers in general, mountains, forests, deserts, and the rest of the world. And again, the main motivation here is to generate a new digital elevation model and to do the improvement, and the second one is to get some change layers. I'd like to show some change layers that we have already collected, and we had a short view on it already. So we have the TandemX change dam, and this is an area of North New Zealand, as you can see. The colors representing the positive and the negative changes. Positive means something was growing potentially, and negative means something was cut down or is missing. And if you zoom now into this region that you can see here, then you see on the right, you see the Google Earth map of this area, where we have agricultural field, but also forested areas. And if you look now to the left image with the red and bluish colors, again, red is a minus, so something has been cut down over forested areas between the global dam from 2016 collected to the 2018. And if you look now to the second one, and you see the progress within the years in 2019, we see even that we have the reddish color specifically on the left side. On the top, it's even more reddish. This is the forest area, and you see how strongly really changes are occurring within this area where we have strong cut downs of forest. The other parts, which are more structures, more in the middle or on the right side, we see these are agriculture areas where we see the changes due to the crop changes and the crop growth that you can see here in the area. So what is probably interesting is really that for each of the new maps that we have a specific time indicated time, so you know exactly when the data has been acquired and how the dam has been generated. We have done also we had some views over the southern Patagonia ice field, as you can see here. Again, the red changes is really the melting over these glaciers, and the bluish one is an increase due to accumulation that can happen over the time. And a last kind of example here is an open pit mining in Australia. Again, the one is popping up like positive and the other one negative, because all the material for the mining that has been shuffled up has been deposited on a higher part. Therefore, you see these two differences as a line over this region of interest. On the right side, it's very small. You can't see it, but it's kind of, this is a zoom in of the left from the right side, which is in the middle of the image. Okay, how we proceed now? So we generated already, or we started to generate these change maps that we have. And since then, how we are calling actually our phases here from 2020, so we are further collecting data. We call it the 4D phase. The 4D because it's not only the 3D as a digital elevation model, but also the time now included. So therefore we have the 4D. And our next plans are really to cover certain areas of interest where we know that scientists are interested into it. So we are providing to make a kind of regional interest on these change acquisitions. And this is, you see the regions now from 2020 to 22, which are mainly the areas of the permafrost areas, the Greenland ice sheets, but also you see the forest areas, which are also changing. So also forest here is a big issue. So we have done this now over the years, or we will do this over the years. So today we have 2023. So that's a plan, what we are intending to do for the next year. So everything that is green and yellow will be done every second year. So we will have these acquisitions. And then we have areas which are here blank still, but now it will be filled. These blank areas are regions which we will only cover once. Whereas one part, I need to say that we will do a refinement, which is in India part. So just recognize it. So India is a part that we will do a revisit also like for the other one, so every 2 years. And also a little bit some parts of Asia in addition. So this will be refined, but all the rest is kind of set. So why or how we are doing this? So the problem is, as said, we are already now 13 years old with a mission. We do not know how long it will still exist, so that's always, can be always a technical failure. You have seen from the hydrazine and from the battery, it's still can be still operated and can be operated until 2029. So that's the main goal that we still have until 2029 to operate then. But what we need to do in order to save the batteries and to save the fuel, we have now developed a certain drift formation, how we install our baselines. So therefore what you see here, the baseline installation is kind of a drifting thing so that we do not need to control it anymore so strongly. And save fuel with it, so we do not have then this control, but we're doing a drifting shift. And after this drift, we are again having a maintenance so that we can, in principle, shift it back. So that's the main idea. And for the batteries, what we do here, you see it on the right side. It's a little bit small. Now what we do, we take very, very small data takes. Data takes are around 40 seconds in the moment, and after data take, in order to have some coolings of the system, we have a gap, and then we collect again data. So therefore, it takes also longer to do a global DEM acquisitions nowadays for us. But however, like these, we save the energy and the capacity of this mission. Here you see again, just for the different years, you see the area of interest that we have. And again, for the forest, we have every second year a complete forest cover, which is important in order to see what are the changes. And the rest, you see also we have some regions of change, which are the orange one that you have seen also before. Okay, here I'm skipping this one because that's the one that I just explained. So what we had before, just probably like this, we had from until 2020, and this you see here, we needed always to do a maintenance, so we were correcting the baselines by really commanding the satellites. So like these, we had a lot of energy and fuel consumption. We had a little bit a gap, and this you see as an outage between January 2020 to, let me say, mid of 2020. Therefore, the baselines have a little bit of problems here. But then since this year, we are continuing with the new phase that we have with the drifting formation where we save a little bit on hydrazine. Okay, what are the new products that are coming out? As already mentioned, 2 of them. So the one is we are developing, or we have already started to process the Tandem X-DEM 2020. So from the Tandem X-DEM that we had now published and which is available on the Copernicus site, we are now generating a new Tandem X-DEM, a global DEM, which will be completed next year, so mid next year. And we have, as said, layers already, change layers of the different years. So the changes between the main dam of 2010 to 2015 to now 2017 to 2020. What is different here, it is not the 12-meter change layers, but these are the 30 meters change layers, because this has been done on a 30-meter edited product, so therefore the 30-meter. And these will be complete, or is closely completed until September this year, under 2023. And we hope that these data can be made open available, like also the 90 meters, so without any proposal submissions. So you just go to the server and you download them immediately. So this is something that we started now to approve, or to look for the approval by the Federal Office of Economy Affairs and Export Control, because these are the limiting factors, as I was saying before, why we can't really give it free like ESA and NASA, because we have these national limitation. However, if this doesn't work until September, so we will still wait, this can take a little bit longer probably, this process, we will make these data anyway open, available over announcement of opportunity, which means you can submit a proposal, and then the data can be available and free for download then later on. Yeah, the TandemX science server, please have a look there. We have always some news there which can be interesting for you, but this is also the main portal where you submit your proposal. As said, we have the joint path TandemX and TerraSAR-X proposal announcement of opportunity open already. And what is now new and we are discussing is with the RADARSAT constellation mission. So we will have a RADARSAT constellation announcement opportunity open with all the 4 satellites. So if you're interested in RCM C-band data plus the X-band data, then you're welcome to submit also in a proposal of opportunity, or a proposal here for us. And will come soon means potentially it will come until October. So in October we potentially will open it. October is also a big event that we have. So we have normally every 2 to 3. Now with COVID, we had a little bit longer pause between the science team meeting. So we will have a new science team meeting in October 18 to 20. So you're welcome to join and to submit some proposals if you like. The deadline actually is already gone from yesterday, but for the audience here, you just contact me if you like to submit still something, and we can still, let me say, make it open for you, or you can, it is still open, so you just submit it, and we will just let it a little bit unofficially open for longer until probably beginning of next week. So until next week, you can still submit a proposal here. Yeah, that's already my last slide that I had. Just as said, some pictures, images here of some highlights. One thing that I've found very amazing is potentially also what TandemX can do if you have very high spatial resolution is to observe solar power plants, for example, that you can see here. That's amazing where you have the mirrors. You can see the mirrors quite well. You see the separate mirrors here. So that's also a new topic, which is now with climate change very important, is energy. A big topic is energy and energy consumption, and also how we can, in principle, redefine and see how much solar system do we have and how much energy is available in the different countries. With this, I would like to close my official presentation, but I do not like to close my last words now, so I just have some final words. I would like also, from my perspective, I would like to thank also very much Yves Louis. I was thinking that TandemX is already so long working very operational and fantastically with very, very good results. And my feeling is it's like a tandem. So our tandem, so Yves Louis and me, we have worked also since years together. We have done together the IGER symposium in 2012. And also we had a hurdle with a book publication, and we managed to do it. So I'm really, really proud to work with it in a tandem with Yves Louis over all these many, many years, and having this great support from him. And like these, I have something for him too. You can guess what is inside. Yes, it's a tandem, right? Perfect. So it's a tandem, and yes, so that's a little bit from our institute.
Very nice.
Thanks a lot. Yeah, just.
Yes, properly.
Yeah. Yeah.
It's a 3D model, as
Yes.
it should be.
Yeah, it's a 3D model, right, with a tangent.
Thank you.
Okay, you're welcome.
Thank you, Irina. So I suppose that if we have question to Irina, she's here during the week also. No? Yeah. Yeah. If there's a question from the audience. Yeah.
Hi, my name is Ji from MDA. So I have a question about the accuracy of the height over the forest area. So we know the mature forest, the biomass, measurement is different from young forest. Like some mature forest may be 30 meter high, and then the young forest may be 10 meter. So my question is, 12 meter resolution and 30 meter resolution, what's the accuracy for the height, like over the forest area? Thank you.
Yeah. It's clear we are generating a radar dam, and this is what we say. So the digital elevation model is a radar dam, and it's clear that we penetrate, right? We penetrate into the forest. Everybody knows it is X-band with 3 centimeter wavelengths. It's clearly depending on the forest type, as you said, and the structure and the age of the forest. You have different penetration capabilities. So there's not one value that you can state, right, how much it's penetrating. We can just say how much experiences we have, right? So for tropical forests, we know we're not penetrating so strong because we have denser forest, denser leaf canopies, right, on top. So can be 1-2 meters somehow. For very sparse forests, for example, we know in the boreal forest we penetrate much, much deeper. Even sometimes we see the ground. So that's really what we can say, yeah.
So the DM value provided is the top of the canopy or the surface of the soil?
No, it's kind of in between, right? So over forested or any kind of dense vegetated areas, you're somewhere in between. So you're not really on the top and you're not completely on the bottom, as you said, depending on the forest type.
Okay.
That's how the radar dam works. So over strongly vegetated areas, it's clear that you need to subtract this information. But for all the other areas, we have, as said, flat areas where we had a look on it, we were around 1 meter.
Thank you.
Okay.
Clément?
Okay. Yeah.
No, thank you very much. It's amazing results. My question is that, okay, nothing lasts forever. We see Ivry is retiring. And what's the future of TerraSAR and TANEMX? Is there a follow-on mission plan?
Yeah, in the moment, there's still, so we had, we had already since years some investigation to do a high-resolution wide source X-band system, so an HRWS system. This one, unfortunately, has been not signed up by the ministry from the science point of view and from the industry point of view. This is something that we have wished to generate. But as we had then suddenly the crisis now with the war in Ukraine, so there are a lot of things changed, we have to say. So we have really now the problem that the monies are not anymore floating to the satellites or to the science in this case in the moment in Germany, but much more to other sources. So therefore this has been stopped. It was already everything planned and done, but the last signature was missing. However, now the new investigation is ongoing, so we have again, we have been asked from the ministry in Germany to make an investigation what kind of satellites we can use or reuse, right? And what is really needed. So in principle, we're starting again somehow, not really completely from the beginning, but start again to rediscuss what is possible in order to downsize the satellite that we have already submitted as a proposal. This satellite has been really a technology high level with very new components inside, but with this also very expensive. And the question was now if you can downsize in order to have a cheaper version. That's a little bit the process in the moment. So we will see how does it works. Yeah.
Okay, so you remember, Irina, that in years ago, we thought that to take X band for the top of the forest, dense forest, and P band for the bottom. And to subtract those, you can have the forest height. Yeah, it was maybe 30 years ago.
That's true, yeah.
Okay,
yeah. But I think we learned a lot, right, now over these years, and that's interesting.
Yeah.
So still we think, so therefore I was pointing it out, we are working or operating until 2029, and we tried really to do every second year forest mapping, which should be important for the biomass mission, right? So we like still to combine measurements from Tandemix with biomass.
Okay.
So that's so this is something for the science community. This is really what we still like to provide.
Okay, 29 is far from now, but I hope that biomass will be still there.
Yeah, I hope it's in there, right?
Okay, so
So I think
thank you,
we
Irina. Yeah.
thank you, Irina, for the nice words for tandem. So it will still be operating during the week. This is the good news about the tandem. So we will resume at 2:30. Is it okay, Francesco?
No, it's 10 past 2. No, 2:30.
2:30.
It's okay then.
2:30. Magda instructed me. So then you have 1 hour for lunch.
Yeah. So before you go away, we need the presenters of the first session to give us the presentation, because none of you has given the presentation yet for the first session. We need it a bit in advance. And the other thing, don't be shy to use the Padlet that Klaus mentioned. You can do it in an anonymous way, so nobody will know who gave the negative comments, so don't be shy.
Just in the regie over there, something from you. Thank you. Thank you.
You're welcome.
Sabrina for the loading of the presentation.
Yeah.
Per le presentazioni.
quale il motivo? Perché io non c'è, io cambio solo il numero, devo controllare. No, no, è lui qui. Claudio, cambia il numero. È il primo.
Quindi è come risulta il cartaceo.
Certo, perché uno ha cancellato giustamente. Do you need to upload?
Yeah.
Okay.
Can I use any USB sticks?
Yes, of course. Adesso il secondo me la sta portando.
Sente molto basso, il fonico deve alzare il volume. Il fonico deve alzare 5 giga pure io. Tu quanti? 3. Io 5. 3 qualcosa. Strano però, tu stai a meno di 20. Controlla l'audio pure della tua registrazione. Io l'ho controllato adesso. Funziona bene? Io non ho sentito qualche pezzo spot qua e là, però. Io questo non posso andare avanti, guarda. Ce l'hai quel sì? Sì, lo so, lo apro. Non te lo apre? Sì, me lo apre, però il fatto che il volume vuole sentire un altro programma di... No, non vedo diverso da qua. Va in distorsione. Come lo tocchi va in distorsione. No, la registrazione, quando quello che ti manda lui te lo regoli da lì prima finché non ti... No, faccio così adesso perché è troppo basso. Pure io ce n'ho qualcuno che ha parlato più vicino, si sente più alto, alcuni hanno parlato un po' più lontano dell'altro. Vabbè, chiuso. Perfetto. Poi vediamo. Vai. Se va bene. Facciamo così. Vai. Questo è pronto anche... Oh, grazie. Ho fatto anche la... Vedi che ho fatto io le cartelle. Vedi? Come le parti, le facciamo uguali. Dei uno, dei due, dei tre, dei quattro, dei... Io l'ho chiamata qua la data, però tu guardate così, poi abbiamo la cartella del... però Tolosa video però,
Poi ti dirò, domani c'è...
Ti lascio la giacca qua?
Sì, sì, domani c'è Michael Ferrier che parla, che è un campione di Esther, che c'ha una presentazione con un video. Gli ho detto di venire assolutamente prima perché bisogna testare il video, perché è un video pesante.
il video è dentro la
presentazione
e lo devo lanciare io?
Non lo so ragazzi.
Se è pesante...
Gli ho detto a Klaus che deve venire un po' prima perché bisogna fare test.
Sì, sì, assolutamente, perché una volta si è bloccato il video perché è troppo pesante. Allora, indizio, che indizio li metto? Secondo me va bene questo. Guarda che c'è almeno 1080, perché non ho visto qualcuno erano 720. 1080 è 1080 c'è il sicuro. 1080 per 30 fps. Una cosa incorporata. Va bene per quello che ci devi fare, una cosa tipo la telecamera, una webcam sì, è per tirare la camera, capito? Allora, proceda all'acquisto. Kim Jun-soo? Yeah.
Kim, easier.
l'altro puoi mettere, l'acquisto lo fai tu, però magari puoi mettere sul citofono, metti una nota, mi pare su Amazon, no? Quando lo consegno metti... Nota per consegna per Basile Giannini, Jacopo. Però metti suonare a, perché sennò magari non cercano, cioè, dobbiamo far capire al corriere che c'è sta il cognome tuo. Lo dobbiamo notare su sia su Amazon.
Ascolta, mancano 2 presentazioni, questi sono andati a mangiare, quindi appena...
Basta che prima dell'inizio, perché sennò poi diventa un macello.
No, no, lo so.
Perché...
Io dico,
No, no, mica, cioè, non è colpa tua.
no, no.
È che prima per esempio c'avevo la pennetta bloccata, non la potevo staccare perché stavo presentando col PC. Quindi ho dovuto aspettare.
Ho capito. No, ho capito benissimo, lo so. Il problema è che nessuno segue le istruzioni, nessuno ci si fila, nessuno legge quello, cioè,
Vabbè,
l'avevo
come
detto,
classico, no?
cioè non mi frega un cazzo a nessuno, cioè, e poi giustamente mi dispiace questa bloccata la presentazione dei prima, ma non penso che...
Non è sempre bloccare.
No, che non è la giusta. A me se mi possono i
quello vedo qualcuno che lo vedi direttamente da te.
Esatto.
I was just coming, I need a bit of water in my face. So, do you presentation now?
No, now.
No, come on, I'm free. I'm
No.
free. A lot of issues.
Which session? The start, okay. So,
Presentation number 1.
I mean, there was so much changes in the program.
Okay. If I change it, I will come again to you.
Okay. Thank you, Costas.
I thank you. Stressed? No.
No. Why?
No, no.
No, it's under control. The fact that we had some problems with the ship of the technical equipment, which was blocked for a strike, and we were panicking because when you don't have the technical stuff, it's the 50% of the work for us.
And for you, it's the first time outside.
That's
already...
For PolInSAR, yes. For me, because all my PolInSAR were in Esrin, and in Toulouse, but it's okay, we managed in the end.
Very good. No, it's great.
It's also because
Thanks
in 20...
to you.
Grazie, Costas. And to you, because you...
No, I've done nothing. I'm just
you
blah,
are
blah, 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 you know.
No, you are always present, so this is the importance. The community is the presence.
Yeah.
No.
Okay, you make the work and you make the blah, blah, you know.
Grazie, Costas.
No.
Allora, Sabri,
sì.
Allora, Marcusenda vuole chiudere pure a blu, ritirare i 5 metri.
Io
non la voglio chiudere
sono d'accordo,
personalmente.
ma Cusenda non ci frega un cazzo
Esatto.
perché non è l'organizzatore.
Esatto, e poi qualcuno dice che è freddo dentro questa sala, io non lo percepisco alla reception.
Io sono Francesco, che non è che mi ha detto non trovi freddo, io ho detto no perché io purtroppo ho i valori, perché io non sono da prendere come metodo di paragone, perché io per me io sto benissimo, Dì che l'hai abbassato.
Sabrina, sorry.
Are you the one?
Sabrina,
For the
for the presentation.
Hello.
Can you hear me? Yes. So welcome back. We can start the session now, which is about SAR missions, calibration and validation, chaired by Professor Rao and myself.
Okay. In this session, we have 4 presentations, and 3 are calibration related, 1 is mission related. Actually, this session name is SAR missions and calibration. Calibration is more, missions are less. I think my name is Y.S. Rao, Indian Institute of Technology, Bombay, and I have been attending PolInSAR for 20 years. And you know, Kait Rane, Shane Cloud, Martin and Boerner, big people. And very happy to, actually, I am replacement Scott Ansley, Jet Propulsion Laboratory, USA. He could not come, and just a replacement. Anyhow, I'm happy. And Saipal, of course, Klaus Saipal forced me to sit to represent ISRO. Just I want to say good news that ISRO S-band data is also free, and NISR, L-band also free, both are free, just for your information. And now, without any delay, I invite first presenter, Sean Kogan, very famous for his well-known book, Understanding SAR Images. First time I'm saying, I see his book every time, but first time I'm saying. Yes, University of Sheffield, and estimating SAR polarimetric system errors in the presence of Faraday rotation using a transponder. Yes, floor is yours.
Okay, thank you. Tui just said to me before I came here that this lunchtime that people don't need to come to this talk because they won't understand it anyway. Now I couldn't decide whether this was a comment on me or a comment on you, so we shall see. Okay. The PARC, I mean, you can't use PARC instead of transponder. It's has a key role in biomass calibration. The transponder site, it's a single transponder. It will be down in New Norcia in New South Wales in Australia. We couldn't have it in Europe because of the restrictions due to space object tracking radar, so it's down there. Its role in the calibration, there are 3 main ones. One is to characterize the antenna pattern. The second is radiometric calibration, and the third is polarimetric calibration. Now I'm going to talk about the third one of these. Now, I need to show some equations, but I try and make sure you know what they mean. And that up there is, if you like, the basic standard system of equation for a polarimetric radar. And basically, you read it as you've got a signal which you transmit. Sorry. Okay. If you read from the right, you distort your signal on transmission from the satellite. It passes through the ionosphere and it gets Faraday rotation. It scatters from the ground. It gets Faraday rotated again on the way out, and then it gets distorted on the receive part. And the part at the front is the radiometric calibration, so I'm going to ignore that. And you've also got noise in there as well, and the noise can include clutter. So that's the basic equation, and you can write it much more compactly as what you measure is a mixture of receive and transmit distortion, Faraday rotation. Now, with a PARC, you can simulate that S thing. You can generate an S matrix to have any shape you want. And if you do that, then if you count them, you'll have what you know about the S matrix, and you'll have 1 real unknown, which is the Faraday rotation, and 6 complex unknowns. That's the 2 crosstalk terms on the left and right, and the 2 channel imbalance terms. That's the Fs. And the Fs I'm going to think of as 1 plus epsilon, because they're nearly 1. Okay. So in that equation as written, you've got 13 unknowns, and you've only got 4 complex measurements on the left, so you've got 13 unknowns and only 8 measurements, 8 real measurements. So you can't solve it. But if you just simulate some more targets simultaneously with the PARC, you can generate all sorts of things. If you generate 4 independent scatterers like those, then you've added 8 new measurements every time you simulate a new object. You've still got the same number of unknowns. So now you've got 13 real unknowns and 32 measurements. So you've got lots and lots of ways of solving that system using analytic methods. And for example, there's a paper by Chen et al. In 2011 that does that. However, it's not quite that simple because the park is not error-free. So instead of having an S matrix, you have an S that's perturbed. And the model for that perturbation is written on the right there, on the bottom rather. And this adds 6 more complex unknowns. So now you've got 25 real unknowns. 12 of them are complex and 1 of them is real. And you've got 32 measurements. So you're still okay. You still solve that. But you can't do it analytically. It's just a mess. So you can do it with numerical methods, and that's fine. You get on with that. But then there's what we've left out of that is the fact there's a noise term, noise and clutter term. And that's an extra set of unknowns, and there's 16 complex numbers in there. So suddenly you're in a situation where you've got much fewer measurements than you have unknowns. So what happens when you add clutter and noise to your measurements? And which performs better, the numerical approach or the analytic approach? And we've approached this through simulation. I need to take one slight detour, which is we used the Chen solution, but Mark, my co-author, noticed an purely empirical improvement, which was that in the Chen solution, you get 2 estimates of the Faraday rotation. And he averaged them and used that as his estimate of Faraday rotation. Now, that is anything but obvious to do because that average solution does not solve the system without noise. But nonetheless, it does appear to give better performance. I'm going to show you the results from the simulations now, which contains quite important things, because this isn't some game. This is the biomass calibration procedure I'm talking about. This is what do we need to do to get the numbers out. Okay, so on the left-hand side, you may not be able to read some of the bottom axis, so let me just tell you what's in there. On the left-hand side is the mean error in delta. That's the crosstalk terms. And on the right-hand side is the mean error in epsilon, which is the channel imbalance error. As you read from left to right, you're reading from a signal to clutter noise ratio of 50 to 80 dB. Okay? And of the colored columns, the blue one is the Chen algorithm, the red is the average algorithm, and the orange is the numerical method. And this has some very strong messages. First of all, you'll notice that the red one, the average solution, is way better than the Chen solution, certainly for delta. It's a bit better for the epsilon. And it's actually better than the optimization approach until you get down to 80 dB signal to noise. And that's for delta. And on the right-hand side, for the epsilons, you see that it actually does better than the optimization, even at 80, a signal to noise ratio of 80 dB. So there's a very clear statement here that this analytic approach is really competitive with the optimization approach, which is not at all obvious when you set the problem up. The other thing that is really striking, it struck us immediately, is that if you look at the variation, the scatter, which is indicated by the error bars, this analytic solution, the red one, is almost completely unaffected by noise. It doesn't matter what the noise is. You get more or less very, very little scatter. We had no idea why it was behaving like this, so we tried to understand it. Oh, the other thing I should say is the numerical approach doesn't always converge. It's numerical, so you start it somewhere in a bad place and it doesn't converge. And so what this is indicating for 4 levels of signal to noise, it's only for for 20 simulations of the system errors. It's only for the highest signal to noise that you get convergence for all of them. And if we simulated another 20, it may well be that one of those would fail. So there is a problem with convergence for the optimization method. Okay, so we tried to, I tried to make some sense of this noise tolerance of the analytic solution, the average one. Now, what I'm looking at is that horrendous equation at the top, which on the face of it, you cannot get nearer. But if you're prepared to sit in a dark room for a month and just do a first-order solution, it tells you some very interesting and important things. So what I did the first-order analysis, and what I'm going to show you are the conclusions. I'm not going to show you any of the workings because they are horrendous. The first thing to say is that if you estimate Faraday rotation, the channel imbalance error, in the imaginary part of the crosstalk terms, they're all unbiased. That's very important. And I can write down explicit values for their variances. Okay, I've made some small assumptions here, but they're not important for this talk. In that equation, I've got terms for cos of sine 2 omega and sine of sine 2 omega. The T on it in the subscript indicates that's a transponder term. It's the error in transponder. And I've also assumed there's a correlation coefficient between delta 2 and delta 4. That's two of the crosstalk terms. I've done that because that's what Airbus told us is likely to be. So I can show they're unbiased, and I know the variances, and I know which are equal and which are different. I can then do the real terms. Now, the real terms are actually, it's much harder than you think to do the real ones, even to formulate the problem correctly. But what you find is the real part of two of them are unbiased, and for two of them, they are biased. Now, that matters. You're going to get the wrong answer for those real parts. And that is actually built into those results I showed earlier. But I can also calculate the variance. So you get very strong predictions from this first-order analysis. Now, the question is, are they right? So what we did is a full analysis using the full simulation. So now there are no approximations in what I'm going to show you, but the full simulations. This is for the imaginary parts of all the deltas, delta 1, delta 2, delta 3, delta 4. And the prediction was they would all be the same, they'd all have the same variances. That's the histogram, which I could never get from doing first-order analysis. And you'll see that that prediction is completely supported. Now, this is for the deltas. There's a delta 1 and delta 3 should be unbiased. And for delta 2 and delta 4, they should be biased, and that bias depends on the correlation coefficient. And as the correlation coefficient gets nearer to 1 and it's real, then the bias should go away. On the left-hand side, the correlation coefficient is 0.9. On the right-hand side, the correlation coefficient is 0.5. And the blue curve corresponds to delta 2 and delta 4. And the red curve green, corresponds to delta 1 and delta 3, which is correctly unbiased. And on the other one, it's correctly biased. And as you'll see, the delta 1 and delta 3 have the same variances, and delta 2 and 4 have the same variances, exactly as that first order predicted. So we've got a really powerful way of analyzing that system. The other really important thing you can do with this, let me just back up 1 minute, is that from those equations, you can tell which terms matter in terms of the variance, or the error variance. And it turns out for all of them, the noise term is insignificant. So in this first set of pictures I showed you, the reason why the average solution was unaffected by noise is because it's unaffected by noise. It's just not the dominant term in the error part. Yeah, it comes from the transponder terms, and one of them comes from the original system. Okay, so with that, my key conclusions are the following. And as I said, this is not a game. This matters, because it helps ESA to make the right decision on how to deal with the part when they use it. First of all, the performance of the analytic method is, to solve the Park system, is competitive, or better than numerical optimization. The numerical methods may not converge. The first order analysis indicates biases in the estimates of two of the crosstalk terms. And the last point is that you can correct the bias if you know the correlation coefficient, so you can correct that error. but the analysis of having done so still needs to be carried out. And that's it, except I want to say one other thing is that my time's limited, but there would be quite a bit more to say here about what DLR did on the same problem. And there was another point, but I forgot what it was now. Okay, but there is more to say about this, which but that'd be for another talk and for another time. Okay, thank you very much.
We have 7 minutes
Really?
time. Yes, we can open for questions.
Okay, so if there's no immediate questions, I will say what I remembered what the extra point was, is that in this solution scheme, you need to estimate the Faraday rotation. That's the first thing you do. Now, DLR correctly pointed out that you can actually do this estimation of the Faraday rotation in a completely independent way. You can use the properties of distributed targets around the transponder and then provide a separate estimate of the Faraday rotation with a known variance, because we know pretty well what the error properties of a Faraday rotation are, a Faraday rotation estimation are. So that scheme can also be implemented in here. I've not shown any results for that, but we have actually done the calculations for that particular way of doing things. And I suspect that for the biomass mission, we will actually use the Faraday rotation method to get that estimate rather than the park directly. Though we can check whether they're given the same answer. I think he was right, nobody understood it.
Just 1 minute. See, Anthony Freeman, Jet Propulsion Laboratory, suggested different method. I think you can see that paper on hybrid polarimetry with Faraday calibration with Faraday correction. Anthony Freeman.
Okay, I know Tony. I've worked with him a long time.
Yes, yes. And how to see INSAR phase deviations, distractions, INSAR phase. Is it possible to PARC give something about INSAR phase deviations? Interferometry.
Well, the INSAR, you'd have to deal with these system errors in the. Well, INSAR's to do with the propagation phase, propagation elements. This sort of calibration is to do with the intrinsic system errors. Now, there is issues with if the crosstalk, and actually probably Kostas can tell you better than me, if the crosstalk were large, then you're going to get problems of losing coherence, I guess, between channels, I think. So this is relevant for that, for the INSAR, but it's not the immediate problem here. And INSAR isn't, I think, going to help you with the issue here, which is how the part would be used. So I think there's definitely this issue. There are definitely points where you've got to consider in INSAR which come from the system calibration. But that's not the particular, that's not even, it doesn't affect, I think, what I've said here. I think.
Any impulse response deviation?
Well, okay, no, that's more subtle. I've not at all considered impulse response deviation, but that could very much be relevant, because that would cause phase perturbation. Whether you'd be able to measure them, I'm not sure.
Still we have time?
Oh, no questions.
Yes.
Stefano, I'm delighted.
You say that the first thing to do is to get Faraday rotation, right? But you do get Faraday rotation and with errors on the other parameters. So I get that you can get Faraday rotation because you assume that all the other errors are small. Is that it?
Excellent point. And the key thing about the methods developed by DLR is you get an unbiased estimate of Faraday rotation in the presence of system errors. It's a very nice piece of work that did that. I'm not even sure I would imagine, I don't know whether Costas has published it, but it's, you know what it's like. But that's the scheme you'd use. So you would get an unbiased estimate of Faraday rotation, but with a standard deviation. You can just feed that into the solution scheme, and then you can go through from there. So, and it's easy. I mean, there's no problem in doing it. You can put it straight into first order analysis. What it would do in this analysis, it would actually remove the. I had a term to do with correlation of two crosstalk terms. That vanishes. They don't appear anymore. So you should get unbiased estimates for all parameters then. So there's lots more to say, but not today.
Thanks.
Okay. So we can move to next one. Yes, we can move to next one. Thank you. Yes.
So the next presentation is by Dr. Jun Soo Kim from DLR. It's about polarimetric requirements on spaceborne SAR for the observation of mid-latitude ionospheric activity.
Yeah.
The floor is yours.
Yeah. Thank you very much for introduction. The topic of this presentation is about the polarimetric parameter accuracy requirements for the spaceborne SAR for the observation of mid-latitude ionospheric activities. This work is done by me and Kostas Papathanasiou in DLR Microwave Radar Institute, and also Hiroaki Sato in Institute of Solar Terrestrial Physics in another DLR institute. Yeah, the ionospheric activities at high and low latitudes are characterized very typical, their own characteristics. At high latitude, the charged particle from the solar and cosmic origins near the Earth are guided by the geomagnetism. So they can enter only through the auroral oval latitude, and this precipitated charged particle changes the electron density distribution of that latitude, and induces scintillations. At the bottom, you can see one example of the such an scintillation effect captured by the SAR's azimuth servant shift estimation method. It is near the Tromsø. Its scene extent is 70 by 70 kilometers. They can see some very large azimuth servant shifts up to plus 30 meter, and they are very well aligned with the direction of the geomagnetic field projected to the SAR observation geometry. At high latitude, because the orbit direction and the geomagnetic fields are perpendicular to each other, they are quite sensitive. The Faraday rotation becomes quite sensitive to the TC, the electron integrated electron density. So, yeah. And in the contrast, in the low latitude, the source of the scintillation is completely different, completely internal. At the post-sunset sector of the equatorial ionosphere, the devoid of the electron density distribution at low latitude formed by the recombination process start to generate Rayleigh-Taylor instability, and they start to ascend. But because of the motion of charged particles are strongly confined by the geomagnetic field at that local area, they are extended very extremely long. And there, these irregularities of the electron density distributions causes on SAR to be observed because of the diffraction effect they causes. At the bottom, black and white picture shows this is not something modified, just the amplitude imaging, scaled from -8 to 6 decibel, because the diffraction effect causes the undulation of backscatter. Its extent is in horizontal direction around 60, 70 kilometer, and vertical direction is 10 times scaled squeezed into. So the geometry of at low latitude, the orbit direction is perpendicular to the geomagnetic field. So TEC becomes ineffective to induce Faraday rotation. However, it does not mean that polarimetry is useless in the observation, because the squint dependency of the Faraday rotation, the conversion factor change is strongest along the equator, so we can still use polarimetry to estimate TEC on the equator. Then, what is happening at mid-latitude? The most popular ionospheric activity in mid-latitude, at least among the ionospheric researchers, is traveling ionospheric disturbance. It is waves of the ionospheric undulations of which amplitude is less than 1 TCU, or even weaker than this one, and obviously wavelength is some hundreds of kilometers or even longer. So single GPS station cannot observe this one, but large and many GPS stations of network can observe this one. Luckily, in 2019, August 20th, GeoNet, the Japanese GNSS receiver network, has detected the suspicious traveling ionospheric disturbances. On TC map shown on the left, the TC distribution is quite calm, but on the right, the TC differences in 15 minutes shows some disturbances aligned in north-south direction, and its amplitude is around 40 to minus 80 milli TCU. It's quite small. On the very right, it shows the positions of GNSS receiving networks, and the coincide the ALOS-2 acquisitions passing from south to north, 8 ones. So its extent is the swath width in range direction is 42 kilometers, and its length from the south to north is 460 kilometers. It corresponds to the time, azimuth scanning time around 70 seconds. This slide shows the Pauli color-coded image of this acquisition. At top is the coincide acquisition. The greenish color is based mainly due to the forest and agriculture field of this area, but at the very south, the greenish colors are from the rotated dihedral backscatter from the metropolitan area. And luckily, almost a year after, 2020, 18th October now, they made a second acquisition that enables the interferometric applications. Comparing two Pauli images, they are quite similar, and by explicitly estimating the level, each channel how much strong they changes, then at the bottom row we can see they are quite gray, so there's no big difference of the land use or natural status. So from there, because we are available with the quadrupole imaging, we try to estimate Faraday rotation. The Faraday rotation is the rotation of a polarization plane around the line of sight in the linear basis. It happens under the magnetized media. This kind of media are a kind of a special type of anisotropy, of which eigenpolarizations are circular basis. Therefore, in the circular basis, the Faraday rotation is interpreted as just the phase difference of two circular waves. What the famous Bicker and Best estimator do is exactly measuring the phase shift or phase difference between two circular bases. Here we can see the matrix 1 is the transform matrix from linear to circular basis. The Faraday rotation is directly proportional. So the Bicker and Best estimator calculates the phase difference between the left-right and right-left polarizations. The Faraday rotation is directly proportional to the TC, which is again the integrated number density of the electrons, and also proportional to the BK, I will call it in short, the parallel component of geomagnetic field to line of sight. These two parameters are connected to the Faraday rotation in this form shown at the bottom. And our test site geometry, 1 TCU induces almost a quarter degree of Faraday rotation. This is the result of Faraday rotation estimates. At the top, it shows that Faraday rotation changes from 0.2 degree or slightly higher to 0.8. And a year later one, it shows a slightly higher level of Faraday rotation. It is possible to estimate the difference of Faraday rotation. Then it shows the feature that directionality that runs obliquely through the obliquely. And another point is there is some artifact like depression of the Faraday rotation value around the fifth frame because the extent is 8th, so the fifth frame shows some low the value of the differential Faraday rotation, and it is associated the slightly overestimation of Faraday rotation at the fifth frame on the first acquisition. Also, there are another point, I was almost forget, there are some spiky, the overestimation of Faraday rotation. Also, we can get some Faraday rotation even over the ocean surfaces if they are not completely specular. But it gives another point that the azimuth ambiguity from the ground also contributes to the estimate of Faraday rotation on the ocean. So we have to be somewhat cautious to the interpretation of Faraday rotation values on littoral sea area. So we step forward slightly by converting the Faraday rotation to TC. Here we show the pattern is quite similar. I said that in this region, 1 TCU is induced. 1 TCU induces a quarter of Faraday rotation, but in this slide, I elaborated the conversion by calculating the conversion factor BK from each point. So we can see around 10% of the increase of the BK parameter from south to north. So we can explain also some 10% of the increase of the Faraday rotation, especially the second scene, attributable not to the TC change, but the change of the geometry. And now, because we are available with the interferometric pairs, I also applied the interferometric analysis. The top shows the interferogram, of which the delta T is around a year. Because here I used a quite large number of looks, the deviation of phase estimation is quite low, but seeing the coherence map at the bottom, they show, coherence is quite low, especially at the forest area at north. We can see, again, around three cycles of fringes at top, and the direction, the obliqueness of the pattern is coinciding with the differential TC, differential Faraday rotation we see. And again, very funnily, the fifth frame shows some strange behavior, anomalous behavior of the pattern. Now we apply the split spectrum method to estimate, to extract the ionospheric contribution from the interferometric approaches using the dispersive character of the ionosphere. So to make it, we made two interferograms at pH and P low, and by linear combination of the sum and subtraction of these two different interferograms, we can extract the dispersive ionospheric phases here. In the case of ALOS 2 pulsar 2 condition, the center frequency is 1.236 gigahertz and delta F is 13. So it means here the factor F0 over 4 delta F becomes quite large. So anyhow, this figure shows two interferograms at low and high center frequencies. They are, it have to be quite similar, but there are some differences which can be exactly visible at the south part. From the equations before, we could calculate the ionospheric phases. They show the same, the directionality obliqueness in this direction, and again, some depression in fifth frame, and then compared with the ionospheric phase value estimated from differential Faraday rotation, it's like this. So both two estimates are quite similar each other. So you can say mid-latitude ionospheric disturbances are detectable using both the polarimetric and interferometric method, and the differential T-state estimates from the two methods are quite consistent. We could, at the same time, identify a couple of problems. One is the discontinuity at the fifth frame of the both polarimetry and interferometry. And there are some strong azimuth ambiguity visible over sea surface. And there are consistently spiky Faraday rotation biases over the urban area. And we think this is another aspect of the azimuth ambiguity. So we analyzed some polarimetric analysis to estimate noise equivalent sigma 0 using the fourth eigenvalue of the covariance matrix. It shows how they are different in two acquisitions, and their levels are quite low at ocean surface because there's no backscatter, while at the ground, the level of the NSG increases around minus 24, 25 decibel. And there are strong azimuth ambiguity effect at ocean. We can see quite clearly, and also at the lakes, here and here, we see these effects again. So another interesting point is in the case of second one, along the azimuth time, there are some changes of the NSG level. Maybe this is related with the JAXA's processing routine. So yeah, just I can guess. No. Here I see more closely this spiky bias of Faraday rotation estimates. In the master and slave, during the two acquisitions, we can see the biases of the Faraday rotation estimates are consistent. So we guess that their sources somewhat on the ground, not ionospheric one. And this might be likely the ghosts of the very strong targeted urban area, because we can see them only around this urban area, not in the forested parts of the much north part. So we here see more closely what the Bicker and Base estimator exactly do to estimate Faraday rotation. At the bottom, two scatter plots are shown. They are the real and imaginary part at X and Y axis, shown what the value of the SLR and SRL conjugate multiplication. So here the red cross is the average of all the distribution, and Faraday rotation by Bicker and Base estimator finds out the angle of this mean value as the 4 times of Faraday rotation. On the right, this is normal case, is quite good, but in the disturbed condition on the right, you can see over the normal distribution, we can see some strong contribution in the azimuth, the imaginary parts. So they elevate the average value to the imaginary parts, so the Faraday rotation estimate becomes strongly biased. So in order to cope with this problem, I was thinking about, instead of just taking the average, to find out such a line that passing the origin best fits the distribution. So shown like the green line here. Then I could possibly build a line first to parameterize the line using the slope tangent theta, and by finding the minimum solution that fits the distribution should meet this condition, and then the 8 times of Faraday rotation becomes some parameter we can estimate from the SAR data itself, where the X car and Y car are the real and imaginary part of the SLR, RL, conjugate multiplication. Then this shows the result of the new Faraday rotation estimator. Then we can see the spiky biases of Faraday rotation could be largely suppressed at the cost of increased noise level. But potentially, this method can be applicable to urban area. But at the same time, we have to think that this new Faraday rotation estimator has double wrapping cycle. So the Faraday rotation is not 4 times, but 8 times of the estimated number. So it's less optimal to the low frequency systems like biomass, if not compensated. As a last condition, not polarimetric and not interferometric analysis is performed to the data set. This is azimuth solvent shift estimates of the first acquisition where the ionospheric disturbance effect had been detected. We can here see clearly some pattern that runs the same direction as the projected magnetic field alignment. Here we can see some shifts plus minus 1 meter. At L-band, 1 milli-TCU per kilometer can induce ionospheric gradient can induce around quarter meter of azimuth shift. So the azimuth shift estimates indicate quite non-quiet ionosphere. They are well aligned with the projected magnetic field, and geomagnetism seems to govern the small scale dynamics, as we can see. They are well aligned there. Their effects are not visible either polarimetric and interferometric analyses. And SAR is the only tool that can map these small scale irregularities. Not any ground-based radar or GNSS network can catch it. These effects are so high resolution and high accuracy. So I can conclude that our research is like this. The mid-latitude ionospheric activity is observable at L-band. Polarimetric method and interferometric method yield consistent results for the estimation of differential TC level and waves of ionospheric disturbance of amplitude of 0.5 TCU and wavelength of 200 kilometers could be detected. And a new Faraday rotation estimate had been proposed, which is less sensitive to the azimuth ambiguity effect. And also kilometer level scale ionospheric irregularities exist, and they can be also detectable using the azimuth spectral, azimuth solvent estimation method. Thank you very much for attention, and also JAXA for the data attribution. Thank you very much.
So thanks, Yoon. Any question from the audience? Sean?
Thanks, Junsu. It's a very nice talk, as usual. One's a question and one's a remark. I'll do the remark first. I mean, you've got to be careful when you say that you can map the ionosphere. Yeah. Because you can't map the ionosphere. You can map it along the orbit, only along the orbit. So, for example, biomass will be very good for the dawn-dusk orbit, which is an interesting time for the ionosphere, but we can't map the rest, and none of the missions can map the rest. Okay.
Yes, because we are on the fixed local time, so, but because we have somewhat large swath width, so if we go to Rose L, then even at the ionospheric altitude, the swath width will be around 200 kilometers, and this is, I think, wide enough to say this is a mapping of the ionosphere.
The question, though, is you saw what you think was a traveling ionospheric disturbance, but they are normally launched by a big event in the aurora, and then they propagate down to the equator or can go through the equator. Do you know whether that event matched a big event up in the aurora?
I'm sorry, I didn't catch your key point, sorry.
As I understood it, the observations you showed corresponded to a traveling ionospheric disturbance.
TID, yes, I understand, yeah.
And what normally launches a TID is a big event in the aurora, and then it propagates down through the mid-latitudes. So my question is, do you know if for that event there was a big disturbance up in the auroral zone?
Oh, on this date, I just, I was searching for some coincidence event of TID, suspicious event, and ALOS data. So I didn't search for if this, the initiation of this TID event is somewhat related at higher latitude.
Yeah, because you'd see it in ionosons as it was coming south, or it could be coming from the South Pole. No, I mean, the presentation was great. It's just what I'm saying, there are other things that could corroborate what you're doing, particularly ionosons further down the latitudes. Okay.
Thank you very much for nice suggestion.
Any other question? Maybe I had another question, but it was anticipated somehow by Sean. So is it, you think you could do some similar analysis also in P-band, where the Faraday rotation would be much larger, or the resolution maybe is not adapted to this type of analysis?
Well, for me, the big advantage of the ionospheric application of SAR is we are relatively free from the resolution matter, because the ionospheric things are normally quite high, large, so we can reduce some resolution by large multi-looking. We can still see some ionospheric things. So, yeah, in P-band, they is more sensitive to the Faraday rotation around the factor of 8 and 9. So, yeah, still, in the case of biomass, I think it is much more favorable condition to the ionospheric monitoring. This is my personal opinion.
We will see.
Yeah.
Any more questions? Well, then if not, thanks for your interesting presentation.
The next presentation by Pardini Matteo. Sorry. Costantini. Yes.
So, good. This is
DLR. Germany. This.
Okay. So, I think it's easier. So, good afternoon, ladies and gentlemen. That's a presentation about using polarimetric measurements to estimate the electron density profile of the ionosphere. So both presentations before were addressing ionosphere, and this is going also in this direction. That's the result of a master thesis of Simone. And Simone was supervised at DLR by Matteo and Junsu, and in the University of Pisa by Fabrizio. So one master student, 3 supervisors, a nightmare for him, but he managed very well. So, and we thought that this work has some relevance for future missions and the potential of them, and therefore we thought that makes sense to go through it. So every spaceborne mission which images the Earth through the ionosphere. So this means that the propagation through the ionosphere introduces a number of more or less serious artifacts or disturbances in the SAR image, independent of frequency. We see this in tandem X, but of course, with lower frequencies, these effects becoming more severe and not more so easy to be avoided, to be ignored. So many of these distortions are controlled by a single parameter, widely, the so-called total electron content, which, now I need a pointer that maybe works, I don't know. So here, it is given by, now with 2 remote controls, it will be a comedy. So it is given as the integral over the electron density along the propagation path. So, and if you know tech, you are able to, I don't know, assess or even if you are lucky, to compensate for some of these distortions. And now comes polarimetry, and as Junsu was making the point before, but also Son, so polarimetry allows you to estimate Faraday rotation very accurately. What is Faraday rotation? Faraday rotation is the rotation of the polarization plane imposed by the propagation through the ionosphere. So, and if you look from what Faraday rotation depends, it depends on the same integral over the total electron content, over the electron density, but it has also modulated or multiplied with this geometric factor, which is nothing more than the projection of your propagation vector, so the line of sight of the radar, if you like, to the magnetic field component at the particular location. So the idea is measure Faraday rotation, get tech, and use tech to compensate. This is one approach. And in some way, it's also followed to calibrate biomass. However, the conversion of Faraday rotation to tech depends on the profile, depends on the vertical structure of the ionosphere. So this is widely unknown. So if you make this conversion without knowing the vertical structure of the ionosphere, you can make an error on the order of 5 to 10%, in some dramatic situation, even 20%. So knowing the vertical profile of this electron density content may allow you to make a more accurate conversion. And this presentation of this work is going to address this estimation of the vertical electron density profile by means of a single SAR image. And it's nothing new, since almost the middle of the last century, people working on the ionosphere was trying to do this. We are trying, or Simone was trying, to do this by means of Faraday rotation measurements and to explore how they change across azimuth sublux. Why this? So for every the difference between two azimuth sublux are two things. First of all, the line of sight changes. So this means this geometry factor changes, the projection of the line of sight on the geomagnetic field. And the second thing what changes is, of course, the propagation path, and this means that you have an effect there. So the challenge, what we have is that this angular change, so we'll try to explore our angular diversity, but this is very small. For ALOS, for example, this is 1.5 degree. So it's not the principle, it's just the boundary conditions which make this challenging. So the first what we have to do is to express Faraday rotation as a function of azimuth and squint angle, so look angle if you like, and then you see that as well as the electron density, as well as the electromagnetic field, depend on both of them. And then you have also the line of sight, which is a dependency only on the squint. So now, one important point is to take this direction of propagation and split it into components. The one is parallel to the direction of propagation, and one is parallel to the propagation vector at 0 Doppler. So, and then we get the two components, and with this we can split this projection also into components, and we become one component of this which is parallel to the 0 Doppler range, and one component which is parallel on the flight direction. Good. So, and now with this, we put it in our equation for Faraday rotation, and we get the Faraday rotation depending on these two components, and the one is a cosinus squint angle dependency, the other one is a sinus squint angle dependency. And we are coming back to say we have to deal with small angles. So this means that we can make a small angle approximation. The cosinus becomes 1, the sinus becomes beta, and we end up to have here two components which are different sensitive. The one is only indirectly sensitive through the sensitivity of the geomagnetic field, and the other one has a direct dependency on the squint angle. So if you like to make now to use this to estimate something, then you like, of course, that to maximize this term and to minimize this term. But unfortunately or fortunately, how big these terms are relative to each other are depending on the geometry, on the geomagnetic field and your orbit. And it seems here, let's assume that your Earth is a dipole, then this is the magnetic field, and then your orbit is around here, and then you see automatically that on the equator, this is large, and on the poles, this is small. And now, this is now the real field, and much more interesting is, of course, the horizontal component. For a polar orbit, you can take this as an approximation, if you like, of this term. So, and then you see that close to the equator, this term becomes small. Far away of it on northern and southern latitudes, these terms become small. And now we are going to compare two locations, so a northern one and the equatorial one, the one we call Fairbanks and the other one we call Malaysia. And maybe one more time here. So this is now the azimuth dependency, because this is what we're going to explore, for the Fairbanks side, for the component which is parallel to the 0 Doppler range, and this is for the component parallel to the platform movement. And we see that this one is the main which is changing. Why it is changing? Because the geomagnetic field is changing. And then we move to the equator, and then we see that these two are reversed. If we like the dependencies, this is because the geomagnetic field looks in the other, almost in the other direction, and the main variability is in the zero Doppler range component, and the constant is here. But much more important is the difference in this axis here. We like to use this one. You remember, parallel to the platform movement. And you see here that if you compare this axis with this, that you are here about a factor 40 more sensitive. So, and this is exactly the one which you like to explore. So, some sensitivity analysis, you would like to get an estimate of the vertical profile of the ionosphere. You will make a sensitivity analysis, you take a Chapman layer, and there are 3 parameters which we modify. So the height of the maximum, so then the width of the upper part of the layer, of the upper distribution, and we also modify the surface under the integral of under the surface, which is the total tech. And we try to do this now for our 2 positions. And what you see here is for the Fairbanks geometry, for the northern geometry, the dependency or what changes in your Faraday rotation measurements when you start to vary, in this case, the mean height. And you see some sensitivity here, and this indicates the 2 angular extents, or the angular extent of the ALOS azimuth look, azimuth aperture, if you like. But if you see the values here, they are very, very small. And what happens if you start now to modulate the shape? We see almost no sensitivity. And if you modulate the total electron content, then of course you get this because this is what you measure. But you see here, of course, you are more sensitive to the maximum and significantly less sensitive to the shape. And we move now to the equatorial area. So the only what changes is that geometry. And then you see suddenly that here you have some hope. So these values here are, again, order of magnitude at least higher than this one, and the sensitivities are higher. And you have a chance here, according to this simulation, not only to get the location of the maximum, which is, if you like, a 0-order approximation, but you have a chance also to get something about the shape. Next one. An important point, not all the points of the ionosphere are the same, because this is your orbit, this is the ground, and this is where you focus. This is your SAR image, and this is the ionosphere. And let's take a point on the top side of the ionosphere. This has exactly this trace on the image. You see it for so long. A point on the bottom part of the ionosphere is significantly less. This means that in your data, you have more information about the top of the ionosphere than on the bottom. And this means, again, that it's easier to get information about up here than down here. Good. Let's go to make inversion. Inversion is already addressed in multiple, as I said, old papers. So you discretize the space. So the nadir or the range azimuth space, you have a number of voxels, and you express the Faraday rotation as a function of azimuth and squint angle as a sum of the contributions of the voxels. And in every voxel, you have the line of sight component, you have the electron density, and you have here your geometry. So you like to know this, you like to know this, you measure this, you know this, and you know this. So this means that you are able to build up an inversion, a linear equation system. So these are the Faraday rotations, these are the sums across the voxels, and here is in principle your ionospheric profile. So the problem is the angular diversity, too small. This means that in general you always have to fight with ill-conditioned inversions. And this means that this standard least square solution do not help you. You need regularization in different ways. Good. How an inversion may look like. What you see here, we are in the Fairbanks geometry. You see here the input. This is what we like to estimate, the Chapman layer. And these are now the reconstructed profiles for a 9 kilometer aperture, which corresponds to 0.75 degrees, a 19, this is the actual ALOS one, and a WFAN, 38. So we just increase the angular variability in our measurements. So, and we have these three parameters to measure: the peak, the top, and the bottom. And then you see automatically, so you get the height, you have big problems on the bottom of the ionosphere and less problems on the top of the ionosphere. Now, what we do, we change the height, the rest is constant. This is the reconstruction for a different height. And again, here, because you are a bit higher, you get a better performance on the bottom part. And then you can change the structure, so making the upper part fatter. And then you see already for the standard number of, for the standard SAR configuration of ALOS, you go here, you collapse. Huh? So you need wide apertures to get something like the red one, like the green one. And then we move, we change the tech. And then you see, of course, that you are not sensitive. Why? Because the tech is the integral under the surface. So in principle, you always get the correct tech, but you get the wrong profile to be integrated. Therefore, you don't follow this. And then the same for the equatorial, for the better suited case. And you see here, of course, a bit better behavior. You do better on the bottom of the ionosphere, but still not great. And then increasing the height, you are able to. So this means the good news is you have a higher sensitivity to the maximum position of your Chapman layer, the vertical position. Here you have some success to track the shape. And here we have the same story that the overall tech is fine, but you get the erroneous profile, so the integral is correct, but the profile is wrong. So, and how it looks with real data. So we have the two situations. Here, this is Fairbanks, and this is Malaysia. This is ALOS 1, this is ALOS 2, and this is the Faraday rotation. And we try to look at cut here. So here you have a significant disturbance. So you jump here from 1.5 to up to 4 degrees of Faraday rotation. And here you have a more interesting scenario on a tropical case. So this is now the change of the Faraday rotation estimates for approaching and departing sublux. This is your information. For the one case from the other, here it's of course because you have this step inside, it looks more impressive, but it's not what you're using for. And that's the reconstruction. The reconstruction for the first and for the second case. So with one kind of regularization, you see that you have a significant problem down here. We can increase the change the regularization, then of course it becomes better, but still here the lower part are inaccessible. Why? Because on top of all the lack of sensitivity, you have now also the errors, the variance in the estimation of Faraday rotation, which goes hand in hand with real data. And then, what is there? If you compare this with this, however, that's the Faraday rotation. So this is the vertical and this is the horizontal. But you see that, of course, what you get, it is not very far away. So there is still hope. Good. I think here you are. So it's not dead, and it's still alive somehow. But of course, its future depends on the angular diversity of your SAR. So, and of course, where you are on the planet. On the tropics, it's significantly easier than on the boreal issues. So, and this, of course, are in this room good news for biomass, because biomass has both. Has longer angular sensitivity, longer apertures, and at the same time, you have also a higher sensitivity to the defect. So, yes, so I think that's all. Catching the 3D structure of ionosphere, it is, of course, very important for driving the accuracy of ionospheric corrections to the next level and to the accuracy where applications today are asking for. So I would like to thank first Simone and then also for you for your time. And if you have questions, I'm happy to discuss them. Thank you.
So very good presentation. Now the paper is open for questions.
Yeah, thanks, Kostas. Again, it's excellent work on the ionosphere DLR. Two questions is, do you intend to do this systematically and actually produce sort of what do you call this, a synopsis of the biomass behavior? And the second question is, are you looking just, this is ALOS 2, so it's, is it noon midnight? I can't remember. What's the orbit?
ALOS 1 is down dusk, ALOS 2 is the opposite.
Oh,
ALOS 1 is down dusk, ALOS 2 is the opposite.
Oh, right, okay, sorry, I thought one was noon midnight. Okay, are you going to look at, okay, you're going to look at both ends of the orbit, because it'd be interesting to look at the difference between the ionosphere in the morning and the evening, if you're able to do that.
We are not so far. We just try to see, because we need it for biomass, we need it, it improves. It's also the next step to trying not to get only the height of the layer, but getting more out of it. So, and to understand a bit better now the limitations because of geometry, where you are on the planet, and because of your integration time. Now, of course, if this works, we would like to use it everywhere. But this has to be proven that it works. But we expect, based on the numbers and what we understand, that it works better for biomass than for ALOS. And for ALOS, you rely to start to condition even more. You can think, you can condition using a ionospheric model or whatever, but maybe biomass is by itself good enough to get here out something.
Oh, yeah, sorry, I just thought, on the bias, can you use ionoscent measurements to help you to correct things?
Do you have them everywhere? I think SAR, it's much better than all of them together.
Okay.
Any questions?
Then I'm free, oh? Thank you.
Thank you.
So the next and the last presentation is not about calibration, is more about present SAR missions. In particular, it's by Zhenshu Zhou from CSIRO, which is the Commonwealth Scientific and Industrial Research Organization in Australia. And it's about NovaSAR-1, operational updates and CEOS analysis ready data products for land, PS compliant, which means products family specification compliant, analysis, ready data production in Australia. The title is a bit complex, but the content hopefully will be less complex.
Yes, thanks, Chairperson. This morning, our colleagues from the ESA and the JPL mentioned about the IRD. Now, sorry. This morning, colleagues from the JPL and the ESA mentioned about the IRD. So today we will talk about some of our practice about NovaSAR IRD. And also, the NovaSAR S has been mentioned with one of the PolInSAR workshop objectives for many years. I guess that will be the first talk about the NovaSAR. Yeah. Here's my talk's content. There are main two parts. One is NovaSAR operational updates, and also about the CEOS IRD. PSF combines the NovaSAR IRD production. I will give you a brief introduction about the NovaSAR 1. This is the official name compared to the NovaSAR S. This is low-cost SAR technology demonstrated by sharing satellite technology, UK, and with Airbus Defence and Space, with UK Space Agency sponsor. CSR and the NovaSAR partnership had acquired about 10%. The share of the acquisition and the tasking capacity of the satellite provides the national with the the first ever surveillance EO satellite capacity in Australia. And this is some spikes about the Novasar. And this is S-band. This is the satellite, the state. The SITL happy with current state, and the satellite, the health is expected for this stage in this mission. Calibrations ongoing with the annual campaigns and orbit maintenance maneuvers over every 2 months to synchronize with the Sentinel-1, cause some disruption, but we are loaded well in advance so we can plan or coordinate. And this is also with AI sensor on board with the satellite. This is the AIS pilot acquisition stage. And this Novasar has been set up as national facility as in Australia. So we acquire the request over online or the port, and also we provide the data harbor for data access, and also we have done some background mapping, and also established downlink link in Alice Springs, and also have successful projects and collaborations. This is the data request port. So this is similar to the data acquire port with SKI, the space astronomy for the international data acquisitions. And also we have the data port harbor provide all the source data available, free available to public. Here are the use registered from 28 countries, and there are 400 the registered users. Here is the background mapping with 35-meter resolution, the triple mode in Australia. And also, this is good addition to other submissions. We could give a coverage to very small island in Pacific nations, especially when the Sentinel-1B is available at the moment. Here is the ground receive station established in Alice Springs. It's the first Australian Aboriginal people owned the company to do the data downlink. We also have done the calibration for radiometric and geometric calibrations. So use the calibration site in the Queensland, the colorimetric arrays, and also WA, the geodetic stations. I think these two have been used for many of the submissions for ESA, DR, JAXA, and also NASA's. So we also think about possible the calibration site in Antarctica. Hopefully that will be discussed more in October at DR. So that will be more interesting for more space agency or submissions partners. This is an example. We did the Novasar calibrations with the Queensland, the colorimetric arrays. So this is the colorimetric array on top of Novasar imaging, and also show some locations of the Novasar with SAR imaging, with the case of the colorimetric. Okay, here is the ground segment. We built this, show the diagram. We received the link, direct link to Australia, and we built the data archive, and also we built the data process, the workflows. This is current capacity share using the main for the the projects, and also for the background, the mapping, and also some disasters, and also for term, and also for the calibration validation. The second topic is about sales RD. The name from the cutoff error officially changed to sales RD because to accommodate the RD for ocean, not only for land. So if you're looking for more information, please get this site, get for more information about the sales, the RD product family specification requirements. So for the SAR, the normalized rate backscatter is now version 5.5. We process all the novel SAR with these requirements. So this is the name conventions for the novel SAR sales RD, NRB, normalized rate backscatter products. So, so the sales, that should be sales RD. We including the ascending, descending, left-looking, and right-looking, and also very different combination of the observation image modes. Here is an example of LOSA, the RD product file structures. Within the zip the product, we including annotation, measurement, preview, and also including format of the XML and YAML, the general metadata for machine readable, the general metadata products. This is the per pixel metadata and the annotation, including the gamma to sigma ratio, local incident angle, the mask, and the scattering area. This is example for the measurement. This is for the preview with the quick look imaging and also on the KML for quick share on the Google Earth or QGIS. The data format is cloud optimized GeoTIFF and also including floating 62 for per pixel metadata and also unsigned 16 for the measurement. This is the main steps for the sales RD, the combined Novasa RD productions. We use the Gamma software for the process. Here show an example of Novasa RD process. So this is sending left-looking around the kinds in Queensland. This is the source and the imaging. After the radar geometry convert to the map projection for the beta nodes on the right. Then we could have the sigma nodes after radiometric terrain correction on the right compared to the beta nodes. Then we have the gamma nodes RTC on the right. So here shows the per pixel metadata imaging. This left side panel is the ellipsoid incident angle, and the middle is the scatter area, and the gamma to sigma ratio on the right. And this is the beta nodes. If we divide by scattering area, and then we could get the gamma nodes, normalized rate backscatters. So now to show you how we use the per pixel metadata to generate the different products. If we use the gamma to sigma ratio, we could convert to gamma nodes to the sigma nodes for different applications. And also we could use the very popular SLAP toolbox to convert the measurement, linear intensity, or we convert to measurement in dB. So we can also use the popular the tool to do some the spectrophometry spec filtering not being provided as RD, but you could done by end of users, and also some of the correlation. Now I will show you some of the Novosar RD applications samples. This is for the bone area mapping in Fisher Island, Queensland. So we could compare with the Sentinel-2 before and after, and Novosar, and compare with Sentinel-1 combined with Sentinel-1. So we have the bone area image. And also, we have used for the flooding mapping in Australia. This is used before the flooding and during the flooding, we could get the flood area on top of the site imaging. And also, we could use the dual pole imaging to get only single date acquisition to get the flood mapping in WA early this year. And this is another example use Novosar for the ship detections. This is the acquisition over the Phillip Bay close to the Melbourne. So we could classify with the vessels less than 100 meters in length and greater 100 meters in length for 2 of these cases. This RD probably is not quite interesting to the SAR experts, but I think that would be very good to promote the SAR data technology and applications to more generally yield the communities. This is I've done the safe assessment. I have just recently submitted to the sales AVS virtual constellation for review. The data, all the source data are available at the port, and also this assessment review, the sales review is underway. Okay, thank you very much for your attention. I have one more information for sharing with the community. So we will have a new poster especially for the PolInSAR start very soon. Will be announced in next month. If anyone would be interested in, please keep an eye on the PolInSAR group at LinkedIn. We'll post it there as well. Thanks.
Is there any question from the audience? Okay. Sorry.
Did you use Snap software?
Yeah, we use the Gamma software for the RD process, but the SLAB just showcase how you use SLAB to do further the process.
A question from me. I understand that there is a quite good coverage over Australia, and that the data are available open and free, right? Yeah. So is it the case only for the data over Australia, or is it also for the other data? Only the data over Australia distributed open and free, or also the others?
Yeah, with the current archive, we acquired another partnership. We acquire in Australia and also have some acquisition in Africa, in the North America, and South America. And also India is also the partnership with the Novosar as the main part of the partnership.
So it depends on the area of acquisition, whether the data are available for free and open.
Yeah, yeah. We could task data acquisition around global.
Yeah. So what about Europe, for example? What about Europe?
Europe, yeah, it's possible. I think the UK, SITL, has the resource to do this kind of acquisition. Yeah, but if your proposal has been approved, the acquisition is possible.
Okay, thanks. So then if there are no more questions, thanks a lot for your presentation, and we can conclude this session. Now there is a coffee break, right? Yeah. Good. So yeah, we reconvene in about, at 4:30 we should start again with the next session.
c'est là qu'il faut. Oui, le pointeur vert sur le vert.
Ah mais attends, il doit y avoir toutes les couleurs, non? Non? Tout à l'heure, il n'y avait pas un rouge? Ouais, bah non, t'as raison. Comme il a fait Costas, il a peut-être utilisé un autre
Il a
pointeur.
donné le sien, ouais.
Ah, c'était le sien, d'accord.
Peut-être, hein.
Et après, non, c'est quand même pas tout automatique. Et là, il faut lancer, on a la main comment là-dessus?
Oui, il faut le faire. Bon, de toute façon, on est parti pour être en retard.
Ouais, bah ouais.
Okay. Welcome back, ladies and gentlemen. We have a speaker. So the next, sorry, my name is Laurent Ferro-Famille. I come from Isaïe Supairo and CESBio in Toulouse. And together with the co-chair, Ludovic Villard, also from CESBio, we are very happy to welcome you to this session on PolSAR and PolInSAR methods, which will be composed of 3 papers related to technical PolSAR and PolInSAR data processing. Unfortunately, some papers were cancelled, originally planned were cancelled in the session, so we will have 3 papers, and at the end of this session you will have another session presented by Francesco Sarti on the analysis of the recommendations from the former PolInSAR conference. So it is our pleasure to welcome the first speaker, who is Vahid Abkari, who is now with the Department of Computer Science and Mathematics at the University of Stirling in the United Kingdom.
Good afternoon. Hello, everybody. Welcome to my presentation. I'm here to talk about 2 change detection algorithms that we have developed. One in my PhD, and another one recently we published a paper with my French colleagues. So here I'm presenting these 2 detectors and compared with a well-known change detection algorithm named likelihood ratio testing statistic. So I'm gonna give some brief introduction and about the theories of these 3 detectors and show some experimental results, and in the end I'm gonna discuss about each of these detectors and compare them. in terms of the performance. So basically, these detectors are used for multi-covariance matrix data set. So we convert the scattering vectors into multi-covariance matrix data with the L number of looks. And we have two assumptions. The first assumption is that the X and Y as a two covariance matrices at time 1 and time 2 are statistically independent, and they both follow a scaled complexity star distribution. For X and Y, so we have got two parameters of the scaled star distribution, Lx and Ly, and sigma X and sigma Y. So for hypothesis testing, we have one assumption that Lx as estimated number of looks for each X and Y are treated as a global parameter for the entire image for at two different times. So we then do hypothesis testing under null hypothesis that we test if these scale matrices of X and Y are equal, and alternative hypothesis for change pixels. So this is just give you some introduction about these three detectors I mentioned. Firstly, the Wishart likelihood ratio test statistics was developed in 2003 by Technical University of Denmark, by Conrad and his team. So the second detector named complex kind-Hartley Lowry trace statistics, which I developed in my PhD at the University of Tromsø together with my colleagues at the University of Genoa. In 2016, the paper was published. And then the third one, which is published newly in 2022, it's named determinant ratio test statistics. So basically here, I'm here talking about these three detectors and discuss about the results and also a theoretical aspect of each of these detectors. So the first one is well-known detector, likelihood ratio test statistic, which is this formula here, which is function of number of looks, Lx and Ly, and D as a polarimetric dimension. And this LRT is asymptotically approximated by three terms as a chi-square distribution, where D is polarimetric dimension. And we have omega 2 in the second term, which is function of Lx and Ly, which are estimated beforehand. We do modeling this test statistic. And then we estimated threshold of likelihood ratio test statistic and using this integral, and we then apply this threshold on test statistic to get the binary change results. The second test statistics is named complex kind-Hartley Lowry trace statistics, which compare equality of two covariance matrices Y and X, Y covariance matrix at time 2 and X covariance matrix at time 1. That is used for hypothesis testing. And then there is no exact distribution for Hartley Lowry trace statistic. So we used Fisher-Snedeker distribution to approximate this test statistics, which has three parameters, Chi, eta, and mu. So to estimate the parameters of this Fisher type distribution, we derive the moments of Hartley Lowry statistics. For more information about how we derive these first, second, and third order moments of Hartley Lowry statistics, I refer you to read my PhD thesis. So, but basically these three moments are functions of Lx, Ly, and the polarimetric dimension D. The mu parameter is estimated from first order moment. It's easy to calculate. But to estimate the ET, two other parameters as a shape parameter of Fisher distribution, we need to use the second order and third order moments of Hartley Lowry statistic. But to do that, we need to localize moments of Fisher-Snedeker distribution and moments of Hartley Lowry statistic. So that equation. So to estimate these two parameters here, we use minimum distance optimization to get them. So that is important that we estimate LA and LB, or Lx and Ly in this case, accurately beforehand. Any bias in the estimation of LA and LB will lead to a very wrong problem in the fitting or distribution of the FS. So these are the steps that we used for HLT and CFAR type thresholding. I call it CFAR type because it's not CFAR. We use the principle of CFAR for thresholding. So these are the steps that we applied. So we estimate the ENL, or nominal number of, the number of looks for each image before and after change. And then this is the, compared to LRT, this is two-sided test. For LRT, all types of change are in the tail of the distribution, but here we can detect direction of change if you have positive change or negative change. But if you want to detect any type of change, we have to use a combined test, which is here, a maximum operator, that we take the inverse of y at time 2 and then multiply by x and then trace. And then also we take the vice versa, that we take inverse of x and y and then we combine it using maximum operator. So this is the way that we transform all pixels to the tail of the distribution. So when we do this, we need to put a number 2 in the integral to estimate the t, because we use both operators. So we estimate the t as a threshold here at a given probability of false alarm rate, and then apply it on our maximum operator to get the binary change detection map. And the third operator that we developed recently is named the determinant ratio test, which takes the determinant of Lxx in the numerator and Lyy in the denominator for hypothesis testing. So we want to measure the similarity between two matrices. For this, we treat the ENLs, as I said before, as distinct parameters for both x and y. So the one thing that we have done that is different than other two detectors is that we have derived the exact distribution of DRT, which is a Wilk lambda distribution of the second kind, which is also a product of beta distribution. But the one thing is that here it's interesting to see that it's just the distribution itself is a function of Lx and Ly and D. So for more information on how we derive this, I refer you to read this paper footnoted here. So these two plots show this distribution for dual pool data and for quad pool data. You can see this is for dual pool data, that the shape of the Wilk lambda of second kind varies with the number of looks starting from 2.5 until 20. And then this is for quad pool data. And then what we did for thresholding or getting change detection map, these are following steps that we again estimate the number of looks for both images. And then we generate the DRT statistics using maximum operator again. And compared to, I want to highlight that, compared to trace operator, because the trace takes inverse of x and they multiply by y, and then trace uses the only diagonal elements. But in here, I think the good thing about this detector is that it takes the determinant, it uses all elements, diagonals and off-diagonal elements. So this is, I think, one thing good about this detector, and we have got also the exact distribution of this detector compared to other tools. So we again use this maximum operator to solve this integral. And another point that I want to highlight, that our HLT detector was CFAR type detector, because this integral we solved it numerically. But in here we have got the CDF analytically, but to estimate the T we have to use numerical solution. And then we apply, after that we estimate the T parameter, we apply it directly on maximum operator to get the binary change detection map. So here I'm showing the experimental results. The one thing here to test that our modeling works better, that we have to test it with simulated data, because the L here is just the estimated number of looks is equal to nominal number of looks, because the samples are generated independently. So it's a good that we do it with simulated data, not going directly to real data. We want to test first if the modeling of the HLT, LRT, and DRT has worked very good with the distribution that we have derived analytically, or yeah. So these are two quad pool images before and after change. We simulated the classes, 7 classes. We have taken the statistical parameters of each image from real data. So class number 7 here has got very high texture. This is simulating urban class. Class number 3 is from homogeneous class of water, and the other classes has taken from agriculture and other vegetation types. So the image we have got also, that is ground truth, that we are going to use it for performance detection analysis. And this are just showing one example. For testing these images, we simulated with different number of looks, starting from 5 to 8. I think one thing that we want to test is that if this modeling works for lower number of looks, because it was more challenging than using images with larger number of looks. And in the equation of the equations of the HLT, in the denominator, we had some special cases that it could goes to infinity. So when the number of looks were small, so we simulated with different number of looks. These are showing just with L equals to 8, and showing DRT, HLT, and LRT. Test the statistics itself and the modeling. So the first detector is Wilk-Lambda second gun that has got very good fitting to the normalized histogram, and middle part is for HLT. Again, we used we estimated parameters of the FS that has got also good fitting to the histogram, and the third one is the chi-squared, 3 terms of the chi-squared distribution. So comparing these three, we have got some conclusion that DRT has worked better than other tools, especially for low number of looks. The HLT has got the problem, and also LRT for lower number of looks. This is the second thing. But when the L increases above 8, then both HLT and the DRT works similar. And also, one thing that I want to highlight here, that central class here that is more noisy, it's because this is the one class that we have taken from very textured class. So DRT has worked better than other tools. And in terms of the results with different false alarm rate, so we have, you can see that DRT has worked better again, and again you can see with different significance levels. And for looking into RAC curve, also you can see that the black curve, which is for DRT, it shows very larger area under curve compared to other tools. And then this is another example that we have used with a large number of looks of 24, 6 in range and 4 in azimuth direction, 2 images taken by RadarSat-2 in 2009 and 2010, before and after change. And this is the ground truth that we have got. The white pixel represent no change pixels, and the gray pixels represent change pixels. And these are the results of DRT in the first row, HLT in the second row, and the LRT in the third row. Maybe you see that it's a little bit speckly outside those validation pixels. We don't know if they are change or speckle or any noise. But the fitting that we have, you can see here, for all these 3 cases has been good. But DRT has been better than other trees. But the one thing that I would like to say here, that the HLT has got better results than DRT for larger specified false alarm rate, about 5 and 10. And we can also see that in the RAC curves that DRT again has worked better, but for a larger number of for larger values of significance levels, HLT has been better. So the other example is UAV SAR data, which we multi-looked with L number of with L equals to 6 before and after change, and this is the ground truth data. The results are here. That I think one thing that I highlight that again, the DRT has been better than other 2 detectors, but the LRT has failed when we looked into the distribution of the model that has been proposed when looking to the third one here. You see that always we have got the trouble with the modeling when we try to use the small number of looks. And finally, this table summarizes the characterization of all these 3 detectors. So DRT and HLT are both 2-sided. So we use maximum operator to combine positive change and negative change, or increased backscatter, decreased backscatter. So these two detectors we can use it for detection of the direction of the change detection, but the LRT is only one-sided. So in terms of the statistical modeling, as I said, the DRT is using exact distribution of Wilk lambda of second kind, while the other tools use approximate modeling, which are very dependent on number of looks estimated. In terms of performance, again, DRT works better for a small number of looks. The other tools, in some cases, fail. Maybe we have, especially in the texture cases. The future work, there are two things that I would like to extend this work. One thing is that because in the hypothesis testing, we only do hypothesis testing for a scale matrix of X and Y 2 different times. We ignore L here. L is treated as a global parameter, while in mostly urban areas, applications or texture cases, we have to estimate this as a local parameter for each sliding window of multivariance matrix data. For that, then we use this type of hypothesis testing that for H0, we use we test equality of a scale matrix of A and B, and also number of looks, and alternative hypothesis with distinct ENLs for each multi-look windowing. And then the second thing that we want to extend this work, the LRT has been extended to use the omnibus test for measuring the equality of several covariance matrices, that we measure several matrices. So we want to extend HLT and DRT both for this omnibus test. And before finishing my presentation, I would like to draw your attention that there is one special issue in DPI journal that I'm guest editor of this, so I would like to ask for your contribution for this special issue. Yeah, that's it. Thank you very much for your attention. Any questions?
Thank you for this presentation. Do we have some questions? Yes, Armando.
Please.
Thanks, Faid. Great presentation. Very good results as well. So I really liked it. My question is maybe a little bit theoretical, but have you tried to simulate some unitary similarity transformations? So the one that don't change the product of the three eigenvalues, but they mix them. So like dihedral became a trihedral. Because if the three eigenvalues stay the same in the product, then the determinant should be 1, right?
Yeah, exactly.
So the ratio of the determinants should be 1. So did you try to simulate it?
No, basically this is a good comment. We haven't done that, yes, but maybe in future we're gonna test this as well.
I think the fact that you don't see in the real data is a good sign. So maybe they don't exist.
Yeah, yeah.
So it's okay. Don't worry.
Yeah, that's a good comment. Thank you.
Any other comment? I may have one question. If you go back to the definition of your DRT test, you have a ratio of 2 determinants.
Okay.
So it means that you don't take into account the eigenvectors of your matrices. They can factorize.
No, we don't take that.
Then it means that X and Y could be different, and still you will get the same ratio. So you're just comparing the eigenvalues of both matrices, or the distribution of eigenvalues.
We only compare we only take the matrices.
Yes.
We haven't looked into the eigenvalues of these two matrices.
Yeah, but since you take the determinant, you take their product.
Yeah,
so you're comparing the change in the product of all the eigenvalues.
Okay.
Yes. Then it means that you could have different scattering mechanisms for the same eigenvalue distribution. If you apply a different eigenvector matrix, you can have very different scattering mechanisms from a polarimetric point of view. So did you meet this problem in practice?
I haven't experimented myself, but this is a good comment. My colleague Nizar Behlul has experimented this. But basically, this is a really good comment. I would like to thank you for this.
Okay. Thank you very much. Thank you.
Yeah, thank you. And I think, So I think it is time for the next presentation about, from Numesh Kati, and about polarimetric analysis of permanently shadowed region on the moon using dual frequency full pole data from Chandrayaan to the FSAR. So in short, probably the very highly hidden biomass on the hidden side of the moon.
Yeah.
The floor is yours.
Thanks for the introduction. So I am Unmesh. I am come from the Indian Institute of Technology in Indore, in central India. And so this is essentially a work done by the master student Hamish at IIRS in Dehradun. And I was requested, since he could not come to the meeting, to essentially carry out the presentation. So probably this is the only work which is done on the DFSAR at this meet, if I'm not wrong. So the motivation behind this was to kind of just to do a theoretical analysis for Artemis 3 candidate landing regions, which is something that NASA is working on, and one of the probable ones are in the South Pole of the moon. So these regions are different because like for Earth, typically our axis is tilted at 23 and a few degrees, and so most of the regions on Earth will get sunlight sometime during the summer or the winter season, depending on which side of the hemisphere you're on. But for moon, because of the peculiar conditions that it's tilted at just 1.54 degrees, so in these crater regions at the South Pole, wherever you have craters, the solar illumination is never found there. So these are perpetually dark regions, and so optical data sets are not able to visualize anything in this. But it has been theorized that in these cold traps, we have volatiles as well as water ice. So these volatiles are essentially whenever meteorites hit in these regions, they will break apart and they will spew their material, which will be in the lunar regolith in these regions. And since many of the areas which are along the crust, they have a very high variation in surface temperature going from positive 150 to negative 150. If and not the solar illumination is there, the water, whatever small amount of hydroxyl ions which are there, they can directly go from a solid state to vapor state, and so that's why they are called as volatiles. One of these motivations resulted in a kind of some work that Hamish did during his masters, which was to see if the Chandrayaan-2 dual frequency SAR data can be used just to analyze one of these areas. Chandrayaan-2 is a mission sent by Indian Space Research Organization in 2019. It carried a dual frequency SAR payload, which operates at LNS band, kind of what NISAR will do. However, this is a fully polarimetric data, but the data sets are not captured in all the locations of the lunar area. So we went through the database, which is publicly available on one of the ISRO's websites, and there are around total of 2,000 acquisitions, but only 200 of them have both L and S band frequencies provided. Out of these, only 20 were acquired in the South Polar region, which was of interest, and so hardly a few could be actually be used to process the data. So in this case, the data set that was used is given by this particular nomenclature, which essentially has this FP, which means it is a full polarimetric data. I don't know what the other, probably there is a date and time mentioned, but I'm not sure if dual frequency data sets are characterized by the nomenclature here. So this was captured on 13 September 2020, and this is the data set shown here, and we were interested to see the rim of the Faucini crater. So this is one of the probable areas which might have Artemis 3 land. And the reason is that the crater wall is kind of more flat and where probably the lander can land, and the darker areas might be more habitable and also might protect the astronauts from harmful radiation in the cosmos. So this has proximity to solar illumination because the crater is almost always illuminated. So solar power plants could be set up here, and also for it has a direct visibility to Earth. However, the immediate crater can host the does host the permanent shadow regions and can host the astronauts. Okay, so besides SAR data, we also downloaded a few of the optical data sets which were available here. So one of the earliest ones, not the earliest ones, one of the early ones was Clementine mission, which acquired data in ultraviolet and as well as visible. And so the resolution is very poor. So that is the image on the extreme left hand side. So this is a UV visible camera. Only the rim is visible, and because of the high albedo, the camera saturates. Then in 2009, the LRO mission has a wide angle camera as well as a narrow angle camera. So the second and the third images are from the wide angle and narrow angle. So the wide angle has a better tonal contrast, and so we can see a few more details, but nothing is visible inside the rim. The narrow angle camera essentially has a very long exposure time, and it tries to integrate even starlight which will be irradiant on the moon. And because of that, we can see the insides of the crater using this narrow angle camera images. However, because of the long integration time, there is a high noise, and the base of the walls of the crater are still hidden. And finally, the last image on the right hand side is the Chandrayaan 2 DF-SAR image. So this is essentially the linearly polarized image, HHHV and VV. And from the L-band data, we just color coded it, and we are able to visualize the entire surface. However, the topography of the crater is not immediately visible, but looking at both the optical and SAR, we can see that the rims of the crater are resulting in a more, okay, I don't know if this is visible, but this is the rim of the crater, and so it has a slightly higher volume scattering or HV component as compared to the base of the crater. Okay. So there was an issue with the way the data is provided by ISRO. So they provide a kind of selenoreferenced image, but these images are essentially binary images with the latitude and longitude given only for the four corners. And so they are not true selenoreference and could not be used essentially to also be mapped with optical data. So that has been one of the pain points kind of to use this data, and could not be done much with it. So first we just tried to analyze whether the cross-pole backscatter matches. So in selenoreference case, there is a correlation of around 0.9 between L-band and, at L-band and S-band. So on the left-hand side is L-band scatter plot between HV and VH, and on the right-hand side is the same for S-band. But we could not use this because of only four corners that were provided. So we went back to the SLC data that was provided, but this SLC data doesn't have any co-registration info, the selenoreference information provided, like georeference information. So again, very limited beyond just exploratory analysis. But here the correlation coefficient is much lower, and we are still trying to coordinate with the guys who process this data at ISRO to see if they can correct for any errors that might be there. Also, we don't have any calibration targets on Moon, and so it became difficult to calibrate this data further. Anyway, going ahead with this data, essentially the distribution of the backscatter is Gaussian in dB scale. So on the left hand side is the L band and S band data sets at HH and HV, and below is VVVH, and they follow what we would expect from these products. So one of the first things that we tried was to do a HA-alpha decomposition, and the histogram on the top is the entropy. So the entropy at L band has a peak of around 0.5, but at S band the peak is around 0.7, which suggests that probably because of the smaller rocks on the regolith, at S band frequencies they are much more randomized than L band, which might be penetrating more and hitting the bedrock, where the entropy might be lower. That's my guess. Again, the anisotropy is shown, which is again slightly higher at S band here. And the alpha angles typically are between for L band they are around 20 degrees, while for S band they are a little higher. And so since most of the alpha is below 45, there is a dominant surface and volume scattering present in this case. A polydecomposition image at S and L band is shown. So this one is at S band, and the area of interest for which lies with Artemis probable candidates is shown by this circle in red. And so there is a slight difference between the way that L band and S band are interacting with this regolith. One of them is that there is a lesser contribution of double bounce in L band, while it is slightly more at S band. And the rim and ejecta of the crater show higher volume scattering, but odd bounce scattering is higher in L band. And so this could be due to L band waves penetrating through the upper layer and interacting with the denser surfaces below. There is another area of interest which is okay. So I think, oh yeah. So for another way Hamish tried to do this was to use a model-free decomposition proposed by Avik. And here, in case of L band, we get a higher volume scattering, essentially in these plane regions, while at S band the volume scattering is less. Again, this can be characterized to the penetration in this very flatter regions at L band. But for the crater areas, the decomposition is kind of giving almost similar results, where we are seeing a lot of interaction from the boulders, which are resulting in this dihedral scattering, which is shown by the pink color on the screen. And those areas lie on the right hand side of the images. Also, again with Freeman-Durden decomposition, similar characterization was found out, and the loose ejecta that is spewed around the crater results in a higher volume scattering in this case from Freeman-Durden, both at L band and S band. However, at L band the contribution of surface scattering is also there because of the interaction with lower layers for the lunar regolith. So to conclude this study, essentially the non-availability of cellular reference products limited us to only stick with the SLC, but we could not compare them with optical and thermal data that we sought out to at the beginning. And so that was because, and the motivation for that was, as I said, to understand these craters. High volume of scattering is observed from the crater area, and typically for younger craters as compared to older craters. And we need more SAR data for the moon, but combined with that optical as well as thermal data, but all of them have to be cellular reference to each other, so that proper processing could be done. So that's kind of the conclusion from this study. Thank you for listening.
Okay, thank you very much for this yes, impressive results. So any question from the audience? So if no, I have one. I think you could, based on the polarimetric information, and especially the phase, you could retrieve at least azimuthal slopes, which could be very interesting as to map the topography.
Sure.
Did you try it?
No, not
No,
yet,
not yet.
but definitely that will be something we'll try.
Okay.
And will you have some images with different acquisition tracks? I mean, non-parallel tracks?
No, mostly they are one-time acquisitions.
Okay.
So not overlapping with different tracks.
Okay, and any plan to do interferometric processing?
We would like to, but there is not, the appropriate metadata is not there.
Okay.
That is provided. So.
And sorry if sorry, go ahead.
Yeah, I was wondering about the polarimetric calibration. Have you done the similar calibration using the system on the Earth? So this data could be used for the calibrated data on quiet on the Moon.
No, we have not done any studies on polarimetric calibration, how well they are calibrated.
If I may, sorry if I miss it, but what was the reason behind the choice of L and S band for the dual frequency?
I don't know. That ISRO probably can comment more.
Okay, because I think it's also something planned for the exploration of Venus, but yes, probably there is a trick. I don't know if someone have the answer.
Venus, probably NASA has a mission that is going.
Thanks.
Okay, thanks.
Okay, the last paper of this session is dedicated to tensor decomposition and time series analysis, and it will be presented by Nikita Barsagin from DLR.
All right. Good afternoon from my side. Basically, we've just been to the Moon. Allow me to bring you back to Earth and also do a few decompositions. However, this time we will be talking about tensors, and we will be looking at polarimetric time series and what changes we can detect there. So basically, when you work with SAR data, you often have a few data dimensions. For example, since you have images, you naturally have the spatial dimension. If you have a time series, then you can have a temporal dimension. In addition, if you have polarimetric sensors, you can use polarimetry to get more information about the target. We can have different frequencies, and this is increasingly becoming available. And in addition, we can have the interferometric and tomographic information if you have different baselines. And the motivation of my PhD topic is basically to look for methods where we can jointly analyze several of these dimensions. So typically, we have methods that focus on one or two dimensions, but I'm looking for methods where we can have more than two. And one mathematical way to look into this problem are tensor decompositions, which you can see as a generalization of matrix decompositions. There are a couple of formulations, but today I'm going to talk and focus on the CP decomposition. And here the idea is that we have a tensor X, and we are representing this tensor by a sum of components, and every component is an outer product of several vectors. To make it a bit more visual, I prefer this representation. So we have a tensor here, and it is represented by a sum, in this case, of 3 components, and every component is an outer product of vectors. Now, of course, you can just take this method and try to apply it to SAR data. However, you will quite quickly notice that you need a few extensions in order to get meaningful results. The reason for this is that in the CP decomposition, you always have the same number set. For example, if your tensor is complex, then all your factors will be complex. And by the definition, the factors are limited to vectors. However, for example, if you work with polarimetry, we usually have matrices, let's say coherency matrices, if you work with two-dimensional, second-order statistics. So it would be nice to have a decomposition that directly gives you those matrices and not vectors, where you have to do some reshaping operations. In addition, SAR data typically has a very specific structure, so we want to constrain our solution to really give us some results that are physically meaningful. So we don't want to obtain any matrices, but we really want to have a solution that we can interpret in a physical way. And to make this example a bit more specific, let's define a decomposition where we have dimensions. The first one is polarimetry, and here we're using coherency matrices, and the other dimension is time. So we have a couple of these polarimetric coherency matrices taken at different times, and now we can just stack them into a tensor, which mathematically speaking is a three-dimensional tensor with a shape n by 3 by 3. And we would like to decompose this thing into a few components, and every component is supposed to have a polarimetric factor that describes the scattering mechanism, and a temporal factor, which basically explains how this polarimetric signature is changing over time, whether it's getting stronger or less prominent. And of course, we want to constrain the solution so that our polarimetric matrices are positive semi-definite, basically Hermitian with positive eigenvalues, and so on, as you would expect from real data. Now the question, of course, is how do we obtain these factors? And ideally, we are looking for a method that is generic enough to work not just with this decomposition, but also where you could add additional data dimensions or change your constraints, and the method still should be able to give you a solution. And one way to do it is basically to use iterative numerical optimization. So I will just briefly give you an example how we can do it for this decomposition, but it works the same way for other decompositions. So what we do is we basically start with unconstrained factors, and those can be initialized completely randomly. And in the next step, we basically apply constraints to them, which means we take our factors, that can be anything, and apply a function to them that transforms them into a constrained space, meaning that the constrained factors are constrained in a subset of valid solutions that we're interested in. Once we have this, we can apply the reconstruction function. So basically do the outer product of the factors and sum the components. And now we have basically a reconstruction, a tensor. And this one we can compare to our real data that we have. And what we do is we compute the distance between these two. And in the first iteration, obviously, because we started with some random numbers, the distance between the reconstruction and the data will be very large. What we want to do now is basically to minimize this distance to make the reconstruction as close to the data as possible. And to do this, we can, for example, apply gradient descent, where we can compute the gradients for every of those starting elements in respect to the loss function or the distance. And this tells us basically how we have to adjust those initial values in order to make the distance smaller, in order to get a better reconstruction. And this we do not just once, but we do several iterations. And after this procedure, after we converge to a solution, we have our constraint factors. Now let's see what happens if you apply it to some real data. We are looking at the CropX campaign, which was obtained by DLR's airborne sensor in 2014 in Germany. We have a few frequencies, and as you can see, we are looking at agricultural fields where we have quite a lot of changes in a relatively short period of time. And what is basically changing are the crops. So obviously they are growing. Then we also have some drying effects, changing phenology, and a couple of other things like harvesting and so on. So a lot of changes. And now we are interested in seeing how we can basically characterize them and visualize them. To do this, I'm using a method to basically visualize the changes with polarimetric change matrices. So let's say you have a time series of a few acquisitions in the Pauli basis. So basically, the color coding is noted there. What we can now do is basically to see the differences for every pair of acquisitions. So we have, let's say, in this example, 4 acquisitions, and then we can plot them here as well, and form a change matrix where for every pair of acquisitions, we can show the increasing contribution in this upper diagonal and the decreasing contribution. So how does it look like for real data? Here we are looking at a cornfield in C-band. What you directly see is we have a decreasing contribution here. So basically, at the beginning, we had quite a lot of surface, and over time, it's getting less and less. And we also see a very strong yellow block here. So something is obviously increasing. And this is a combination of the double bounce and volume scattering, where we basically have red and green, which gives us the yellow. Right. Remember, we just talked about the decompositions. So let's see what happens if we compare this change matrix for the original data and for our components, what we have. So the original data, we just had it. And now we can basically plot those change matrices for each decomposition component. And then they look like this. The first thing we can see is that we can now resolve finer details because every component is separate. And for example, in the original data, we had everything thrown together. So you wouldn't see this increase here in this block. This is the first thing. The second thing is we can also obtain the component weights, which basically indicate us how much of the energy is attached to one component. And here we see that the first component has around 60% of the energy. So even though this change here appears to be small in the relative terms, it can be still quite significant in the absolute terms. And in addition, what we get are the time factors, which we can also plot in a line plot and basically analyze how the components change over time. And I find this line plot sometimes a bit easier to interpret than the change matrices, because it's just a line, you directly see if it's getting more or less. This was C-band, where you see that the components appear in more or less Pauli colors, so they are quite pure. If you look at some different frequencies, you might have mixtures of components, where you have, for example, in this case, for L-band, the first component is still relatively blue, so similar to the first Pauli component. But in the second and the third components, we now see mixtures of different scattering mechanisms. And basically, the scattering mechanism is defined by the polarimetric matrix. All right. So this was the polarimetric time series decomposition. I would like to mention a couple of extensions that we can do in order to apply this also to other data dimensions.
So this one you already know, but you can apply the framework to different data dimensions, and one of the candidates would, for example, be the sum of Kronecker products, SKP decomposition, which takes polarimetry and tomography. So this is an existing decomposition, but you could take our framework and implement it there. The advantages are that you now can have more than 2 components than in the original combination. And you also guarantee to have a solution because you're always in this constrained space. So you're always limited to valid results. So the take-home message here is you can apply this not just to polarimetric time series, but you really can combine different data dimensions and experiment with the results. Another extension, which is quite interesting, and we are currently working on it, so I don't have results yet, but maybe next time you see each other. What we can do is to integrate physical models into the decomposition, because previously we had constraints, which was a function, and if you have a physical model, which is also a function, you can replace this basically with a model. And now instead of going from unconstrained factors to constrained factors, you can basically go from physical parameters to your predicted backscatter signal. For example, you can have a Bragg surface model where you have as a parameter the soil moisture. And now instead of obtaining these constrained factors, you can directly optimize for physical parameters. In addition, it is easier to interpret the components because you have a clear physical model attached to them. And since we are working with multidimensional data and we have a larger observation space, we can also, in theory, have more complex models because we have more observables, so we can invert more parameters. All right, let me sum up the constrained tensor decomposition framework. What we can now do is to basically jointly decompose and analyze several data dimensions. We can make sure that our solutions are physically meaningful by applying constraints. And because we are using optimization to solve this problem, the framework is quite extensible, so you can add additional data dimensions or physical models, and you can still basically run the same algorithm as before. That's it. Thank you. I'm looking for questions.
So I imagine we have plenty of questions. Yes, please.
Yeah, thanks for the interesting talk. I wonder, have you tested a crop at a situation with the different harvest dates? I mean, for the polarimetric time series, which is for one kind of crop, but one is before the harvest and one is after the harvest.
You mean in the polarimetric time series, what changes we see after the harvest? Or maybe I didn't get the question.
Yeah, I mean, in this case, you said the harvest at the same time for one crop, but if for one crop, but the harvest time is different. One is before the natural acquisition, one is after natural acquisitions.
I'm not sure if I got the question correctly. So
you just show a diagram or imagine. I think about.
Okay, maybe I go back and then
somewhere.
It's easier.
A bit further. Further.
Takes a bit of time.
No,
Almost
bit
done?
further.
Okay.
You show the different crops with the different lengths of the time.
Ah, okay. I think now.
Yeah, here. So for the example, for barley or for the rapeseed, you have the harvest at the same time. If the harvest at a different time.
So basically, today all the polarimetric change matrices I have shown you were just for corn. So maybe I forgot to mention it on this slide. Basically, if you would have different fields that have different harvest behavior, you would also see different changes there. Because obviously,
If you harvest later, then you have different acquisitions.
So maybe we can discuss later.
Yeah, sure. I have more data on my computer.
But how big area for your test? I mean,
the area that we're looking here are always single fields, and I think the cornfield was quite large, so around 300 by 300 meters. And here I was averaging basically the whole area in order to have just one polarimetric matrix per acquisition. But of course, you can also do it for smaller areas.
There was a question at the back, please.
I want to ask a question about your method, the tensor decomposition method. The input data you use is a whole complex matrix, or you separate it into imaginary part and real part?
So basically, we are using the whole complex data and directly optimizing on them. So it's a complex optimization problem.
Okay. So we can discuss the method by email. Thanks.
Sure.
Armando.
Thank you. Very interesting. Really love these things. The question is regarding the time series analysis. So you take all these covariance matrices, and then you take the Pauli decomposition and the three components. But have you, so this is only consider three numbers there, the three intensities. Have you tried to use some methodology, use all the covariance matrix, maybe performing an optimization, find the one that is changing the most, and then using that one?
So basically, we are actually using the whole matrix in the optimization. So we are really trying to reconstruct not just the diagonal, but all the elements. Here, I was just color coding them, so you can see which elements have what polarization. But in the optimization, we are really using the whole matrix.
So you do an optimization then, it's not just the three elements.
Yeah.
That's good, thank you.
So in the same way, you don't limit yourself. You mentioned in your presentation that you're using rank 1 representations, but in fact, you're using full covariance, full rank covariance.
So the components, the polarimetric components are rank 1. And the reason for it is basically if you use rank 3 components, you might get ambiguous solutions because you have too many degrees of freedom.
Okay.
That's why we constrain them to be rank 1. But in theory, if you have a very long time series with a lot of different changes, you can also go for rank 3 components.
This was another question about identifiability. Okay. Mm-hmm. And the reason for using models is that you want to, if I understood correctly, to avoid making this decomposition only on the orthogonality principle. Then you want to follow some physical scattering mechanisms? Is it true?
So the main motivation for the models, at least for me, was that for some fields we can decompose. And then basically we have components, but the interpretation is sometimes a bit difficult. That's why if you have models attached to specific components, you really know what this component is basically explaining. But the cool thing is you can actually mix model-based components with like non-model-based components. We haven't done it yet, but it might be quite interesting. For example, you have a surface, and then you have something on top of it, and you have a model for the surface, but not a model for the other thing.
Okay, thank you. Any other question or comment? Then if we don't have any more comments, we're going to close this session. Thank you.
Thank you.
Thank you very much. And now I'd like to invite Francesco and Björn to hold this session on the recommendations of the last edition of the conference.
Me too, it was not cold.
So thanks for staying here so late. But I think it's really important that we have a plenary participation. So we profit from the fact that some people cancel their presentation today, and we create this time slot to discuss this recommendation. Of course, during the week, there might be new recommendation coming from the different sessions, and they will be taken into account. We also have a wrap up the last day, and if there are new things, we'll discuss it. But now what we would like to do is to look at the recommendation from the last PolInSAR to see what has been done, what has not been done, and how we could tune or improve this recommendation for the future. So if you, Sabrina, could put the first slide. Sorry. Okay, this is just to remind you that you can use at any time the Padlet to add other recommendation and feedback all the time. So not only now, but all over the week. If you have any idea, please, about possible recommendations and things to be done in this field, don't hesitate to let us know. So this was the first recommendation, which was to create a data set of multi-mission and multi-frequency data on some selected areas like wetland, coastal areas, deserts, forests, oceans, and so on. So the idea is to coordinate acquisitions for present missions and future missions, and also airborne data, possibly to be co-registered on the same grid at level 1 and level 2. So this is the ideal wish. What we've done in the last months actually was to look at the airborne campaigns which exist, at least at ESA side, and there are of course many. We try to characterize them by revisit and campaign duration. So here you have some of them. And ideally, we should identify some specific areas of the type which I mentioned there, and also push space agencies to acquire data over these specific data sets, in order to create the data sets. This has not been done as far as I know. Unfortunately, there is not a serious working group which is coordinating the acquisition of the different missions of the space agencies. So there are different working groups where we could propose to look at this task. For example, in the virtual constellation, they have a group for forest, another one for agriculture, and so on. And this is in fact a proposal which has been done by Laura Frulla, a SAOCOM mission manager. She will talk with Rosenquist of the Virtual Constellation Working Group and see whether for these specific applications, so forest, agriculture, etc., they could identify a site corresponding to your requirement. And then the next step, of course, would be to co-register the data and put them in an appropriate format. That's the easy part. But the most difficult part is to convince space agencies to adapt their acquisition plans to cover these requirements. In the case of ESA, in this moment, for example, with Sentinel-1, we would have problems because after the problem with Sentinel-1B, we have a half capacity, and it would be difficult to adapt our acquisition plan to cover this requirement. For SAOCOM, Laura, who is not here, but she's aware of this requirement, and she presented the recorded presentation this morning, say that we could nominate maybe a person of this working group, of this community, PolInSAR, and act as a project leader for a dedicated project of PolInSAR in the PUMAS announcement opportunities, and request SAOCOM either archive data over these sites, if they exist, or we can even ask for future acquisition of SAOCOM if we can identify site corresponding to this wish list. So I don't know if who could act as a PolInSAR project leader for a okay, so my colleagues are kindly volunteering me. But I would still need your help. So if you have specific ideas on a site where you know that there are already some acquisitions, for example, either airborne campaigns or from one of the missions that are of interest to you, then we could use this site as a test site or a potential super site to make other acquisitions, starting with SAOCOM. So this is just an idea, but of course, any other ideas are welcome.
Okay, now, yeah, thanks. No, I think that's a great idea, actually, to have super sites and to coordinate with other satellite missions. So, for example, for TandemX and TerraStrix, we have super sites, and we can just provide, you know, the coordinates of the super sites, and if you like, you can just adapt it to this, right? But I think there's also other missions which probably have super sites and a lot of data collection over the years, and this can be coordinated, I think, somehow.
For the TandemX super sites, are these flexible? So these are already defined, or we can add super sites to the list?
You can also add super sites to the list, yes. Mm-hmm.
And who is the contact at DLR for doing this? Ah, Irena. Okay.
Me.
Yeah, I was always talking to Costas. Wrong person, huh?
So then, so far, Irena, it's you and me. So we will coordinate each other. But other people are welcome, of course, because we would like to add other missions and start coordinating the super site between different missions, rather than having different sites for each mission. Anybody has additional ideas or proposals for this? In order to proceed with something concrete, because otherwise we repeat the same recommendation every 2 years, but we would like to go to a concrete direction. Please.
Hello, everybody. So it will be good to have these super sites for different applications, for biomass estimation in forestry or maybe agriculture, or just one specific super site.
It would be nice to have a common super site for the different missions. So in the case of biomass, Rosel, we have here the best person to talk to.
Yeah, it's a bit. For biomass, it's a bit tricky, of course, because as most of you know, let's say biomass got a very peculiar orbit, let's say. So we're not, let's say, revisiting a certain area a lot, let's say, apart from the transponder in our calibration orbit at the beginning during commissioning. But of course, in the end, there are going to be, let's say, of course, also for biomass, there are going to be, let's say, specific biomass reference measurement sites that we are going to use, let's say, for our product validation. But of course, those have to be, let's say, dispersed over the entire globe. So in that respect, let's say, we'll need something like 50 to 100 sites overall. And of course, we don't have them all, I believe. No, we're still working on, not yet. So we're still working on trying to get them all. Once we have those, of course, then those will be clear, and we will have KMLs for all these areas and the exact, let's say, delineations of these areas. So you want to say something as well?
Yes, my question is, what's the value of super sites without reference data?
Well, for forestry, for example, we work on a network of super sites where we acquire data on the ground, LiDAR data, and even terrestrial LiDAR data. So it's a very detailed description. Of course, all this costs a lot of money, but at least for forestry, we're working towards this. I don't know, agriculture, there were some in the CEOs, there was some discussion that these super sites also exist, but I'm not an agricultural person. But I agree, yes, without ground data, it doesn't make any sense, yes.
And I think what you need is a collection of where you have ground data and then have the satellites to acquire data there. So the question should be the other way around.
I was just wondering, Irena, for your data, you have any ground data for your super sites?
Yeah, our collection was actually on the PIs. So because each of the super sites that we have defined at the end because there are some PIs behind and they're collecting the data. But this PIs, I mean, we do not have the data of the PIs, but the PIs have the data and could distribute them if needed. So you can ask them actually, and you can potentially get them. I'm not sure how restricted this is, but we have started to work on this. And probably also to mention, we have super sites over very, very different applications. We have over Greenland, so ice, snow, forestry, agriculture. In agriculture, we have also tried to have super sites over areas where we have also ground measurements, so ground measurement stations. The one that are connected with SMAP, for example. We have smaller areas than SMAP has, but there are some ground stations on, available, let me say. And if you're in this network of soil moisture, let me say, then you can also retrieve this kind of data from them. So for each of the test sites, let me say, there are ground measurements, but they are not collected on one server. That's a problem, potentially, right? Because it would be great to have them somehow collected so that you can directly retrieve them. I think this would be immense work, or at least it would be great to have these somehow.
Yes, I completely agree with what was said, and of course, Kostas, that's what I meant. Let's say also with super sites, of course, are of course in the context where we're using satellite data these days. Of course, the areas where we have indeed in situ reference data, and indeed the point is, and it's very clear what Irena mentioned, is that there may be reference data there, but where is it stored? And I think this is one of the things where also Klaus is working on with in the Geotrees initiative to try to get all this, let's say, on a let's say a single stop shop for trying to get this type of reference data. And as a user, that you don't have to just go around and try to ask people whether you can please use their data, etc. So, although some of the we did something a couple of years ago in the Netherlands, trying to put all the agricultural fields in the Netherlands and try to to use all the Sentinel-1 and Sentinel-2 data there. But in the Netherlands, there's of course a very nice, let's say, public data set available from all the farmers that have to provide what the main crop is and the exact conditions, the harvesting date, etc. So this is of course information that we have, let's say, over the roughly 800,000 fields in the Netherlands, parcels, agricultural parcels, but it is not everywhere. And then of course the main point there is still, you still have to create a big data set out of this, because also these public data sets, they make them public, but they're not, let's say, direct, let's say, fully accessible because they're in a strange format, etc. And this is something that the users will have to put some additional attention to try to do this. And there's no single recipe there indeed. And it depends, of course, what was said earlier as well, on the application. So I think super sites are directly bound, of course, with the actual application area.
We have to move on, of course, but it's true that this is a challenging recommendation. It's not easy to do. Maybe that's the reason why there is not much done yet. Also because the in situ data that Kostas mentioned are important, but they would need to be continuously acquired together with the satellite acquisition. It's not enough to have a super site where there are in situ data if then the in situ data are not updated together with the satellite acquisitions. So, tricky point. So if we move on, the other recommendation was to provide tools for multi-mission data processing, like precise co-registration, data fusion, maybe with machine learning. And okay, I know that many tools are being updated with machine learning. And so, for example, in ESA, we have some ongoing activities to inject machine learning into our tools and our algorithms for information retrieval. Now we are working for the next version of SNAP. Well, there is no machine learning for sure. We have new readers for many different missions. Maybe Magda can add something on that.
Yeah, so for SNAP we have, of course, we are trying to implement the readers for the new missions, and now we are working on SAOCOM. We already have ISI, and of course all the other missions that will come. Of course, we are also working on the injection of new products, so we will support all the new products for Sentinel-1, because there are also some changes in the next months. Then for the other tool that you probably all know, PolInSAR Pro. So there is another project that maybe I think in the next slides we have a bit more about that. Of course, ESA, NASA, the multi-mission algorithm analysis platform MAP, that is ongoing project. The idea is that we will be able to process multi-mission data on this platform. There are many platforms. Yeah, maybe Francesco.
Yes, we are also developing ESA many other platforms for higher level products like the ESDL, the Euro data cubes, etc. But they are not thought for L1 data. They will not include SLC data. However, we are also considering in ESA to develop cloud environments for with open source processing for SAR data at L0 and L1 level. So this is something which is coming.
Yes, and to fill this up a bit, let's say also the map was mentioned here, but we fully embrace this concept already within ESA, and we're following up on this what we call now the Advanced Data Access and Processing Service for Collaborative EO, Earth observation. And the idea is that by 26 there should be an operational continuation of the map pilot done, let's say, and operate in such a way that that users can really interact with the data, and this goes all the way, let's say, in principle from level 1 up to the higher level products. So we really are going to put, let's say, an effort here to make something available for the users, that they don't have to play around with data sets, downloading data sets, etc. But you really have, let's say, a computational environment with it. And there's some big budgets involved in this type of activity. So this is something that will be coming and should be operational for the users around 2026. So that's at least for the upcoming missions like Roselle, and as well for the Earth Explorer, this is going to be, let's say, great benefit to the end users.
So we are moving on this recommendation. We go to the next. Sorry, yes, Stefano.
You say that there is no support for SLC data in ESA platforms.
No.
What does it mean?
No, I'm saying we have platforms for high-level products, for example, the geophysical parameters, which are coded on data cubes, but they don't include SLC data. They are for there are maybe GRD products, there are don't know, LAI, NDVI, etc. So this type of parameters which are coded on data cubes to make easy access to users, but they are not thought for SLC data, at least at this time.
Okay.
But it's only specific platforms. Huh? There's other platforms like the map where you have access to all the level 1 data as well. So you have that. Then there's the one that is more for the downstream scientists who are not do not want to deal with SLCs or so, and they can work on the level 2, level 3 data sets that are stored on this, for example, Euro data cube.
Yeah.
I have one recommendation here because I have worked with people having a radar background before, but last 2 years I have worked with computer vision background people. So one thing that I noticed there, that people who works on use of deep learning or machine learning techniques in remote sensing, there is because they have a knowledge gap, so they don't care about some information that we care about, for example, spectral information or this kind of things. I think there are some people working on this, but for example, when they pacified images for deep learning bases, they just simplify and they lose a lot of information. I think some people, we need some tools that people can use it, that we don't miss a lot of information in the data. But I don't think your list, but I think if we are interested in having a plugin Snap, how we want to, how you cope with that kind of information, that we keep the original content of information in the data for deep learning purpose.
Maybe it's interesting for you, Manu?
You have the tools, you have the raw data, you have the product, so I think everything is there. I didn't fully get the question, because you have the tools to go from low-level products to higher-level products. You have the raw data there, so you can go forth and back. So
yeah, I mean, normally the computer vision people, they do a lot of steps like data augmentation or normalization or different transformations, which maybe not interesting for remote sensing people or SAR people. We want to work with the original statistics that we have got it, but they do this and we lose a lot of information. So I think it's important to consider all these aspects, that what kind of transformations are being done for deep learning or machine learning steps.
Okay, so if we now move to the next recommendation, because we also have limited time. So the third recommendation was to try to provide the synergy of satellite systems. So, for example, trade-off between full pole versus dense time series, to also minimize the time difference between acquisition of different satellite missions, ideally simultaneous. Of course, that's not possible, in order to exploit the synergy. So for agriculture, it would be ideal to have a small temporal baseline. For forest, to better separate acquisitions if they are in the same frequency. In the case of multi-frequency, to be as close as possible, so ideally simultaneous again. And then it would be nice also to synchronize different missions, for example, Roselle and Sentinel-1 Next Generation, to help the LC band synergy applications. So what is being done so far? There is ongoing joint research between JAXA and ESA for some specific areas and applications. I don't know if maybe Klaus, you know something about that? No? Bjorn, are you involved in that?
No, okay, from our campaigns group, yeah,
people
people are involved there, yeah. So this is ongoing, and this is being done, let's say, a regular exchange of coordination of data sets that are being needed, let's say, for the European users. So, yeah.
But there's also, I think, the opportunity there, if you have requests for covering certain areas, that you can contact us and we can pass this message on to the people who are involved there. And you can access maybe some ALOS data that you normally do not get.
Yeah, we're also coordinating with the SAOCOM, ESA and SAOCOM, for the preparation of Roselle in the frame of the PUMAS cooperation. And there is acquisition coordination, well, there will be acquisition coordination between Sentinel-1 Next Generation and Roselle. So this is something that we are aware. And there is also an international coordination group for spaceborne synthetic aperture radar missions. I don't know if some of you are part of these working groups.
Yes.
Good. So you can comment on that.
Well, it was recently established a group of all agencies that operate SAR missions. So NASA, DLR, ISRO, ESA, JAXA. And we try to coordinate a bit our activities, and this is not so much coordinating the system itself, but more where we acquire data and if we can complement, and if there's some common interest. So if there is some interest, for example, about the super sites, we can also table it there, and we can try to address this topic there. So if you get a recommendation, for example, from here, then we can bring it forward.
So also on this recommendation, then we are moving. The next one is about the wish for multistatic experiments and simulations, for example, related to harmony. And here I think that Bjorn has some information to tell us about ongoing experiments.
Yes. Now, okay. In terms of experimentation, of course, we closed, let's say, the phase A of harmony last year in July, and now we're currently closing the phase B1. And we had some, let's say, here specifically talking about, let's say, multistatic experiments, more about the campaigns part. We flew last year in March. We flew the PolInSAR campaign. We're looking, let's say, to look at the bistatic geometry and to see how actually, let's say, what we be able to could measure and how good we'll be able to get the bistatic Doppler for ocean current retrieval. And this is something that we've flown, I think, last year. The data is still being processed, so it's not yet available to the community. But of course, like all our data, all our campaign data, you can find it, let's say, on the ESA campaigns website. Sorry. And there you can actually find all, let's say, in principle, let's say, download all of these data sets once they're there. We did as well something over land for Harmony in the French Alps. We have a ground-based bistatic reception receiver, which is actually receiving Sentinel-1 data directly, and but as well, let's say, looking, let's say, in bistatic areas with different polarizations. In this case, we're looking more about, let's say, trying to get a time series, let's say, for interferometric SAR in a bistatic configuration, and there, of course, looking as well at the issue, let's say, of snow and firn penetration over those areas. And all these data sets are going to be made available for Harmony. There's now, let's say, we are planning, of course, future campaigns, and also some other campaigns are being planned. But of course, this mission is going up, let's say, in say 2030. So we still have time, let's say, to build up on campaigns. If there's anything from the community that needs to be done, of course, we're always open to consider this.
So going forward, yes, please.
Yes, yeah.
So just in perspective to rows L, I think would be an interesting row also for L1 probably, potentially, I don't know.
True, of course, yes, yeah. I think there's something, of course, where we can, but the only point is what we see is that, of course, it's not, we don't have so many multi-static, let's say, receiver instruments. We do also have, let's say, some people may know, we have the wideband spectrometer that was built, let's say, as a success to the SnowScat instrument, which is a ground-based instrument, which is going all the way from L-band to Ka band, which also has, let's say, was designed to be extended at some point, let's say, to also bistatic observations. And this is something that we're currently doing to try to extend it indeed, but it was actually built for this. But it was, of course, initially a monostatic, let's say, radar. Of course, okay, it was bistatic, but for a very small bistatic angle because of the separate receive and transmit antennas. But this is something that we are going to do to make sure that we're also going to be able to do, let's say, more looking at, let's say, scattering, multistatic scattering, investigation, etc. And then we can cover multiple wavelengths. But as you know as well, let's say for airborne campaigns, it's a bit more tricky. And of course we have C-band now, but of course this needs to be as well extended to other bands if you want to look into this. Yes. Yeah.
Good. So if I go to the next, the need to have studies regarding retrieval and electromagnetic models. So to put more effort in modeling to prepare studies and tools on multi-frequency mission data and studies opportunities for the research on retrieval and electromagnetic models. For example, forward and inverse should be launched by ESA and by other space agencies. So what we have presently, okay, we have in PolSAR Pro a vegetation scattering model. It's called PolSAR Pro Sim, but of course it's limited. And then there have been ESA activities just launched in this direction, like the GAFA and the Ocean Electromagnetic Model. Maybe Bjorn can spend a few words on those.
Yes, of course. Yeah, so there was some question today, I think, from Marco about, let's say, SAR processor and whether, let's say, we are developing something in this extent, let's say, also in Europe. This is, let's say, as it says, geometry and frequency agnostic. So you're able, let's say, to do either whatever wavelength, but also, let's say, whatever type of SAR geometry. So looking at, let's say, of course, principal build, let's say, for spaceborne spaceborne geometries, but including as well geosynchronous, but also for LEO and covering, let's say, both monostatic and bistatic observation geometry. So it's been already fully, let's say, validated for Harmony and Sentinel-1, and we're now extending. Now, once this activity will be finalized by the end of this year, we plan to extend it as well to make sure that it can also read ERS and NVSAT level 0 as well, so to be able to process this. And that will be really nice because then we have a unique kernel that's able, let's say, to process process all this data that we've been flying, at least in, let's say, with our C-band SARs. Regarding the ocean electromagnetic model, this is a model. I'm not sure if we already made it fully available, but it's able for people to put, let's say, kind of the different SAR geometries again to check how the ocean response is specifically for SAR. But also on top of this, there's as well in the context of Harmony, which is all the overall development that we're now doing, especially in the Earth Explorers, is completely open science. So in principle, all this material is going to be made available through the ESA websites. And sometimes it takes a bit of time before all these things are becoming public. But in the end, they will be all becoming public. So all these also for all these forward and retrieval models, they're all going to be, let's say, they're all going to be made available. And as well on top of this, we're now as well working on libraries for forward and retrieval models for EM scattering. And this is also an activity that's ongoing and will be closed within the next year or so.
Thanks, Bjorn. So the next one, okay, here we didn't have done much. It was to include wetland and coastal areas among the sites for multi-frequency acquisitions because they are of great importance for many different countries. So this maybe is something that could go together with the first recommendation regarding the so-called super sites. We, for example, informed the SAOCOM mission manager, but as I said, so far, nothing has been done, to be frank.
I think it comes back to the comment from Irena. When you come with a properly observed ground site, you will also find interest by the mission manager side to cover these sites. But just on suspicion that something might emerge in future, I think it's very difficult to justify additional acquisitions. So we will first need to identify the groundwork.
So the next one was about the new science opportunities that should include also subsurface studies for multimodal data, for example, combined with frequency, polarimetry, and interferometry. And this would open incredible opportunities for biophysical parameters at different depths in preparation for biomass and Roselle. Yeah. And also have forest disturbance studies. This would be very interesting if we could use full pol data at different bands. So there are some ongoing studies, I understand. Maybe Klaus can comment on those.
Yes, so for biomass, we were planning for some months or even years to fly a campaign in the desert, in the Namibian desert. And we were already quite far with DLR to prepare all the flights, and we were stopped actually last minute by the Namibian government who didn't allow or didn't give us permission to fly. So this was one opportunity we missed. And of course, it's now a bit difficult to find new sites. This takes again quite some time, but we are preparing for this for biomass. And there are some ideas that we do some ground observations so that once biomass is available, at least we have the ground observations to validate those observations. But in terms of airborne campaigns, it's a bit more difficult, I would say. Also because many of these areas are in regions where you cannot easily fly a P-band SAR system. So this is a bit an open question, might change once biomass is launched. On the Antarctic ice campaign, well, I should hand over to Björn because he's the ice man.
Yes, I will tell a bit more about as well tomorrow in my tomorrow morning my presentation. But we do have we're planning currently a campaign that should take place at the end of this year for the Polaris system to fly in Antarctic for doing different things, both looking at the ice shelves, but also looking at, let's say, the potential to check out for a potential calibration target for the biomass mission once it is in orbit. So more about that tomorrow, actually. Yeah.
Well, and then the last 2 points. So we had one study coming out of these recommendations as well to look at in forest change over the Amazon. Was a big study using Sentinel-1 data that came to a conclusion actually a few weeks ago. That was quite successful. Also looking into polarimetry and how you see changes in this polarimetric, well, polarimetric data. It was not full data, but that was closed. The other thing that is actually more interesting maybe for this audience here is Carbonix, is a new campaign that actually emerged quite fast and more by coincidence, I would say. But Irene will report on this tomorrow, Friday. Okay, we'll have a presentation on this campaign, which is a revisit of the AFRISAR campaign sites, I think 7 years after the first flight. So we will be able to look into change and how we see this change at different frequencies.
So on this recommendation, luckily we have something to report.
Even presentations, huh? So
Even presentations, yes. Yeah. Good. So the next one it was about PolSAR Pro, the fact to implement PolSAR Pro functionalities also in Python and to be implemented on MAP, the multi-mission platform. And actually something which is ongoing. Madda can report about that.
So it's nice also to report on that, because 20 years ago the recommendation was to build PolSAR Pro, and after 20 years we have recommendation to re-implement PolSAR Pro functionalities in, let's say, modern programming languages, language actually. So we have since November 2022 we have a project with SATIM. It's planned for 24 months, and this is to re-implement selected PolSAR Pro functionalities in Python. And these functionalities were defined during the last PolInSAR. Of course, it's in Python. We prefer to use the efficient and the most popular libraries. So this is ongoing activity. We are already, yes, okay. So the first set of the functionalities you see here in the first phase. So we are in the middle, more or less, of this phase. And then in the second phase, you have in the next 12 months, we have other decompositions and other functionalities that will be implemented. You can.
Just the fact that the work is being done by this Polish company, SATIM, but it's done in cooperation with Armando Marino and Eric Potier. They are in charge of the scientific validation of the results. So, and of course, in case you would like to be involved, please contact Armando and Eric, and the contributions from everybody. This working group will be welcome, of course, to test these new functionalities.
Sorry? Yes, okay. So if you have any specific wish of the priorities, however, I mean, the list of priorities is quite well defined, but if you have any specific suggestion, you are open to that, of course. Yes. The next recommendation was about the PolSAR Pro Bio, about the continuation of the PolSAR Pro project. So here it's a bit tricky. The PolSAR Pro Bio exists, and it is doing very well. And of course, we are still maintaining the software. If there are any bugs or any needs, specific needs, we are always trying to answer to that. We have, so you can download PolSAR Pro from the website that is specified here. We also have a set of nice test data set that you could use, especially maybe for new people in the community. You could use for your tests. And we don't have any new plan activities regarding PolSAR Pro Bio. However, there is a next slide. Okay. Yes, maybe the one that is remaining, the activity that is remaining regarding PolSAR ProBio is the SAOCOM toolbox. So this is almost ready. There are a few, as Eric says, there are a few bugs to be fixed. So I hope it will not take too long. We were planning, of course, to support ESA missions, but this depends on the availability of the sample data. So this is something that possibly can be done in the future. I would like to comment also on the recommendation 11. So for the, we should avoid duplicate efforts between PolSAR Pro and SNAP. So for now we have some polarimetric functionalities in SNAP, and we are maintaining this definitely. In the current SNAP contract, we don't have any plans for the development or implementation of additional polarimetric functionalities. And regarding the bridge between PolSAR ProBio and SNAP, the thing that we have currently will be maintained, but we will not do any further development in this direction, since let's say we have many new versions of SNAP. Let's say every 6 months we have new release, and sometimes it's a bit it's not working well with the PolSAR Pro. So since we don't have any ongoing live projects with PolSAR Pro, I think we will stay with what we have now, and we will not further develop common functionalities.
So I think that's all. So these were all the recommendations. We should confess, maybe Madda didn't say that, we have been a bit slow recently with the PolSAR Pro development. That was also due to health problems of Eric, but hopefully by the end of this year we should complete the remaining tasks of the contract, and we should close the contract. It will remain a separate toolbox, so even if we are implementing the functionalities in Python, we will continue also with the present version of PolSAR Pro, following your recommendations, and we will maintain it and distribute it.
Maybe one more comment. Also, we had some comments from teachers from the last training that we had last week, that in fact PolSAR Pro is a very nice tool still for didactics, for education. And Carlos was really confirming that they are still using, it's still used at the university to teach students. So this is one of the, I think it's good, and we should maintain definitely PolSAR Pro for, at least for this reason, if not for others.
Yeah, just a quick comment about SNAP. So it's true what you said, Magda, that in the current contract there are no plans, but since biomass is launched relatively soon, and roll cells in the pipeline, and we have a program called SUP, so Central User Preparation, we will add polarimetric functionalities as needed. We will also support NISAR fully, so level 1. So things are coming. So I don't think that, yeah, maybe we should revise those sentences a little bit there.
Okay, so I think that was all concerning the past recommendations. I would propose, if it's not yet the case, that Sabrina put this online so that you can access this presentation during the week. And if you have additional ideas, comments, recommendations to go on during this week, please use the Padlet to add your input online, and when we review them, and maybe on Friday when we do the wrap-up, we could go through new recommendations coming from the audience.
And the paper boards in the icebreaker.
Good. So I think that's over, and we can move now to the icebreaker.
No.
No? Sorry.
No, photo first. Photo first. So before everyone jumps to the beer and to the sandwiches, please come to the floor. And we make the photo here. And exactly. And then we make quickly a photo, and then you are free to enjoy your break.
But you remarked that I changed it. Yes, yes, this morning. You said me, yeah, it might be complicated. Well, it was not complicated. Exactly, yeah. But since I have a list of things which I have priority, of course.
Really? I was surprised because we didn't even announce it, huh? We didn't make an announcement. Can you please quickly come to the front? Then we can make the photo and then have a beer. Please come to the front. So the only thing is who is taking the photo.